Okay, good morning everybody and welcome to our third day here at Physics and Reality. We'll be starting today's programme off with our third topic block, Metaphysics, Quantum Theory and Applications to New Domains. And it gives me great pleasure to introduce our first speaker this morning, Professor Tuomas Tahko from the University of Bristol, who'll be talking to us about mapping the space of scientific possibility. Over to you, Tuomas.
Thank you for being here. The talk today is bringing together some of my work on metaphysics and epistemology of modality, so possibility and necessity, and scientific modeling more generally, as well as ontological dependence. So I'm trying to bring in a couple of different threads, and there's quite a lot of different threads to bring together and very little time. So I'll try to be brief and leave a little bit of time for discussion if you want any clarification on anything, but hopefully we'll get there. So the starting point here is that when we do science at the cutting edge, we do need to delimit our efforts. We need to choose which avenues we pursue, and that requires focusing on the relevant possibilities, the relevant possible directions for future science that we think do have some sort of viability, if you like. But the problem is we don't always have a clear sense of what is relevant, so we end up pursuing all sorts of false directions, and indeed in our modeling efforts we end up idealizing and pursuing false models. Indeed, you might think that it's necessary for scientific modeling to pursue those false models. So we need to make some sort of decisions about which direction we go to. It looks like a lot of our scientific models then end up having non-actual or false targets, because we might even expect from the outset that the model that we are dealing with doesn't exactly correspond with reality. So we have to find ways to assess those models, assess the viability of those models. Now, there's a big literature on scientific modeling on this, and I'm not going to go through that, but that's kind of on the context of this type of efforts. So the point is that we have to find some ways to delimit our efforts, some ways to decide which possibilities to pursue. The image here is supposed to be inspired by the pursuit of dark matter, which is a good example, I think, of an effort to explain some data from gravitational effects by postulating something that would fit our current understanding. But obviously, there's a lot of uncertainty in the area of research like dark matter or alternative cosmologies. So we need to decide how to delimit those efforts. Okay, so that's the context, but I'm going to jump straight into my own way of thinking about these sort of relevant possibilities, which relies on a framework of ontological dependence that I've worked on for quite some time. I'm not going to give you the full background of ontological dependence. If you're interested, I refer you to my Stanford Encyclopedia of Philosophy article on ontological dependence. But I'll give you these two definitions. A rigid and generic version of dependence. So we might say that X, we'll get to what that might be, that X entity, depends rigidly for its existence upon Y, another entity. Well, that just means that necessarily X exists only if Y exists. So you might think that this conference, if it is an entity, exists only if Paavo exists, because Paavo has put us together here. Perhaps also Tuomas, Suntola, and various other people, but Paavo is definitely one of the entities that needs to exist for this conference to exist. So the existence of this conference, in fact, necessitates the existence of Paavo, we might say, since we're here. Good. And the generic version, which is actually what I'm going to be focusing on, is just a more general version of this type of dependence. So we might say some entity X depends generically for its existence upon the F or the Fs. That means that necessarily X exists only if the Fs exist. So to give you another example, also a bit of a toy example, but nevertheless, CH4, methane, depends generically for its existence upon the existence of carbon and hydrogen. atoms. So both of these Fs Fs would be carbon or hydrogen in this formula. So we can use this type of generic dependence relation to express dependence relations where a type of entity is needed. So the methane molecule, the methane kind, if you like, depends for its existence on carbon and hydrogen, but not any particular carbon and hydrogen atoms, unlike in the case of the rigid dependence that I just gave you. It is the particular barber that this conference depends on, but the CH4 molecule is dependent on any carbon or hydrogen atom, as it were. Okay, so I said I'd tell you a little bit more about what the X's are there. I'm going to have a very broad understanding of what you could put into those formulas. So we can talk about entities in a very general sense. Entities would be the broadest possible category that we might be interested in. And the point here is that we could be relatively neutral on the ontological structure of reality. We might be able to accommodate views which don't have substances, such as ontic structural realism and so on. We probably want to refer to properties in some way, though, such as charge, spin, mass, perhaps relations themselves as well. You could reify the relations if you need to. We can debate about whether properties are universals, whether they're tropes, and we can be nominalists about them. We can be Aristotelian, such as like myself, about these properties. But in principle, you could formulate those ontological dependence relations quite regardless of what your metaphysical underlying commitments are. Indeed, you could be neutral about the existence of substances. You could treat them just as bearers of properties or bundles of properties. You could think that there's a mutual dependence relation between substances and properties. You could be committed to the principle of instantiation, just as Armstrong famously proposed that properties always have to be instantiated in a substance. You can be committed to natural kinds as a genuine ontological category, natural kinds such as electron, gold, and water, or you could treat them as bundles of properties of some sort as well. So I'm going to be neutral about all this, but there is one commitment that you will need if you're going to use this type of framework, which is there needs to be some categories of reality. You have to be committed to a categorical ontology. But that, I think, is not going to be a very strong commitment because there's very few fundamental metaphysics, fundamental ontologies that wouldn't be committed to some sort of categorical structure. In fact, even those philosophers who say that there might not be any categories turn out to be committed to at least one category at the end. Usually it's something like a substance or a property. So it's very difficult to get by or to do philosophy or science, for that matter, without a commitment to some sort of categorical structure. And the ontological dependence relations that I'm interested in are, in fact, fundamentally relations between these categories. So you might have a view about how properties are related to substances, such as principle of instantiation, as I mentioned. So a property must always be tied to a substance, if you like. To give you a more concrete example, the charge of an electron must always be the charge of an electron. So the charge doesn't exist on its own, and indeed the electron doesn't exist as a bare particular without any of its properties. So there's some sort of a connection between the relevant property and whatever entity possesses that property, as it were. But as I say, all of these are debatable connections. There just needs to be some sort of formal ontological framework that connects these categories together. Okay, so much more could be said about that, but that will hopefully give you some idea about the background. So now when we start mapping these formal ontological connections, we're effectively mapping the identity and existence conditions of the relevant entities that we're talking about. Those dependence relations that the formal ontological framework would give you will give you those dependence, will give you those identity and existence conditions. And these will all have modal implications. As you could have seen already from the formulation of ontological dependence that I gave you, if we say that the X depends for its existence on Y, we may say that the existence of X necessitates the existence of Y. And indeed, we might have cases where the existence of some entity makes it impossible for another entity to exist. These are more difficult to think of a good example, but you might think that two contradictory properties exclude each other in this sort of way. Or you might somewhat more speculatively say that, well, since we have discovered oxygen, it means that phlogiston can't exist because they aim to explain the same sort of phenomenon. How to map that out exactly is a more complicated matter, but you get the idea. However, we also often consider in science entities that are, or at least seem to be, non-existent, such as yet to be synthesized transuranic elements, which I'll be talking about a little bit. So we need to be able to state these identity and existence conditions for entities that we can't directly observe or measure. We have to postulate those identity existence conditions from something else than a direct measurement of that entity. And I do think we do that a lot in science. Now, fortunately, we are often able to state those sort of identity and existence conditions for entities that don't actually exist, and the relevant properties as well with remarkable accuracy. And I think the history of the periodic table is a very nice example of this. So you might consider Mendel's predictions. Mendel predicted a lot of elements, but at least we often think that he was successful in some of those predictions, namely for gallium, scandium, and germanium, and many of their chemical properties as well. I have a little quote from Stewart here. By prediction, he says, Mendel meant not only that an element of the right atomic weight would be found, but also that it would have properties, such as highest oxidation state, oxyacid formation, atomic volume, metallic character, and so on, corresponding to those of lighter analogues in the same group. In this sense, he made only 3 complete predictions, and his method, illustrated in detail only for these 3, was to interpolate from low analogues and higher ones if available, and from neighboring elements. Now, none of this sounds particularly surprising, probably. This is the nice feature of the periodic table, which is why I like to use it as an example. It gives you an idea of the dependence relations between the various elements, just the way it's set out. And in fact, it gives you a very nice method of also predicting the properties of the elements based on their location on the periodic table. Now, I should say it's not always that neat, of course, and notorious for Mendeleev. He wasn't able to place the lanthanides anywhere, and of course the noble gases he struggled with, partially because their relative non-reactivity. So the method might not be perfect, but it certainly worked for Mendeleev, and that's why we're still using the periodic table. Okay, so let's go into a little bit more detail with my actual case study on super heavy elements. Now, super heavy elements are transuranic elements, but we're focusing at the heaviest end of transuranic elements as well. So typically we're talking about elements with an atomic number greater than 103. Now, there's a lot to be said about the background here, but I'll focus on one specific feature, which is specifically tied to the stability or non-reactivity of these super heavy elements. So Maria Goppert-Mayer did some important historical work on this, and her model connected the orbits of neutrons and protons on their shells with the particle spins. And it turned out, I suppose unsurprisingly, that some combinations of protons and neutrons produce higher stability. But some combinations produce particularly high stability. And it was Eugene Wigner who coined those combinations the magic numbers. So the magic numbers that we currently recognize, that are currently recognized, are as follows there. So 2, 8, 20, 28, 50, 82, and 126, which corresponds with a speculative, yet to be synthesized super heavy element, umbihexium, with atomic number 126. Now, the list may go on. You can continue predicting what those magic numbers might be based on the relevant combinations of protons and neutrons, but it is, of course, speculative. Now, currently, the heaviest element synthesized is 118, which has been named organesson, but that is not one that features one of these magic numbers, and indeed, organesson's half-life is measured in microseconds rather than anything longer than that. So it's definitely not stable. But there has been speculation for a long time in this work on transuranic or super heavy elements on islands of stability. And we have, of course, been able to measure these for a lot of the magic numbers that I mentioned. There's calcium featured there, for instance. But it gets more interesting in the super heavy end of the scale. So in this picture that I've just borrowed from Wikipedia, because it's a very nice picture, we have a seeming island of stability here, while there's instability in between around the neutron number 178 and proton number 1112, which corresponds to the super heavy element Copernicum. Now, I should perhaps say that even though we're talking about stability here, the half-life of the heaviest isotope of element 112 Copernicum is still in the range of 30 seconds or something like that. So it's not exactly stable in the sense that we usually might think of stability, but it is relatively stable compared to the other elements in the super heavy range, if you like. So Copernicum, I think, produces, when it decays, produces Darmstadium, which has something like a half-life of 15 seconds, and then we go down from there. So nevertheless, there is a bit of a strange feature of the periodic table at that end, and we need to be able to explain that, and we are able to say something more about that when we look at those magic numbers. Okay, so let's look at that speculative, still I should say, element umbihexium, the element 126, which does correspond with one of the magic numbers. Now, and I stress this again, this element does not exist. It's not even clear that we have the means to synthesize it. It could be technologically impossible to do so if we don't have particle accelerators with high enough energies. But it seems that we can nevertheless state some properties that this entity would have if it were to exist. So we can state counterfactuals, which are true, or so I argue. But those counterfactuals cannot be made true by the entity itself, because the entity does not exist. And indeed, its properties don't seem to exist either. So here we would seem to have a counterfactual about a non-existing entity or a non-actual target for our modeling activities. And yet we still think, and I think correctly, that we can say some true things about this yet to be existing entity. Now, of course, you can see the pattern that I'm going here. The model here is very nice for super-heavy elements, but if this works for super-heavy elements, this is the trajectory of the talk, well, then we can probably use this type of method for other speculative areas of science as well, where we do need to consider scientific models with non-actual targets or false targets, and indeed counterfactuals about entities that do not exist. Okay, so that's the kind of counterfactual that we might consider. If umbihexium existed, it would have a longer half-life than organesson. Now, I think I can say that counterfactual to be true with a great deal of confidence, because if you recall, I noted that organesson has an extremely short half-life, measured in microseconds, one of the shortest of the super-heavy elements. But we know something about umbihexium, specifically umbihexium isotope 310. It appears to be doubly magic. Now, what does that mean? Using Wegener's numbers, it means that it has an isotope with a neutron number that's equal to one of the magic numbers, namely 184 up on the scale, in addition to the proton atomic number 126. And 126, as you recall, on the list was one of the recognized magic numbers. 184 is, of course, a bit higher than the currently recognized list suggested, but we get this doubly magic effect with that. Now, you might compare that with calcium, so element proton number 20, which has two magical isotopes, actually. Those are the ones with neutron number 20 and 28, which are both in this list of magical numbers. And if we compare the half-life, if we compare the stability of those isotopes to the binding energy that we can calculate with the Weizsäcker formula that's widely used for this, so binding energy of nuclei, then both isotopes have a much higher binding energy that would be expected by using this standard method. Okay. Now, I'm not going to go through this diagram in any detail, but we can come up with a fairly nice prediction, it turns out, for why we have this higher stability for the magical isotopes. So the energy states of the nucleons and their positions in this potential well that's pictured here will give rise to higher stability, specifically in cases where we have closed shells. And the nucleons with the closed shells have a higher binding energy. So we're looking at the relevant entities here being the neutrons and the protons and their relative numbers. And certain combinations of these produce closed shells, which produce the higher binding energy, which gets us to the lower reactivity and the higher stability. Okay, so these will vary according to known structures of binding energies and their energy levels. Now, of course, there are uncertainties, but we can get some fairly accurate and very reliable predictions of where those islands of stability might be, based precisely on these complete nucleon shells or closed nucleon shells. Okay, and we see the element 126 being pictured there, or the proton number 126 being pictured there. Don't ask me about the details. This goes beyond my my physics and chemistry ability, but I take the word that we have reliable methods to produce those. Okay, so I've given you a very rough sketch, and it is a very rough sketch of how we might use this type of method. But how do we fit it back to the model that I started out with, that deals with ontological dependence and the categorical structure? Well, we have to recognize the relevant entities that we're looking at, of course. And it seems that the relevant entities here are perhaps substances, if you think there are such things, but certainly properties. So the nucleons, we're looking at the nucleons and the relevant energy levels of those nucleons. Now, you might understand those nucleons in various ways. You don't have to put them into a substance ontology, but you have to account for them in some way, and you have to account for their properties in some way. So in whichever way you decide to do that, those seem to be the relevant entities that are involved in this model. And now I referred to the shell model of the nucleus, and that seems to really be the key in the work that goes into predicting the properties and specifically the stability of the super heavy elements. So the shell model of the nucleus and Gopper and Mayer's work on this was key. Tells us which shell a nucleon enters, and that depends on how many nucleons there are altogether, of course, because the nuclear model, the shell model, gives us that structure. So if you like, you could look at the nuclear shell model itself as something that specifies the dependencies between the nucleons, if you like. And thirdly, of course, the energy levels and ultimately the stability or the reactivity of the nucleus will depend on these first two steps. So the relevant entities themselves as considered in a more singular fashion and the properties that they have, and then the combinations of these nucleons when they get combined into elements. So again, still a rough simplification, but it gives you at least a hint of what kind of dependent structures we're dealing with when we're trying to calculate or trying to predict those properties of the superheavy elements. Okay. I think I'm doing quite well on time, so I can take my time with the summary and leave hopefully a good deal of time for discussion, so we can specify any aspects of this that are of interest. So I haven't said much about this, but my own goal here really is to produce what we might call an actualist analysis of modality, or the possibility structure. So there's just one world. There's no possible worlds. There's only the existing entities. And then there's the problem that I pointed out in some detail, that we need to consider entities that do not exist and counterfactuals that consider those entities that do not exist. So the problem here is giving truth conditions or truth makers, if you like, for those sort of counterfactuals to consider what look like possibilities, but we only have the actual entities to appeal to. Now, the suggestion here, which you can probably infer already, is that there are still some relevant properties of actually existing entities that contribute to the analysis of these sort of possibilities. So whatever we might say about the element 126, which doesn't exist, well, if those counterfactuals that we said about it are true, well, they are made true by properties that we are already interacting with, properties that we already have a good deal of data about. You know, things like charges and those combinations of the nucleons in the nuclear shell model. Now, ultimately, if this sort of framework works, every scientific possibility, indeed every metaphysical possibility, if you're so inclined, will be possible to be expressed in terms of these sort of dependent structures. Now, I mean, they're not always going to be very simple dependent structures. Even in sort of seemingly simple cases, there's a lot of different dependencies to consider. And in fact, I think that it's a problem, if I may say so, in the usual literature of metaphysics of modality, that we tend to isolate the possibilities, tend to isolate the counterfactuals and consider them in independence quite separately from all the other things that might be relevant for that given possibility. So, I mean, we have to do that in practice in scientific modeling as well. When we deal with idealized models, we remove some variables, and we do that knowingly. But it seems to me that in a lot of the philosophical literature, that aspect is forgotten, that you still have to slot it back into the actually existing network of dependencies if you are going to say anything meaningful. Okay. Now, the hope here is that we have no need for a framework of possible worlds, but actually each of the viable combinations of the dependent entities that we might discuss, if you like, you could call it a possible world in the usual sense. It could be considered as such, but you don't need to reify these possibilities. You're just talking about a candidate set of identity and existence conditions, and well, if it doesn't exist, if those entities that you're considering don't exist, well, then you're not really dealing with a genuine possibility. So I try to avoid this terminology of possible worlds. Now, there are epistemic difficulties in proceeding with this, as always, with modality. So how much confidence should we assign to the relevant potential identity and existence conditions combinations, the different nodes in that sort of framework of dependencies, if you like? Well, I think that that's a problem for everyone, and we can handle it in the usual way, depending on your preferred framework. So I think that we should have a joint effort in model epistemology in settling that epistemic difficulty. But I have just been focusing on the metaphysics of the modality that underlies here. And I think that the fact that we are able to make those predictions, for instance, in the case of superheavy elements, that worked as my case study here, does speak in favor of us being able to sometimes overcome those epistemic difficulties as well. So I think I'll stop there. Just a couple of references for you for further interest, and happy to specify anything that might be unclear. Thank you.
Many thanks, Tuomas.
Thank you, excellent and a very clear presentation. I have two interrelated questions, but maybe I'll just ask one because we don't have that much time. So first, you said that we need some sort of categorization in any case. Could the categorization be pragmatic? So because in some sense it sounds to me that you're saying like, okay, we have to start from some sort of theories or models or whatever about the world, and then we say that things are possible or impossible or necessary related to those theories and models and whatnot. But do we have to say anything about the like more in-depth ontology of these things? We would just say like, okay, according to this theory, this is necessary or this is like possible or impossible or whatever. But we don't have to say anything about substances or properties or essences or whatnot. Could we just say like, according to the theory, and that's that?
Thanks, Hilbert. Good. You'll notice I didn't mention essences this time. but you're not mistaken that my own framework is essentialist. Now, yeah, I mean, you don't have to mention these things explicitly, but I mean, as a matter of fact, when we engage in the modeling activities, we do make those assumptions implicitly anyway. So you make it, well, for instance, an implicit, well, it's not that implicit, explicit connection to or commitment to properties of some sort. So it's difficult to deal, as I said, without some reference to properties such as charge in your theories or your modeling activities. Now, how you treat that charge in your fundamental ontology, there are different ways of doing that. You could consider it to be tropes or universal properties or whatever, and that might make very little difference to your relevant modeling activity. So in that regard, it's yes, there's some pragmatics involved there, but ultimately, if you're going to give a full ontological picture, you know, it would be better if you do it explicitly rather than let be guided by implicit commitments. Now, as I say, the framework that I've presented is intended to be relatively neutral regarding these things. So I'm not defending here today the need to do that sort of work. But any kind of modeling activity like this will make some sort of implicit or explicit commitments to some sort of categorical structures. So there might be alternative ways of doing it, of course, and then you might get competing theories. Yeah. So I'm partially at least agreeing with you.
Thanks. So I'm curious what your metaphysical picture of laws or whatever gnomic force is, because it seems as if in order to really underwrite the truth of the counterfactual claims, you're assuming that you have certain true law-like things, models. But however, you're not going to want to say that laws are just sort of the set of possible worlds that are consistent with the laws or something like that. So if you're denying a modal analysis of law, what is the picture you have, and how does that underwrite the truth of the counterfactuals?
Yeah, good. You're not mistaken. There's work to be done in terms of the connections of this type of framework to laws. Now, it won't surprise you probably that I'm not Humean about laws because it would interfere a little bit with what I want to do. I think it's possible to use a framework not unlike this one to deal with that, but you would have some difficulties with it. So in my view, the laws will be closely tied to the natural kinds that you have in that picture. So let's say electron is a natural kind. You'd get the laws from ultimately from the relevant dependencies that those kinds feature in. So I would build the laws from that kind of picture. Now, the sort of pictures that you see in the literature, this comes close to something like a dispositional essentialist analysis of laws. So you get them from the relevant properties and the natural kinds that possess those properties. I mean, there's some room to tweak this up, but I try not to be very explicitly committed to this type of view because I do think that you have options there. I mean, you could be primitivist about laws, obviously, if you want in this type of picture. That would work just as well. Admittedly, it might not fit that nicely with a Humean picture of laws, but it's not impossible to do. Thank you.
Hey, excellent and clear presentation, as mentioned. I have two questions also, short. Rigid dependence and generic dependence, what differentiates them? What ontological criteria differentiates them?
Sorry, so what's the difference between the rigid and the
Yes,
generic?
What is the criteria, metaphysical or ontological criteria? Because like it was first very clear that you say Paavo and hydrogen, but I'm not so sure. Paavo might be an entity itself, so which one is generic and what is rigid? Yeah,
good. Yeah, I could have been a bit clearer about it. So, well, I mean, Paavo is a prime example of an individual entity, I think, who might have an individual essence. Now, I'm not committed to that, but if that is the case, you know, entities such as humans might seem to differ from each other essentially or by their nature, whereas two distinct hydrogen atoms do not seem to vary from each other in any sort of relevant essential properties except their location perhaps or something like that, and that doesn't seem essential to the hydrogen where it's located. So if you look at sort of generic dependence relations, they're often such as the example a CH4 molecule. Well, there's nothing particular about that CH4 molecule that makes it so very different from any other CH4 molecule that we would need to be able to state. Now, whether you have to state that in the case of humans, I actually don't think that you do, but some people would. So to express that commitment, you would need rigid dependence relations as well.
Okay.
But for my purposes, the generic ones will do the trick, actually.
A bit given, I would say, natural category difference. But
Yeah.
okay, then generic dependency. Okay, I catch you up later on. Thank you.
Thank you. Thank you. I'll try to be brief.
Just clarification. I mean, I take it the actual contingent fact of whether the element really exists isn't really crucial either way here. I mean, I imagine there probably is some of these things created out there in supernovae. There's an awful lot of energy out there. Yeah. But I take it that's the point is even if in fact there's some whatever I can't remember the names of these things, unbinhexium or whatever out there in the cloud of some supernova a billion parsecs away, we want to say, look, the existence of that thing out there is not what explains these counterfactuals we're saying in the lab. It would still be the dependence relations in the here and now.
Good. Yeah. I mean, I suppose if there were some actual instances of that element, well, we could refer to it. But it seems clear that we have some cases where we will make predictions about things that we know not to exist. Well, I mean, you know more about the relevant physics probably, but I think it's very unlikely that some of these super heavy elements would be naturally occurring. But they have discovered some of them.
Yeah, I mean, supernovas just have a lot of energy in. That's
yeah,
what I thought.
yeah.
But it looks like it shouldn't matter, is the point. I mean,
you're right.
The story shouldn't be sensitive to that kind of thing.
You're right. I mean, we can't just point to it. So,
yeah.
So in actual fact, we need to make the predictions on the available data, and
right.
We don't have any available data about these things.
And indeed, my prediction that there is some in this supernova is based on these antecedent facts about it I couldn't have analysed.
Precisely. Yeah, precisely.
Okay, thanks.
Yeah, that's right. Thanks.
Well, we'll leave it there. And yeah, sorry to anyone who didn't get to follow up on their questions and stuff, but I'm sure Tuomas will be happy to chat in the break. And
thank you very much.
Thanks once again. Okay, I'm very glad to introduce our next speaker for this session, which is Professor Marilu Chiofalo from the Department of Physics at the University of Pisa. And Marilu will be talking to us about a quantum toolbox for neurobiological sensory systems.
Thank you so much, Alex, and good morning. It is a pleasure to be here in such interdisciplinary and open-minded audience and context. So warm thanks to the entity, PAVO, and all the organizers for this fantastic get-together. Okay, so I will be talking about quantum physics and reality under the perspective, the angle of my recent quantum program, research program that I named the Quantum Toolbox for Neurobiology Sensory Systems, COOLNESS, the acronym. So, in fact, introducing two additional challenges. One is about the quantum physics of complex biological systems that are at the verge of the classical to quantum crossover. And second, what about perception? And I will do this by discussing, first introducing two, I would say, complementary paradigms for this. One is about using the quantum microphysics modeling of biological systems. There is a lot going on, both under the experimental and theoretical perspectives that go under the name of quantum biology on the one side and on the way back biomimicry paradigms. And then instead a quantum coarse-grained modeling of biological and neuroscience systems that is within the so-called quantum-like paradigm. Both paradigms are not that old, say a decade or so. And within this, I will discuss a few examples. And in particular, I will step on a more recent work that we did with a colleague neuroscientist, Concetta Morrone, that is about perception, and a particular type of perception we are able of, that is that of counting without counting, is a so-called numerosity perception. And then I will try to discuss in the long run, medium and long run, how much we can use these quantum paradigms for building up a real quantum toolbox for perception problems. All right, so let's start from quantum biology and biomimicry. As to quantum biology, of course, biological systems are made of atoms, and so they are quantum, they follow the quantum laws. But when we speak about quantum biology, we mean if any quantum phenomenon, like, for example, coherence or entanglement or tunneling or other, have non-trivial roles in building the efficiency and effectiveness in the way a biosystem process works. And of course, this is intimately related to the classical, to quantum crossover, because biological systems are complex, macroscopic, enough macroscopic, noisy, room temperature, and so on and so forth. So where quantum physics might be not the case, I mean, as an approach. Then we have biomimicry. So if usually the conventional methodology is to exploit quantum technologies to simulate biological systems via, for example, quantum computers, that is conventional, in quotes, because it is a very young field as well. But there is another paradigm, that is biomimicry, that is about, is an emergent paradigm that is about exploiting nature to understand and improve quantum technologies, maybe at room temperature. So you see, there is really a wealth of different kind of realities, and of course, this is also connected to the classical, to quantum crossover. So just to give you a gallery of the most famous problems in biology that are nowadays tackled by experimental and theoretical means, there is, for example, this is the most well-known and also best established, the photosynthesis process, but also the way birds orient themselves into the magnetic field of the Earth, or a research program we are carrying out with my group in collaboration with the agronomy colleagues, the nitrogen fixation that is important in agronomy, and on the way of using quantum computers to make molecule design, molecules that can be useful for medicine or for biological reasons. Okay. But if we are to speak about quantum microphysics and so describe microscopic phenomena via the quantum laws, we need a conceptual map to orient ourselves. So I would like to share the minimum tool sets that we need for this challenging program. So first we have to identify which are the quantum information units. Qubits, if they are quantum states in superposition of two states, or they could be qubits, more than two states. Then we have to understand how the quantum information processing is performed, microscopically, I mean. And then how the quantum information is transported. And all this in a situation in which these biological systems are very out of equilibrium, that actually it is something very good for us, for the quantum effects, because when systems are out of equilibrium, in a way, temperature might be not necessarily an issue, because the energy scale is about the rate of change in that out of equilibrium process. The time scales are wildly different. We go from the picoseconds of coherent transfer, for example, in these Fenner-Matthew-Olson complexes in photosynthesis, or in microtubules to seconds or even hours in the coherent nuclear spin dynamics of, for example, the Posner molecules. That I will introduce in a moment. So, for example, in the brain, this would be something like from picoseconds to seconds, 12 orders of magnitude in time. So just I don't have time to dig into this, but just to give you an idea of the microscopic items that enter these three tool sets, just a list, then if you wish, I can answer questions, about the information, quantum information units. Much investigation is done with molecular dipoles that could be in the FMOs indeed, or the tryptophan in the microtubules, or the spin in Posner molecules introduced by Matthew Fisher, or for the quantum information processing, of course, light-matter interaction, coherent electron spin dynamics that brings to the radical pair mechanism, or coherent spin nucleus dynamics, as in the Posner, or sorry, even entanglement or tunneling. And about the quantum information transport, coherent charge or energy transfer, biophotons that are produced at the rate of something like 1 billion per second, for example, in our brain, and transported through distances of millimeters to centimeters. And then other special effects like long-range disorder, both that bring something interesting with respect to the long distance to which this information can be transported. All right, and I close this microscopic microphysics part with the only, to my knowledge, microscopic theory of consciousness. That is the one of Roger Penrose that has been touched upon in some of the talks at this conference, that has the inspiring role of bringing together many of the words that we have used during this conference. So, quantum physics and reality, because it's based on the objective reduction, and gravity and universe, because this objective reduction is due, in his idea, to the coherence induced by gravity, and third, because the mind and consciousness, because this objective reduction is the onset of consciousness, the being of consciousness, the being time. So let's swap from the quantum microphysics to instead the coarse-grained modeling. And I will be using the quantum-like paradigm that is about describing complex phenomena that do not need to be quantum. And in fact, we just exploit the mathematics and the statistical mechanics of quantum physics to describe physical or biological systems. So why this? Well, for many possible reasons. One is that we can exploit the linearity of the quantum processing, information processing in quantum mechanics, while all the complexity is taken into account by entanglement. Or we can also save computational resources by considering our biological functions as open information systems that interact with some environment, or again, exploit tunneling processes to optimize quantum problems. This is the famous quantum annealing that is improperly considered a way to quantum computing. For what, here I list just some most famous applications of this quantum-like paradigm that, for example, are the quantum versions of the IIT theory for consciousness, or entanglement-based quantum dissipative models of brain, information processing in biosystems, and the very newly born quantum cognition, field of quantum cognition, where this quantum statistical mechanics is used in social studies. Okay, so what we did within this quantum-like paradigm with Jorge Iago Malo, researcher in my group, and in this truly interdisciplinary work with Concetta Morrone and Marco Cicchini, and now we have the two students, Simona and Vittoria, who are bringing forward this idea, and the collaboration of Luca Celardo and Fausto Borgonovi more recently. So We have, first of all, tackled a problem that is very well studied in the Pisa Vision Lab, that is laboratory of Concetta in Pisa. That is a numerosity perception. As humans and also animals, we are able to estimate very well how many items are in a given space. And we perform this task very, very well with an uncertainty that is 15%, no matter whether the number of items is 5 or 200, actually even up to 500. So this means, in a way, that we are counting without counting. So in a perceptive manner, not in a cognitive manner. What Bohr and Ross call analogic sense of number. Now, it's not only number, because time is very illusory in our mind, and not just for philosophical reasons. Also for neuroscientists, it is. Indeed, this property of the numerosity perception is shared also with the time and the space perception. This is, again, what I did is the Weber's law that says, indeed, that this uncertainty in the perception of time and space intervals, as well as number, scales linearly with the number or the time interval or the space interval itself. That is very weird, because our neurons, they fire in a Poissonian manner. And so this is not at all something that is Poissonian. Now, for this reason, neuroscientists, they speak about integrated space-time number perception. So it is our mind works, our brain works as if there were many different clocks, each of them attached also to a position, so that we lively and dynamically remap what we see and make a mapping of our external worlds via this spatiotopic kind of remapping. All right, so what about if we use artificial neural networks to describe these properties? Well, they kind of fail. They poorly perform. And this is because it is found that only, say, 10% of the units, they process this information, while this is really a global property, expected to be a global property. We need very complicated artificial neural networks, and also very often we need to train them, while this is a universal kind of property. So we decided to try with quantum physics, quantum modeling. So we are not saying, again, that there are quantum effects in the brain. We are saying that we can use the machinery of quantum mechanics to model these complex properties. So we made a mapping. Neurons are spins that can be switched on or off, up and down. The activity propagates via transfer of excitations, via tunneling. Then we can have some interactions between neurons that provide the excitatory or inhibitory mechanism. And then we can have different kind of architectures, because the neurons can be talking to each other, nearest neighbor, all to all, or something in between. And then, of course, we will have some dissipation. That means that our brain goes to some resting state. So the mapping is simple. Actually, it brings to, I didn't show the Hamiltonian, but this is the XXZ Heisenberg Hamiltonian for ferromagnetism, only that it is played in a completely different context and completely out of equilibrium. So what happens, just to see, to see a simulation of what happens if we inject an excitation here in position 4, so we switch on a neuron, just one. If we have a nearest neighbor interaction, then there is a propagation with a light cone speed back and forth, and nothing very nice happens. But if we have an all the neurons are connected with all the others, then the excitation remains trapped, and so the system can count very precisely what's going on. And this was very surprising to us, but in fact, as Fausto and Luca suggested to us, there is a beautiful analytic explanation why this happens in this complicated system. So it's, I have no time to tell, but it's the content of Simone's thesis. So what if we inject more than one excitation, many excitations, then what happens something very interesting, that when each neuron is connected to all the others, so in this all-to-all connectivity, the neural network oscillates collectively in a way that has as many frequencies, precisely as many neurons have been excited at the beginning. And no matter how many neurons, where, how, and when. So now, if we use some, what neuroscientists do quite well, I was always very impressed, some decoding of the uncertainty with which the quantum network performs this operation of counting, then guess what? We recover the Weber's law. This is the simulation, and just to give you an idea, this is the experiment in the Pisa Vision Lab. So, a very simple, just one layer quantum network mapped from reality to some mathematics that is capable of describing this very complicated situation. Where we can go with this? Well, we have many questions to ask. One is, of course, that we can, it is not just tunneling and entanglement that make quantum physics, quantum many-body physics so interesting. There are many other effects. Actually, there are real paradigms that have been explored in the last decade precisely thanks to the progress in the new quantum technologies. And I'm going to present some, very rapidly, some of these quantum paradigms just to give you a flavor, because they are concepts that are very well resonating with other things that certainly happen in our brain. And so the question is whether we can keep using this quantum-like paradigm with this quantum network to equip our quantum toolbox with many of these other paradigms and make a real quantum toolbox for neurobiology sensory systems. So let us, and of course, maybe design a quantum artificial intelligence that can be coded into a real experiment. So made a physical, real piece of quantum technology that is capable of reproducing the perceptual properties and capacities of our brain. Okay. So, which are these paradigms? One will be very, very fast, is the open quantum system paradigm. Bert, in the first day, has extensively talked about it, and I just want to highlight that with the open quantum systems, the fact of having a coupling with the environment is not necessarily negative. It can be, it can be quite positive because it is possible to engineer the coupling with the external environment in order to make our system do what we wish. In particular, very interesting situations come in the so-called non-Markovian regime, where it is possible to incorporate memory-based couplings. Second paradigm is quantum chaos. We know that in the brain, different regimes of dynamics can happen depending on the degree of coordination and variability. So ordered dynamics with high coordination and low variability, disorder, low and high, and complex, high and high. That is, the complex is generally at the chaos order criticality. So this is very reminiscent of many things that we can do also with quantum chaos, with some additional counterintuitive outcomes that have been investigated in recent years. So one is that the quantum effects can be amplified in setting quantum chaos conditions. Second is that we can have chaos enhancement by the coherence under special driving, and we can have, vice versa, a coherence enhancement near quantum chaos order criticality. So this looks very promising. Time crystals. We know about brain studies in experimental studies, more recent experimental studies in brain structures reveal that these structures work as a scalable resonators with in frequency ranges that make order and orders of magnitude. And biological clocks, we know, have a proper running time. They are able to return to periodic oscillations after a disturbance by a mechanism that is called phase resetting. Now, there is a system, a concept in quantum physics that is the time crystal, and which resonates very much with this idea. Time crystals that were introduced by Wilczek in 2012, and then proved very recently in an experiment at the Google team, after a lot of interesting work by Els et al. And Kemani et al. So time crystals are out of equilibrium phases of matter that break time translational invariance. They are natural timekeepers due to the internal interactions, even though they are triggered from they need to be triggered from the outside, from an external disturbance. And this is not possible by construction with time-dependent observables at thermal equilibrium because the density matrix commutes with the Hamiltonian. So we, to make a quantum time crystal as a recipe, we need out of equilibrium conditions, external pumping to replenish the energy losses, and we have to avoid thermalization. In this manner, we can break ergodicity, which means that we have exponentially diverging time to reach a time-independent state. So can you see how many resonating things we find? And eventually, information storage and retrieval. Here I present you a bright and bold idea by Giyad Vali, cosmologist. We are in an interdisciplinary audience, so I think it's the right place to say this. He has been using the holographic conjecture to map brain functions via dual bulk boundary description, where the bulk works classically and the boundary in a quantum manner. He has built a dictionary that maps a black hole with a critical state of a highly excited low threshold neurons. If you look at the information, the estimate of the information that is stored in a black hole is the kind of size scaled or properly scaled than with the brain. Artificial quantum neural network are mapped in D-dimensional quantum field model with attractive synaptic connections between the spins, and in this way, he finds that the information is stored in a macroscopic quantum state that is the entanglement of the build-up from the superposition of m to the n-1 states, where n is the number of neurons, and m is the number of spin states. So not just a qubit, but maybe a qubit. And in this way, there is an energy separation and a decoherence time that scale in this manner with the number of spins. And so we can see that if G, the coupling G is small, we can have exponentially large quantum information that is stored in, with longer coherence times. So I'm done. And just one more slide that is about next question, part 2, because besides building this quantum toolbox, we can with equipping it with these paradigms. We can also think as our network of spins as actually a network of quantum clocks, because a spin is a two-level system, so it is also a quantum clock. And so we can imagine to play the same game, recovering the ideas of Diosy and Penrose, about having a network of quantum clocks. And this brings to the, can bring to the idea of quantum time and quantum reference frames that has been played in the last decades. And here there is Nicola with whom we are making, going to put forward a work on this. And then, closing the circle, we might then think to take this quantum toolbox that is a coarse-grained model and equip every single tool set that I said at the beginning, so the qubit, the microscopic qubit, the microscopic information processing, and the microscopic quantum transport, with the real physical processes that are experimentally investigated. So stay tuned, and I would like to thank all my group, colored and very smiling, and of course there is here Nicola, who's in the audience, collaborating to the Quantum Time Project, and here we have Venus, who's our artificial intelligence protagonist of the quantum video game we are building up to promote the cultural heritage of Tuscany. Strange things happen in Pisa. I would like to thank the Slow Science Research Group, Pavo, Bert, and Sabrina, and Women for Quantum. This is a new initiative of a group of something like 40 women quantum physicists, tenured, who have decided this time has come to change the way research environments are run, especially in quantum physics. And given the discussion we had also yesterday, I think that it is really the time to do this and to make all research environments worth and comfortable to be lived with, within, and also, as we wish to say, the evaluation be done in a way that is always open to new ideas and new research. Okay, thank you, everyone.
Okay, thank you very much. We have not too long for questions, but I've been asked to take a question from some of the people joining us online. So the question is, the problem with quantum biology is how far quantum properties can reach. The environment has to be transparent to the particles. See, for example, the two-slit experiment. On the quantumness of photosynthesis, one of the authors of the Nature paper that first pointed out the quantumness of photosynthesis told me that it was partly a mistake. Only the core of photosynthesis has a quantum efficiency of 99%, but the whole photosynthesis has an efficiency of about 20%, less than the usual collectors. Same with the brain. Consciousness spread out in decimeters cannot be quantum because the quantum properties in question are lost at millimeter distances.
Thank you. The questioner is absolutely correct. The progress in wonderful experimental and theoretical progress in this problem of photosynthesis has revealed that indeed there are quantum coherence effects, only that they last really picoseconds, or I mean they are too short to be considered the reason for the efficiency and effectiveness of the photosynthesis process. However, there are other candidates for quantum biology, kind of quantum biology problems where macroscopic quantum effects can take place. As we were discussing yesterday, if one does not invest time, energy, and funds in looking for things that, or in directions where no one otherwise looks, these things cannot be ever revealed. And there is no matter of principle to consider that the classical to quantum crossover cannot be, the border cannot be pushed up and up in the size of the systems. Just with non-living systems, I point out the experiment, more recent experiments by Marcus Arndt and Marcus Aspelmeier, where these huge molecules in the case of Marcus Arndt, of phthalocyanine, make interference, single molecule interference in a diffraction grating. And it's true that there the conditions are very cold and all the possible disorder and coupling with the environment are reduced. However, as I pointed out in one of the slides, the fact that the systems are out of equilibrium can in fact be the key to see whether the energy, the thermal energy is or not the reference with respect to instead the typical energies of these processes. So I think that it is worth to be investigated, even though I agree with the person who made the question that, of course, this is a very challenging and a problem that might bring to anything.
Okay, thanks very much. I'm afraid that's all we have time for now. I'm very glad to introduce our third and final speaker for this morning, Professor Ron Chrisley from the University of Sussex, and he'll be talking about non-superpositional neurocomputation and the foundations of mentality, a reassessment.
Thank you for being here, and thank you to Paavo and the powers that be for inviting me to speak. Some preliminary remarks. First of all, this is not an apology, but this is going to be a change from the previous two talks. You've had two talks of with sophistication in the knowledge of physics and rigor in philosophy. And this will be a step down in both of those, but it's not an apology. I still think there's something of value here and something I want to share with you. But just that's by way of expectation management. This is more speculative philosophically and more ignorant in terms of the physics. The other point I wanted to make was that and apologies to Tuomas. I want to kind of give you an idea of the counterfactuals involved here. So I'm going to be talking about this, but if I wanted to talk to you about the connections between my work and an understanding of quantum mechanics, I could have, in another possible world, I could have done so by showing why I think Penrose's argument against AI, if it does work against classical AI, then it should also work against quantum AI. And I don't think it does work, but I think he's wrong in thinking that his argument doesn't apply to a quantum computation. And or I could have, in another possible world, I could have, in a variation on some, or related to some work we heard about yesterday, I think there might be a way to apply quantum formalisms, in particular the superposition and Hilbert spaces and mathematics of entanglement, to capture the indeterminacies in perceptual experience. And so, why am I telling you that? If you find yourself, say, at the conference dinner sitting next to me, and you really found my actual talk, the talk in the actual world, unintelligible, uninteresting, whatever, then you could try saying, well, what do you have to say about these other two topics? Maybe they'll be more interesting to you. Anyway, happy to talk about those other two issues, as well as my main issue. So, before I get to the main event, I always prepare a different talk pretty much for every talk I give. And in preparing this talk, I thought the best way to, since it's a reassessment of some very old ideas, I thought to motivate looking at those old ideas, I would go over some personal history. So it's a bit self-indulgent, but that's possibly the downside. But the upside is that you get to see some photos of historical interest along the way that I've thrown in there. That you can look at those if you're not really interested in what I'm actually talking about. So. the ideas I'm talking about here go back to my first time that I came to Finland in the late 80s. And it was where my prior interest in machine learning, connectionism as it was called then, or neural networks, met head-on due to my friendship with Paavo. The questions that arose from the foundations of physics, in particular questions about the place of mind in physical reality and ways we might make progress on that kind of mind-world problem by realizing maybe there's a more sophisticated notion of physical reality than what philosophers had been working with up to that point. So that's the starting point here. And at the time, there was a notion of quantum computation that had been relatively recently introduced, but it was of a very particular sort. It's the kind that's still popular now. Quantum bits, qubits, entangled with each other. It definitely involves a notion of superposition, and it's very standard now. But when I was thinking about what I was learning about quantum mechanics and this more sophisticated view of physical reality from Paavo and David Bohm via Paavo, I was thinking, well, what would a quantum neural network look like? Because I was interested in neural networks, and that led me to find a different way that one might have quantum computation than is widely recognized now. And it's probably inferior in many ways, but I think it allows us to see some possibilities for understanding the role of mind in nature that might otherwise, or it helps me to see, and maybe it will help you to see, new ways that mind might have a place in the physical world. And so what I'll do is describe to you this basic non-standard quantum computation model, but then try to quickly get to the current status of, in particular, understandings of Bohm's notion of active information and how thinking about it as playing a role in computation might help us understand how minds can be part of physical reality. Now, why so much about mind? This isn't a quantum mind conference. Why all this? Well, physics and reality, mind is a part of reality, and so it's a special case. You could think of it as that, but also I think one really can't understand either the nature of physics or reality without addressing the role of mind, either in generating those or being a part of those. So, anyway. So I sometimes have referred to these quantum neural networks that I want to describe to you as Bohmian quantum artificial neural networks. So the artificial is important. That this is not meant to be a model of anything going on in the brain. I sometimes, as in the title for this talk, refer to them as non-superpositional, but I've been recently schooled on the confusion that term might engender, because, of course, there's still, as you will see, there still is a sense in which a wave is present, and you understand that wave's role by understanding it as being, interacting with itself, and really there's superpositions play a role, but it isn't the standard notion of superposition where you have entangled, different observables in different degrees of entanglement, and then a collapse of those observable that superpositional state into a classical determinate state. So it's non-superpositional in that sense. So perhaps better would be non-qubit based quantum computation, or non-entangled, or these are single quantum systems I'm looking at, not entangled bits like you often see with traditional quantum computation. Even what's now become traditional quantum neural networks or quantum neurocomputation, which didn't exist at the time I was doing this. So the general idea is that you can think of a quantum process as a computer, like any other physical process, like a soap bubble or any dynamic system. So far, that's uninteresting. But just to spell it out a little bit further, the boundary conditions of the quantum process are they can encode some inputs, And the outputs of that, the result of that quantum process can be taken to encode some outputs. You can decode the outputs from the resulting observations. And you can use algorithms from statistics or machine learning to optimize over some of those boundary conditions. Some of those variables can act as parameters that you modify according to a learning rule in order to make that physical system, in this case, a quantum system, realize any particular mapping of interest. Of course, you don't want to, it would be impossible for a function that's defined over, say, n. You can't give all the training pairs that would be required because that would be an infinite number of training pairs. So the typical approach in machine learning is to have a finite set, very, very small, relative to infinity set of training pairs, and hopefully your system, by getting that finite set right, will generalize to hopefully the rest of the function f or to a large portion of it. So here I've generalized Young's two-slit experiment to an n-slit, well, n times m slit experiment, you could say, where n slits are encoding the input that you're considering on this particular run, and the other m slits are encoding the parameters over which realize your machine learning model, your neural network model, that are optimized over during learning. And you'll get a complex interference pattern over aggregates of single quanta over time. And you could come up with some scheme. I've done a kind of trivial one here where you divide the plate into n region, or whatever, let's call it k regions, and you bin the you have a threshold for each of those regions to say whether it's 1 or 0, depending on whether the intensity of that part of the plate is above a threshold or not. That's the general idea of the BQANN model I was considering it back then. Now, you might think, well, wait, linear wave mechanics, so that's all going to be an entirely linear system, so that's not going to be very interesting because we know from computing theory, it was discovered very early on in machine learning back in the 60s that linear neural networks aren't very useful. There are functions, simple functions, like the exclusive OR function, which cannot be represented in a linear neural network. Even a multi-layer linear network couldn't compute that function, where you only have 2 inputs, say, and you should output a 1 only if exactly one of the inputs is 1. It's true or whatever. If both are off or both are on, then your output should be off, should be false, should be 0. That function cannot be represented by a purely linear system. You need a nonlinearity of some sort. But what's interesting is that even though you use wave mechanics, the wave equation to describe the behavior of this single quantum system, trivially, there is a BQANN that can, without any weights at all. So I showed you on the previous slide the generalized model where you have some slits representing inputs and some slits representing weights. But here we have no weights at all. We just have input slits. And here's a very simple way to compute XOR. If the image on the plate is constant, either non-zero or 0, then you should output a 1. And if it's non-constant, that is if it varies over the plate, like if there's if there's an interference pattern. The extent to which there's an interference pattern there means you should say no. You should say it's that the function yields 0. So it looks like there is some kind of nonlinearity going on here because of the interaction. Nonlinearity in the computational sense. I'm not saying that there's any nonlinearity in the wave equation, but because of the way that it's because of the presence or absence of the inputs and outputs themselves provide a nonlinearity in how the wave equation behaves. That allows this kind of computation. Oops, I pressed the wrong button. Let's see if we can get back. Oh, okay. So I will skip over this slide quickly. I've already mentioned that if you have these parameters, you can perform a kind of learning by just optimizing over those parameter slits and get the system to realize or approximate a function of that you're training it on. So you might say, well, wait, isn't this just optical neurocomputing? Again, I didn't know about optical neurocomputing. I'm not sure. I know optical computing was a thing when I was coming up with this stuff, but I don't think optical neurocomputing was. But I still don't know enough about optical neurocomputing to answer this question. I'll say probably now, maybe this is the same thing. Maybe someone who knows more about optical neurocomputing could tell me. I have no idea what that diagram is representing on the left. It's just an example of a diagram from a recent review article on optical neurocomputing. So that's your reaction to that slide. That picture is basically the same as my reaction to it. So just to let you know, I'm very ignorant about what's going on in optical neurocomputing. But my suspicion is that they are not computing with individual quanta. So I should say something about that. Yes, in everything I've described to you so far, I'm using, when I talk about like the intensity pattern, the interference pattern on the plate, you only get that building up after you send multiple multiple quanta through the system. So I haven't been talking about using single quanta to compute, but you could, of course, look at the plate after one quantum goes through or a small number go through and build up a Bayesian estimate of what the input is or what the situation is, what category the input is falling under, based on Bayes' rule, based on you can have a gradual you can have a way of decoding the outputs so that your confidence in your hypothesis will increase quantum by quantum. And I don't know if optical neurocomputing does have a way of proceeding with individual quanta, but please, somebody inform me about that. So there are implementation issues which I won't go into really. You know, how could you possibly efficiently implement this? So this is completely distinct from, it's the mirror image of Marilu's work, which is trying very hard to think about how you can find these quantum processes in natural systems and artificial systems. This talk is completely ignoring that. It's a purely theoretical model, and I'm using I'm using Young's interferometer purely for pedagogical reasons, not because I think that would be a good way to actually do this kind of computation in real life in order to do computational work. So I'll skip over that. So why look at these models? Why might they be interesting? Well, in general, you have the advantage of quantum. Remember, I'm operating from the Bohmian perspective, so the way I understand it, what is making the particle hit at this point on the plate as opposed to that point is not because it's interacting with another particle or following a wire or anything. You're getting the information about the state of the slits and in the light of the model, which is the presence of the other slits, solely by virtue of it being guided by this quantum potential. And so the advantage is there that you could, in theory, you could have very small scale integration, which means perhaps faster computation or at least faster clock speed, but definitely lower energy, definitely cooler. And these are the main constraints on large scale integration of computational elements at the moment, is just where do you put all the wires, how do you keep it cool, and how do you handle the energy consumption. That would be if you had an actual implementation, physical implementation of this. What about in simulation? Well, it might be, I don't know. It might be that there are no advantages over other computational models if you're just simulating this, if you're trying to explain the mind or something, or how, something psychologically. And in particular, since I've gone out of my way to try and implement classical standard machine learning models, if I've succeeded in doing that, then it seems like in principle there won't be any advantages because it's just implementing what we already know. But recall that XOR problem. That was genuinely surprising to me that I thought, well, this is a linear system, I'm not going to be able to compute XOR, and then thought about it a little bit more and saw that it could. So maybe there will be some ways in which our intuitions about what's possible in different kinds of neural systems, even simulated ones, will be modified using these systems. But my main interest, and how much time do I have left, roughly?
About 12 minutes.
Oh, great. In total, including questions, right. So I finally am getting to the main point of the talk, which is how can we use, how did I try to use these models to resolve some philosophical questions in the area of Bohmian physics and trying to understand the mind. And can there be further developments in that in the light of what's happened since then and now? So we've already seen active information here at this meeting, and I just want to recap that the notion of active information, I'm not a scholar about active information. I get all my knowledge of it from Basil Hiley and Paavo, and indirectly from David Bohm's works. But as far as I understand it, here's some things that people say about active information. The idea here is that the quantum potential literally informs rather than pushes and pulls mechanically the particle or corpuscle that it accompanies. So that means that you have here at the very fundamental level, a level way below where it's normally thought, say, mind could operate, you find sensitivity to pattern and form and shape, not just what we might call amplitude. So Bohm has a nice analogy that I can't go into that illustrates that. You have a non-locality here, so kind of an informing of the particle about the environment, the experimental setup that is non-local. It's unmediated. There's the environment and then the particle moving this way or that, depending upon the configuration of the environment, without any intermediate exchange of particles or wires or anything. There's a direct control there. And it's information for the particle. This would take too long for me to explain, but the rough idea is that the quantum potential might even be different for multiple particles in the same vicinity, and a particle is informed by its quantum potential. It might have its own, in a way, private quantum potential. But there were also claims at the time, this is going back to, say, the early 90s, that, and I think still to this day, proponents of active information might say that, and it's not just classical information in the sense it's actually truly semantic. It's actually, it has intentionality. It's about the quantum potential. It has the information it's carrying is really about the environmental setup and is giving the information to the particle that is truly semantic in a way that Shannon-Weaver information is not. So at the time, I was obsessed with, or focused on content, which is a philosophical term of art that roughly means meaning or significance usually in linguistic contexts, but also generalized to psychology in some cases. So it's more than information in that representation, which is a paradigmatic content carrier, can be true or false. So information in Shannon-Weaver's sense, if something carries that information, it just carries it, and that's the end of it. But when you move to content, or we could call it intentionality or aboutness or representation, you can have a representation that says, hey, there's a dog there, even though that representation was caused by a cat. So the representation can misrepresent. And some philosophers thought that this was actually the sign of genuine intentionality, that there was a possibility that something could misrepresent. If it couldn't misrepresent, it was said, then it isn't mind-like. It isn't the kind of stuff that we're dealing with when minds are engaging with their world. We can be wrong information carriers cannot be wrong about the information they carry. So the idea here was maybe I could use these Bohmian quantum neural networks to explain how active information could be genuinely semantic in the sense of being able to misrepresent, not just being like classical information. Well, that didn't work out. The way I was thinking is that some people at the time said, well, maybe you could understand certain systems, like if they're learning systems, then you could associate what you could determine what the representation is supposed to be about with what it was correlated with causally during its learning phase, and then when it's outside of the learning phase, it might be caused by something else other than what it was correlated with during the learning phase, and that would be a misrepresentation. And I was thinking, okay, these BQANNs learn, so maybe I could just hitch onto that solution and somehow come up with active information that was genuinely intentional and capable of misrepresenting. But I don't think that's a really good solution now. I really haven't pursued it anymore. And also, we want to explain how human brains have intentionality. So unless you think that something like Bohmian quantum artificial neural networks are also natural neural networks, then maybe this won't be a problem, won't be able to solve the problem for the case of humans. It would just be for the case of artificial intelligence, ironically. But anyway, I'm just going to draw a line under that approach because times changed and there was a shift from trying to naturalize intentionality to trying to naturalize consciousness. So rather than just looking at whether or not how representation could be in the world, how could phenomenal properties be in the physical world? And there were people who went so far as to say, well, maybe we have to have a dualistic model of the world. And then you had critics of that dualistic view, like Dan Dennett, who's there holding my son Christian. You have Dan Dennett, who is greatly missed, saying that there isn't any way to make sense of the phenomenal character that these qualia freaks, like Dave Chalmers say, the new qualia freaks were describing. There's no way for those things that are private, things that seem to be unmediated. We have knowledge that's unmediated of them. Things that seem to have their character intrinsically. Things that seem to be inexpressible in principle. Those things, if they really have those properties, then they can't be part of the physical world, is what Dan Dennett was arguing. And Aaron Sloman and I have instead taken a different approach and said, well, maybe the qualia don't actually have maybe these conscious states, which are called qualia, maybe they don't have those four properties that Dan Dennett enumerated, but they certainly seem like they do. So maybe if we could just identify qualia with something that explains why they seem to have those four properties, then we would have naturalized qualia. And I still think that there's a lot of promise in this view. But today, what I'd like to do is go to and finish with this idea that instead we could maybe have a more robust realism about qualia than that kind of revisionist realism about qualia by employing the role of active information. So if our knowledge of our own qualia is somehow, by virtue of us being informed by active information, then we could explain the reason why qualia, that our experiences seem, our knowledge of our experiences seems to be immediate. And when I say immediate, I mean unmediated. Why qualia seem to have their character intrinsically and why they seem to be private. Because actually they would really be, unlike what Dan Dennett said, actually the physical world is more subtle than he thought. You actually can have physical states where there is an immediacy relation between that state and what informs it, where things do have their character intrinsically, where things are genuinely, fundamentally private. So maybe Dennett was wrong about what's physically possible, and that's how mind can be in the physical world. For example, I can't go through that story now, I haven't done it, but for just to take immediacy, that is unmediatedness, that our knowledge of our qualia is not mediated. It's not by virtue of us contingently interacting with something else that we know what the character of our conscious states are. Similarly, it's not by virtue of the particle interacting with something else that it knows about the environmental configuration. Rather, it has that information, that informedness, directly via the quantum potential. So there's an example. So I couldn't find misrepresentation before. Turns out that's a feature, not a bug. It's extreme inability to misrepresent, but there is a representational relation here anyway, and that is the hallmark of knowledge of qualia, perhaps. And finally, of particular note is that this particle is being informed directly, not about facts on the particle level, but about classical structures, such as the presence of a slit, a very high-level entity that you have to build up to with many structures to get from that low level of particles and fields and quantum potentials to an everyday object like whether something is a slit for the purposes of our experiment. And that's amazing because you have something on the classical, everyday level directly, the presence or absence of that very complex phenomenon, high-level phenomenon, directly informing the behavior of the particle, which is, I think, can do a lot of philosophical work. So I don't have time to give my proposal for how we can use this in artificial intelligence. I can talk to you about that later. I just want to say thank you.
Thank you very much, Ron. Unfortunately, we've used all the time in this session, but I'm certain that Ron will be very happy to take questions during the break. We have now 15 minutes for a coffee break, and we will return on the hour. Thanks a lot, everyone.
All right, so welcome to this session, and we have now a keynote from Tim Palmer from Oxford, and Tim will talk to us about the singular role of infinity in quantum physics towards a rational theory of quantum mechanics. So Tim, the floor is yours. And all right, so you need this.
Okay, thank you very much. And again, like all the other speakers, thanks to Paavo for the invitation and the opportunity to speak. Yeah, so in a sense, as I say, the title is motivated by thinking about the role of infinity in physics, which we may have all different views about. And I'm going to use that as a stepping stone for what I am calling rational quantum mechanics, which I'll try to explain. And the word rational deliberately has a kind of double meaning. Rational in the sense of being comprehensible, I think, but also rational in the sense of being based on rational numbers. Well, what's the role of infinity, or let's say, to be a bit more specific, the role of 1 over infinity in physics? Is it just a placeholder for a very small number, or does it play some essential role? And I would argue that in classical physics, it doesn't really play an essential role. And just to illustrate that, imagine you give me some complicated, nonlinear differential equation, maybe for a soliton or something like that. I might choose to solve it on a computer. And to solve it on a computer, I'd have to discretize the equation in space and time. And unless it's a horrible equation, and there are examples of horrible equations, but let's say for generic classical equations, there will be theorems in numerical analysis which will say, if you want the solution to a certain accuracy, specified accuracy, then your discretization will have to, both in space and time, will have to be smaller than, so if your accuracy is delta, your discretization will have to be smaller than epsilon. And so in some sense, as the discretization gets smaller and smaller and smaller, you tend in a very smooth way towards the continuum solution. So that's the theorem. that you can prove about most sort of reasonable classical equations. So I would argue in that sense the infinitesimal is not really playing any essential role here. It's just, you know, something that's small and can be made as small as you like. But in quantum mechanics, things are different, because a very inherent, you know, almost the first postulate when you read a textbook on quantum mechanics is that your state space is a vector space over the field of complex numbers. And by definition, the field of complex numbers is a continuum space. So if you try to get rid of the continuum, by discretizing, you've already violated that first axiom of quantum mechanics. So I would argue, in a sense, that quantum mechanics, it plays an essential role, whereas in classical mechanics it doesn't. Now, what I want to propose, despite having just said that, I want to propose a model, let's call it a model, I think it's pretentious to call it a theory at this stage, but a model where we do actually, if you like, try to get rid of the infinitesimal and treat the state space of quantum physics in a discrete framework. Now, necessarily, by virtue of what I've just said, this theory will have to be very different from quantum mechanics, and I want to describe how that might be. But just before going through that, you might say, well, why bother in the first place? I think there are two reasons. One is that a holy grail, we've had talks about quantum gravity, and obviously a holy grail of quantum gravity is the emergence, the natural emergence of some sort of discretized structure for space-time on the Planck scale. Almost everybody who works in quantum gravity, you know, aspires to that emerging. I personally believe that the reason we have failed to realize that goal is because our quantum theories, and in particular quantum field theories, make essential use of the continuum. So either Hilbert space or Fock space for quantum field theories. So that's just a belief of mine. I'm not going to say much about this, but I have got one slide later on. But the other problem is the measurement problem. And my own view is that the measurement problem, to be really said we were able to solve it, we need to be able to show that the quantum, I mean, something that Einstein always believed should be the case, that the quantum wave function really just represents some statistical ensemble of deterministic solutions, you know, and that has certain statistical properties. But again, you know, we've tried this for the best part of 100 years and haven't succeeded. So my view is that this is maybe the reason it's not possible, again, is because of this inherent dependence of quantum theory on the continuum. I'm just going to quote from some eminent names who have also kind of cast doubt on the role of infinity in physics. David Hilbert. The infinite is nowhere to be found in reality, no matter what experiences, knowledge, and experiences are appealed to. I think I've missed a word out there, but anyway, it doesn't matter. John Wheeler, the familiar quantum probability functions of standard quantum theory provide mere continuum idealizations, and by reason of this circumstance, conceal the information theoretic source from which they derive. And this is a paper by Roger Penrose, his famous spin network paper, where he says the basic theme of these suggestions have been to try to get rid of the continuum and build up physical theory from discreteness. And something I'll come back to, these probabilities that he gets from the spin network model he proposes will turn out always to be rational numbers. If you want to, well, you can just email me. I can send you papers, but there's something on the archive. This is a more recent paper which tries to use the ideas to talk about Bell's theorem, which I'll mention briefly at the end. And one of my projects this summer is to probably try and write this up properly for a kind of mainstream physics journal. Okay, so I want to talk about how one might go about discretizing Hilbert space, because what I want to talk about really does depend on a very specific discretization. This would not work what I'm about to propose does not work generically. It works in what I think is a natural way, but it's a very specific way. And I want to start by forgetting about quantum mechanics for a minute and just think about Hilbert spaces over the reals, and maybe just focus attention on a deck of cards. And the question is, what's the, let's say, what's the state of the top card after it's been well shuffled? Well, you could in principle use unit Hilbert vectors to represent the state of that card. If you have, let's say, a basis of ace of clubs and not ace of clubs in orthogonal directions, then your top card will be a unit vector which will have an amplitude of the square root of 1 over 52 times the ace of clubs and the square root of 51 over 52 times not the ace of clubs. Now, note, obviously, that if you square the amplitudes and sum them, you get 1, and that's just consistent with Pythagoras' theorem. There's nothing more than that. So that the squares of these amplitudes equals 1 is just a statement that we're looking at a unit vector in this two-dimensional Euclidean space, which is where Pythagoras' theorem is held, point made by Chris Isham in his book. And it's also consistent with the notion that there is a probability that this top card could be the ace of clubs, and a probability that it's not the ace of clubs, which also sums to 1. So if we interpret the squared amplitudes as probabilities, we sort of get Born's rule automatically. And finally, that the squared amplitudes are rational numbers, that the squared, not the amplitudes themselves, but the squares of the amplitudes are rational numbers, is just consistent with the idea that we can generate these probabilities from a finite deck of cards. You might have 52 decks of cards that have all been shuffled randomly. So I'm going to argue, this is the first point really, that a natural way to discrete real Hilbert vectors is by requiring that squared amplitudes are rational. So if this is, I'm just going to parameterize that amplitude with a trigonometric function, and then insist that the square of that thing, cosine theta over 2, so square of that is rational, so cosine of theta is rational. But of course, quantum mechanics, the whole point of quantum mechanics is that it's a theory on the complexes, not just the reals. And the question then is, what's a natural way to discretize complex Hilbert space? So going into the complex numbers. So the next 2 or 3 slides are the kind of mathematical meat of what I want to propose here, because the way quantum mechanics was formulated, and I suppose it's von Neumann that's really kind of introduced all the notion of Hilbert spaces and everything. Very mathematical approach where one says, well, we know there is a field of complex numbers, let's use that. The complex numbers were, discovered, invented, whatever the right word is, back in the 16th century, or whatever it was, to solve polynomial equations. It's not obvious that they're relevant to quantum mechanics. So what I want to do in the next 2 or 3 slides is sort of try to forget that we ever knew anything about the field of complex numbers, and try to, if you like, derive complex numbers, or the complex numbers that we'll need in this approach, in a much more constructive way. I'm not just assuming there exists a field of complex numbers, generated by something called the square root of -1. I'm going to try to construct them in a constructive way. And I'm going to do this by thinking of these complex numbers not as numbers, if you like, but as operators on bit strings. And I'm going to typically use as bits the numbers 1 and -1, but it's actually quite important in everything that follows that these are not really to be thought of as numbers. They're just symbolic labels. So they could be up and down, they could be true and false, it could be alive and dead, it could be wet and dry. The only point is that there is a thing called a negation operator, which would take up to down or down to up, true to false or false to true, and so on and so on. So nowhere, although I'll use ones and minus ones, you're not really shouldn't really think of them as numbers, but more as symbolic labels. Okay, so I'm going to build up this very slowly by imagining my bit strings are going to increase in powers of 2, and I'm going to start with the simplest example where this, I only have one bit in my bit string, so that's either a 1 or a minus 1. So pretty much the only thing I can do with that is just to operate on it with the negation operator. So I'll just define minus s as the bit string with minus of a1. If s is a1, the bit string with a1, then minus s is the bit string with minus a1. Well, that's fairly uninteresting. But it gets more interesting if you have 2 bits in your bit string. Now, I should define the negation of the bit string to be the negation operator applied to all of the members of the bit string, so minus a1, minus a2. And now I can do something more interesting. I can permute these 2 elements around, so go a2, a1, and then I'll negate the second one. So this is a non-trivial operation on this bit string. Just reverse the 2 elements and negate the second one. If I do that twice, you see, I take the second one and move it to the front, so that gives me minus a1, and so I take the second one and move it to the front, and I take the first one and move it to the back and negate it. So you see, doing that twice has given me minus s. So in a very kind of simple, simplistic, constructive way, I can represent the square root of minus 1, not as a number, but as an operator on a bit string.
Tim, do you have any questions?
Well, unless it's really urgent.
Just trying to understand what minus in front of just a symbol.
I just have 2. Sorry, I'm not. This is not. There's no addition or subtraction. Sorry, I probably should have put commas. Okay, yeah, thank you. That's useful. I should have probably put commas here, but I haven't. So where you see a minus, it's just this negation. It's a sort of like a multiplicative negation, so it would take up to... It's better to think of these as up and down or true and false or something, and then minus. If A1 was true, then minus A1 would be false. That's it, yeah. Okay, now I can continue this process if I have longer bit strings. So if I have now 2 to the 2 elements, 4, again, I'll define the negation. Again, remember, there's no implied subtraction here. These are just all the negations of a1, a2, a3, a4. And I define I to the half as just an operator as, now I'm going to pull back. I'm going to take these 2, the last 2, put them to the front, and then take the second one, and then take the first one and put it to the back. And if you apply that operator twice, you get this, what I previously called I, applied to each pair of elements. And if you apply it again, you get the negation of S. And I can keep doing this as much as I want. If I've got 8 elements, I define the negation of the bit string as the negation of all the individual bits. And then I can define an operator I to the power quarter, defined like this. And if I apply I to the quarter twice, I get this on each quadruple of bits. If I apply I 4 times, I get this on each pair of bits. And if I apply it 8 times, I just get the negation of S. Now, this is probably not terribly clear. It may or may not be clearer if I was to write this permutation operator, for example, for I to the S in more in a matrix form and operating on a kind of transpose of a column vector. This would be the matrix operator. What I'm trying to argue here is that in this very constructive way, the natural way of discretizing the, if you like, unit complex numbers, or if you like, e to the 2 pi I. So if I have a bit string of length 2 to the capital N, a natural way of discretizing that is these operators, which can be represented as on the unit circle at, if you like, rational fractions of 2 pi. So they go around in equal angles, sort of. And this is actually just basically telling us that the complex exponentials in this picture describe bit string permutation operators and are essentially a representation of the finite group of complex roots of unity. So I want to put this together to form what I call these 2 parts, to form what I call the discretized Riemann sphere. So normally we think of the Riemann sphere as a continuum, but here I'm thinking of it in this discretized form, and going round, if you like, a line of, and each point now represents a bit string operator, going round a line of constant latitude, if you like, then the discretized points are at these uniform angles, sort of regular angles. So this will be 90 degrees, this will be 45, 22 and a half, and so on. So constant rational fractions of 2 pi. On the other hand, coming down along a constant line of longitude, the latitude or colatitude theta is discretized by this condition that its cosine is a rational number. Now, if we take a generic point on the Riemann sphere, this would be the generic, when you'd have this is normally done by polar stereographic projection of the Argand diagram, and the amplitude of a complex number gets mapped to this point here, where the amplitude gets mapped to the cotangent of theta over 2. So if cosine theta is rational, then cosine squared theta over 2 is rational, and so sine squared theta over 2 is rational, and so cotangent of theta over 2 is rational. So this is a point with a rational longitude and a rational cosine of latitude. So that denotes a sort of generic point on my discretized Riemann sphere. Now, what I want to show is that pretty much all of the sort of difficult problems in quantum mechanics in this framework boil down to a very simple number theoretic property of trigonometric functions. So I'm not going to use any complicated abstract operator algebra stuff. I'm just going to use what I call Niven's theorem. And Niven's theorem just simply says, if phi is a rational angle, so let's say in degrees, or a rational fraction of 2 pi, then the cosine phi is almost always irrational. There are exceptions when phi is 0 or 90 or 180 or indeed 60 or 120. But if you just think out of the blue a value of phi that's a rational angle, 33.1692 degrees, or 74.648 degrees, Niven's theorem is telling you that the cosine of that angle will be irrational. All right, so what I want to do then in this talk is take 3 of the kind of key points about quantum mechanics: the uncertainty principle, non-commutativity of observables, and wave-particle duality, and try to account for these without invoking the notion of superposition, but using this notion of Hilbert vectors over this discrete space, what I call C sub D, this discrete Riemann sphere. And as I say, I'm not going to use operator algebra stuff. I'm just going to use Niven's theorem. If I have time, I'd like to show that a kind of a consequence of all this is that, that there is a deterministic theory whose probabilistic structure is based on these Hilbert vectors over C sub D, which is not non-local, the violation of Bell's inequality notwithstanding. Okay, so I need to get from the Bloch sphere, I need to get from the Riemann sphere to the Bloch sphere in order to start talking about the state space of quantum systems. So bear with me as I go through this figure. So if you remember my discretized Riemann sphere, the points were these constructive operators. My block sphere now, the points are going to be these bit strings. Now, for simplicity, I'm just going to keep 8 bit strings. I mean, in practice, this will be a very long bit string, but with a finite 2 to the power capital N number of elements. But just for simplicity, we'll keep it as just 8. So I'm going to start with my Hilbert vector 1 as the sequence where they're all 1s. And now I need to kind of generate some of these other points from this. Now, I need to actually go beyond what I've so far described in terms of complex numbers to quaternions and implicitly then Pauli spin matrices to do this. So here's a quaternion, but you're to think of it now as, in this case, an 8 by 8. It's an operator on, an, if you like, a vector with 8 or a bit string. Think of this as a transposed column vector with 8 elements. So this one is an identity matrix, a 4 by 4 identity matrix, and this is a 4 by 4 negative identity matrix. And this will take me to, this operator acting on this will map me to this bit string, which I'm going to define as this Hilbert vector 1 plus minus 1. So this Hilbert vector represents a bit string with 4 1s and 4 minus 1s. This will be a second quaternion. Again, each of these is a 4 by 4 matrix, but these are now these are again my operators I and minus I. And this will take me to the Hilbert vector 1 plus I times minus 1. And if you just do the kind of trivial calculation, this turns out to be 1 minus 1, 1 minus 1, minus 1, 1, minus 1, 1. And the third quaternion, by the way, if you square each of these, you'll get a minus 1. And if you, say, multiply Q1 by Q2, you get Q3. This is the third one. And you can equally get this 1 plus I times minus 1 by operating on this with the third quaternion. And you can generate the south pole. And you can define distances on this sphere by what's called the Hamming metric, which is the number of bits between 2 bit strings that disagree. So, for example, between this one, this is my reference bit string, and say this one, there are 4 disagreements. So the Hamming distance is 4. The Hamming distance for this one is also 4. With this one, on the antipodal point, it's 8, because they disagree in all of their members. And then this one, again, is 4. And this is, I know it's getting a little bit tedious, so I'm not going to dwell upon this, but you can generate, points at I to the half and so on with other triples of quaternions, and generate things like I1 plus I to the half times minus 1. Anyway, once you've done all this, you end up with a, let's call this a generic point, being represented by a bit string whose average value is equal to cosine of theta, and whose standard deviation is equal to the modulus of the sine of theta. And the probability, if you like, of randomly drawing a 1 is, sorry, that should have just said a 1. Probability of a 1 is cosine squared theta over 2, exactly as in quantum mechanics. So if theta was 0, you see the average value is 1, the standard deviation is 0, and the probability of drawing a 1 is 1. But on the equator, theta is pi over 2. The average value is 0. The standard deviation is the maximum of 1, and the probability is a half. So this is quite an important point, that nowhere will I'm invoking Born's rule. This is automatic in the formalism. All right, so I want to run through these 3 concepts in quantum mechanics. So the first is the uncertainty principle. And there are 2 parts to the uncertainty principle. one is, if you like, a statistical relationship between measurements in different directions, and the other is that it also encompasses the notion of complementarity. So I want to show how both of those come in. The statistical relationship, say, between spin-half particles is really just a statement of spherical geometry. So I'm not going to dwell upon this, but this line, this inequality between this angle theta double prime and phi prime is just a matter of spherical geometry. I'm taking its sine. I'm applying the cosine rule to a triangle which has one vertex up here at the North Pole, one vertex here at the sort of East Pole, or West Pole rather, and the point and some generic point here. And I get, so this is just a statement of spherical geometry, and then I use this point that the sine of theta is a standard deviation. Well, theta prime is relative to this west pole, so that maps to this, what I call delta S of x. This would be the standard deviation of statistics, say, of a quantum spin half particle measured in the x direction. Sine theta double prime, this is theta double prime, is the standard deviation of quantum particles measured in the y direction. And the average of cosine theta, remember cosine theta is the mean value of the bit string, so that's the mean value of the spin half particles measured in the z direction. So I get the statistical uncertainty relation. What about complementarity? And here I'm afraid my computer has or somebody's computer hasn't translated the symbols right, but basically this says, suppose P has, suppose the co-latitude of this point P, which is theta, has a rational cosine. So in my language, then, this point P would lie on this discretized block sphere with Pz at the North Pole. Theta prime is the co-latitude if you rotated the North Pole around and rotated with it the discretization to the x direction. Then Niven's theorem kicks in quite quickly to tell you that if this is a rational angle, if this has a rational cosine and this phi is a rational angle, then this theta prime cannot have a rational cosine. And in the language of complementarity, it's saying that you can't simultaneously define bit strings for this point P relative to this direction and simultaneously in this direction. Or another way of putting it is that if this point P lies on the discretized block sphere with respect to the Z North Pole, it won't lie on the discretized block sphere with respect to an X North Pole. This point won't be on the discretized block sphere with respect to the X North Pole, or indeed the Y North Pole. Okay.
So where is your n going? The number
N at this stage can be arbitrarily large, as long as it's finite.
But your n is your discretization.
Capital N is my discretization. So all these results hold for any n.
But it's independent of n?
It's independent of n. All these results are independent of n. So n can be as fine as you like. You know, n can be a trillion. A Googleplex.
Uncertainties, they don't depend on n?
No, they don't depend on n. So I want to talk about about non-commutativity now. And let's just think about a very simple quantum experiment where you prepare a particle, spin-half particle, with a Stern-Gerlach apparatus in some preparation direction, and then pass it through a second Stern-Gerlach apparatus, which we'll call the part of the measuring system, two detectors here and here. Now, this actually raises an important point, which is that, of course, when experimenters set up experiments, they don't, I mean, I've talked about rational angles and things. I mean, when experimenters set up experiments, they don't, they don't have control even to set up, they can't set up an apparatus to be, one specific rational number or another. They have some nominal, there is some nominal accuracy within which they can set up an experiment. So here, I'm on the block sphere, the preparation direction and the measurement direction. I mean, as far as the experimenter is concerned, just think of these directions as sort of some small disks on the sphere, and all they know is that if you like, for any given particle, let's say there will be an actual direction, an exact direction, but they don't know it. All they know is that it lies somewhere within their disks. So I want to make a distinction between nominal and exact settings. And in fact, in what follows, it might be useful to think of insofar as one can think of this as a hidden variable theory, the hidden variables are the sort of correspond to these exact settings. And they're to be distinguished from the experimentally controllable nominal settings. All right, so in this situation, this is actually not terribly interesting because all that one can say is, well, there is an exact setting. P here, you can think of P as the north pole of my discretized disk. The exact setting will be a point. Sorry, P is the north pole, of the discretized block sphere, and M is a point on the discretized block sphere. It lies somewhere within the epsilon disk. The experimenters can't control where M is in the epsilon disk, but the laws of physics, or at least the laws of these rational quantum mechanics, will be such that this exact angle has a rational cosine. The bit strings basically return the quantum mechanical probabilities of measurement outcome, consistent with what I said a little bit earlier here. Okay. Now, this itself is not terribly interesting, but where it becomes more interesting is if you have three of these things, and this is often used in sort of elementary textbooks on quantum mechanics. So you have a particle, goes through SG1, prepares a direction, then it goes through SG2, and then through SG3. And the question is, suppose we counterfactually, keeping the particle fixed, we counterfactually swap the two Stern-Gerlach apparatuses. What would be the outcome? Now, so this is where it becomes non-trivial. In this rational model, as I mentioned, the relative angle between SG1 and SG2 has a rational cosine. The relative angle between SG2 and SG3 has a rational cosine. That's what happened in reality. So by construction, that's what the theory demands. And just bear in mind, I want to think of the hidden variables as these exact settings. So in the counterfactual experiment where I say, for the same particle, I'm going to swap SG2 and SG3, what that is tantamount to saying is, can I find this great circle between SG1 and SG3 such that its exact so the cosine of the angular distance between SG1 and SG3 is a rational number. Is that possible? Well, if this side has a rational cosine and this side has a rational cosine, then it's a fairly simple corollary of Niven's theorem that this side can't have a rational cosine. I sometimes call this the impossible triangle corollary to Niven's theorem. But this gives you, in a very simple way, the notion that you can't commute these operators without violating the rationality constraints. So this is where it comes in a non-trivial way. I'm going to quickly slip through. I suspect I'm running out of time already, but wave-particle duality, I kind of see this really as a consequence of the fact that these two discretizations along a line of latitude and along a line of longitude are kind of incommensurate in the sense that if you were to rotate the sphere by 90 degrees, so tip the North Pole over to the West Pole here, so to speak. No, sorry, I didn't mean that. Anyway, what I mean is if I made, I can't even think what to do. If I made this a line of constant longitude, so I rotated it so this equator now comes down here, these points would not lie, except at the 0 and 90. They would not lie on top of each other. They would be incommensurate. So I like to think of this as this direction as the discretization direction, where you see wave-like properties. So this would be constructive interference. This would be kind of in between. This would be destructive interference. Whereas this is more the kind of particle-like direction where there is no interference property. And this comes about very, very nicely in the Mach-Zehnder experiment. So imagine just a Mach-Zehnder apparatus where you have, well, half-silvered mirrors here and fully silvered mirrors here. And this measurement is sort of measuring the momentum of a particle in some sense. But now I'm going to remove the second half-silvered mirror. So basically, the detectors are just detecting which way the particle went. So it's like a position measurement. Now, we know in quantum mechanics, the interference measurement is given by this Hilbert vector. And removing the half-silvered mirror is a bit like rotating the sphere, because basically it's like a Hadamard-type transformation, which takes the differences in the phase angles and moves them in, which are in trigonometric functions, and moves them into this complex exponential. And now we see, and again, the computer hasn't translated the rational symbol, but basically you can either choose cosine phi over 2 to be rational, or, sorry, delta phi, cosine delta phi to be rational, or delta phi to be rational. But you can't have the two together. So you can measure that, but if you measure that and keep this fixed, then this becomes undefined in this rational theory. Or if you measure this, keep this defined, this is now a rational angle, then the cosine by Niven's theorem becomes irrational. So you can't have both. So you can have wave-like properties or particle-like properties, but not both. And as I say, this is coming out of just elementary number theoretic properties of trigonometric functions. Now, you can frame this in terms of counterfactuals. You can say, well, in reality, let's say I did a momentum equation, a momentum type of experiment. What would have happened had I measured that same particle, had I removed the second half-silvered mirror? So that's very much a counterfactual experiment. It's not one you can realize on that particle. You can realize it on the next particle, but you can't realize it on the particle that you did this measurement on. And again, think of this, the hidden variables as the exact, as being represented by the exact, in this case, phase angle differences. Now, this becomes relevant when we come to Bell's theorem, which is sort of the last point. Got 10, right, I'm going to try and finish in the next 4 minutes.
You have 5 minutes for the 15.
Yeah, okay.
So you have until 5 past.
Okay, all right. I want to say very briefly, I mean, in this model, entanglement is not conceptually difficult because it's really just sets of correlated bit strings, essentially. So M entangled qubits are described by M correlated bit strings going on finitely. So what I want to try to persuade might be a bit optimistic, but at least, I say persuade you of this, but at least I'm going to run my argument past you and see what you make of it. Because my claim is that this is not a non-local theory. It's important when we talk about non-locality to define what we mean. Pretty much, this was done in EPR. I mean, Bell uses pretty much the same definition, but it's already there in EPR. And non-locality means that experimental outcomes here depend on experimental setups there. So in a Bell experiment, if Bob were to have changed his setup, Alice's outcome would have been different. And EPR just sort of like dismiss that as a preposterous situation. That would be very unphysical if that happened, and I'm inclined to agree with that. And this does not happen in this, what I call rational quantum mechanics, for the following reason, and it's really nothing more than what I spoke about for the Mach-Sender interferometer. And I'm, by the way, a great believer in Feynman's statement that the only mystery in quantum mechanics is in the interference. I don't think we're actually seeing anything particularly new in the Bell experiment from a sort of interpretational point of view. So what, if you do the analysis and again, think about one of these counterfactual experiments where Bob counterfactually changes his setup in a Bell experiment, keeping the particles being measured fixed. And again, that means keeping the particles' hidden variables being fixed, and that means keeping these exact measurement settings fixed, these exact relative orientations between the measuring apparatuses. Then it's not that Alice's experimental outcome changes or is different. It just simply becomes undefined. That world necessarily violates these rationality constraints. So you can put it like this, that if there is a probability density on the hidden variables such that given measuring apparatuses X and Y, that density is non-zero. You could say it's 1 if you like in a sort of deterministic sense. Then that implies that same density on lambda given the counterfactual world where Bob changed his setup on the same particles is identically 0. So that is not the same equal to that. Now that's often referred to as the superdeterministic loophole, which is not a word I'm very fond of, I have to say. But Bell, I don't know, it seems to be used anyway in the literature. Sometimes people use classical examples to kind of show that superdeterminism is conspiratorial. The only thing I would say is if you kind of coarse grain lambda in any way that would be kind of relevant to a classical system, then all this argument breaks down. These rationality constraints just get washed out. So this doesn't have any implications about, drug trial conspiracies or anything like that. It's just something working at the quantum world, in my view. Okay, so I'm coming to the end. I think the important point here is that quantum mechanics is not a smooth limit of this theory at n equals infinity. That's the length of the bit string. It's a singular limit. And this singular limits are something that the physicist Michael Berry has written extensively about. There are many examples you can think of. Flow of an inviscid aerofoil. Aeroplanes would not fly in an inviscid fluid, but they could fly in a viscous fluid, even if the viscosity is, very, very, very small. The ultraviolet catastrophe in quantum mechanics only requires a non-zero value of Planck's constant. When it's 0, then you get the ultraviolet catastrophe. Berry makes the point that old theories of physics are typically the singular limits of new theories as some parameter of the theory is set to 0 or infinity. So I would say that this sort of fits in with that paradigm of Berry's. I did want to say that, just very briefly, since I mentioned quantum gravity at the beginning, my view is that there is something really incompatible between quantum mechanics and general relativity. But I think that incompatibility may be resolved, if you like, if we go back to a more discretized form of both quantum mechanics and if you like, I call this rational GR. I'm not sure that's a good phrase, but I mean, we know, for example, in there's Reggie calculus is a very good way of discretizing GR. And you get closer and closer to the continuum approximation of GR as the volumes of these simplicial triangles get closer and closer to 0. So that's got a nice smooth limit. That's kind of trivial limit. But this is a singular limit. So this is why I think one can understand why these may be compatible at this discretized level, even though they're completely incompatible at the continuum level. Now, if I had another hour, which I don't have, do I? No. I tried to tell you what I think is the deterministic system that underpins this RAQM, because I actually haven't talked about that. I've just talked about these bits being kind of generated by some underlying deterministic system. My own view is that this is actually has to be based on p-adic numbers rather than real numbers. And if you don't know what p-adic numbers are, this is just a simple one-sentence description. They are to fractal geometry as real numbers are to Euclidean geometry. So if you want to add and multiply, do algebra on fractal geometry, you have to use p-adic numbers. Real numbers don't work. And that links to my view, which, as I say, would be the topic of a different talk, which is that actually underpinning all this is, in fact, geometry, and that the universe is a deterministic dynamical system evolving on some fractal attractor or invariant set, as I call it. All right, so I've tried to describe a specific discretization of Hilbert space. I'm trying to say that quantum properties emerge from quite elementary number theoretic properties of trigonometric functions. I hope you've noticed that no collapse postulate is needed. The wave function is indeed, as Einstein always wanted it to be, describing an ensemble of deterministic states. Born's rule is automatically satisfied, so you don't need a separate axiom for Born's rule. For fine enough discretization, experiments that support quantum mechanics will necessarily support this rational quantum mechanics. The exciting possibility is whether there are experiments which support rational quantum mechanics which do not support quantum mechanics. And I have some ideas about quantum computing in this area, which I'm happy to talk about over lunch, if people are interested in. And QM is a singular limit as the discretization set to 0. And, well, I haven't talked about this, but I don't yet. So the most important point, I think the experimental violation does not imply physics is non-local in EPR's sense of the word, but there is something holistic about physics that we're not capturing in kind of conventional physics. It's perfectly causal, but it's holistic. And this notion of an invariant set or constraints that this invariant set geometry might pose could help explain that. Thank you.
Thank you, Tim. This was, yeah. We have almost 10 minutes for questions. Yeah, I will use this one, and I give this for this gentleman. Thank you.
Yeah, thanks. Fascinating stuff. Just try to get into really quickly. One is, did I miss it? Did you go over how Planck's constant manifests itself in your discretization? Because obviously, we actually have an actual bound on our uncertainty or bound on our certainty. So I assume it would be reflected in some factor of the discretization, right?
Yeah, I mean, the short answer is no, I didn't. And in a way, all I did was to introduce it as a constant which gives dimensionality to the, I had a number theoretic inequality, and to relate that to spin angular momentum, I need to introduce some kind of, because on the left-hand side of the inequality, I had 2 standard deviations, and on the right-hand side, I just had 1 mean value. So I've got to introduce a constant which has dimensions to make it dimensionally correct. So that's the only sense in which I've introduced Planck's constant.
Okay.
And I'm not just, yeah, so if you ask me what sets the value of Planck's constant, I'm not answering that question at this stage.
And then very quickly, I'll just try to make a guess about what you might say about quantum computation, or my first reaction was, so now quantum computation will be, all the quantum computations will be denumerable, and so therefore there'll be no hypercomputation, no hyperquantum computation.
No. My point is that in quantum, according to quantum mechanics, if you have a, something like Shor's algorithm or something which gives an exponential speed up over a classical algorithm, you can improve that exponentially divergent behavior with a classical computer by increasing the number of qubits. If you want to factor, a trillion-digit number, you just throw enough qubits at the problem, in a small time. Just throw enough qubits at the problem, and that'll solve it. In principle, that's what quantum mechanics says. Now, if this idea is right, that these wave functions are represented by finite bit strings, there's only a finite amount of information you can encode in them. So you're actually going to start maxing out. That exponential is going to start to saturate and flatten off. And there's going to come a point where you gain nothing more by throwing more qubits at the problem. So that's my prediction. The problem is, I don't know with any certainty what this value of n is. Otherwise, I'd be publishing this and hopefully getting in there before they measure that thing.
I see now in a way that both of the questions are related because it's about the resolution, isn't it? About
Exactly.
what's it? Yeah.
That's right.
I'm just trying to understand your first motivation slightly more. I mean, my immediate reaction seeing it was just, well, we have quantum theories on discrete spaces. I mean, just flat-footedly on the lattice, or in-loop quantum gravity as a subtler case. And those seem to be cases where we've got a continuum, a continuum space in the Hilbert space structure and a discrete space in the space-time structure. Is there something going wrong there by your lights? I mean, perhaps the measurement problem, of course, but other
well,
than
you can
that.
just take, I mean, this comes out just with a single qubit. So we don't have to think about, we don't have to think about infinite dimensional quantum systems. Just think of two-dimensional quantum systems. And so that when you talk about a lattice, you're talking about a lattice in some space-time lattice or something like that, is it?
Sure.
Because I'm talking about a lattice in Hilbert space. And of course, that violates, as soon as you do that, it violates the, the basic axiom of quantum mechanics.
Yeah.
And
So I understand that, but I'm not commenting on the framework. I'm commenting on your original pair of motivations. You gave two motivations. The second was the measurement problem.
Right.
And the first was that we weren't going to be able to do quantum gravity
Right.
and get discretized space without discretizing
Right.
the quantum structure of the theory.
Right.
And I was just saying it seems as if we have quantum theories that do discretize space but don't discretize the quantum structure.
well, I mean, I'm not aware of as I say, I'm not aware of a quantum theory. Well, I'm not aware of a quantum theory of gravity that people accept, and I'm not aware of any natural, rather than sort of ad hoc. You can obviously put in a discretized lattice if that's what you want, but then you have problems with Lorentz invariance of those lattices. So my motivation is that you don't put it in by hand. It'll come out of the discretized state space structure. The discretization of space-time is not something you impose, but it emerges. That's my conjecture, hope, I don't know. It's an emergent property of the discretization of state space.
Yeah. No, and I see how that's intended in the framework, and I see how that's plausible. I was just trying to explore the initial... You started with a slide like, why should we do this? And
Yeah.
one of the reasons you said was,
Right.
well, we won't be able to handle discretization in space-time unless we can do discretization in
Well, I didn't say
quantum
we won't
structure.
be able to handle it, but I don't think we'll have a theory where discretization emerges naturally. I don't think as far as I'm aware, I don't think we've got such a theory. That's a conjecture. I mean,
Sure.
I'm not saying it's true. I mean,
Yeah.
it's just a conjecture.
That's fair. Okay, thanks.
I mean, I've always been, the quantum gravity thing is always, because that's sort of what my PhD was on, but that's always kind of motivated me. But to be perfectly honest, as you probably know, David, I mean, I've spent most of my time just worrying about these more, mundane's not the right word, but more basic issues about Bell and the rest of it, yeah.
So there's room for one last question, if there is from the audience. Not online. I do have one. Is about, so you don't need operators. So what about the way measurement conventionally works in quantum mechanics? And this could have an important impact in the quantum computation process, right?
Yeah, you see, I don't think measurement, you see, in this picture, measurement, in a sense, isn't anything very fundamental. It's not doing anything fundamental except revealing to us, macroscopic beings, you know, the values of these bits in these bit streams. So, you know, somebody who's just said, you know, it represents some kind of decoherent interaction with the environment. I absolutely go along with that. That's basically all it is. But it's not a fundamental, you know, like, you know, it's not like the theory, like in standard quantum mechanics, you go from a superposed state to some eigenstate through some, you know, as yet mysterious mechanism that we don't know anything about. This is not the way it works. These bit strings, you know, they are encoded in the wave function ab initio, if you like. I mean, they do reflect this holistic, I mean, this is an important point. I mean, they do reflect some holistic structure in the world.
But you still have a probability. You still have a probability, or
yeah.
So
you can define you can just find a finite, very simple finite probability measure on those bit strings, and those replicate the probabilities you get in quantum mechanics. But there's nothing fundamental about measurement in this sense. It's not doing anything fundamental like collapsing the wave function or reducing the wave function. That doesn't happen.
Oh, last question. Bert, very short.
The question is short. So you had this polar representation with the discretization. Maybe a more elegant discretization would be something that would be not polar, that you would have a tessellation of the sphere and have equidistant points and go away from such a polar coordinate system. Would that be possible, and how does it affect your?
Well, you can do it on the. I mean, you can do it on the Argand plane, but you end up basically a circle. You know, the point. If you draw a circle around the origin, the discretized points lie at constant angles, and then if you go out along a kind of array from the origin, the square of the amplitude must be rational. So that would define.
No, but I'm questioning. I'm wondering whether you could make another tessellation of the unit sphere, just putting.
Well, an important property.
Point there.
Yeah.
Instead of using this phi and theta kind of coordinate.
Well, an important property.
Can you repeat the argument for the recording, please?
Sorry?
Because he had not the microphone. Can you repeat his argument?
Oh, well, can I do a different, more natural tessellation? I mean, look, you know, there are discretizations of the Argand plane, like the Gaussian integers or the Eisenstein integers. These are all discretizations which actually retain some of the algebraic properties of complex numbers in the sense of being able to add and multiply. But I absolutely do not want that. I've deliberately chosen this, if you like, tessellation because of this, because it has these two incommensurate, the discretization in the sort of equatorial direction and the discretization in the going over the poles are incommensurate, and that is a fundamental property. That is the thing that gives me all these properties about counterfactuals being undefined. And that's the thing that allows me to evade, you know, the normal interpretation of Bell's theorem, for example. So it is important that it doesn't have the you know, a mathematician would hate this because you lose a lot of the algebraic structure. But I would say, to hell with that, because the algebraic structure, you get it back once you dig down to the deeper deterministic level. Losing it at the Hilbert space level, who cares? Because these Hilbert vectors aren't fundamental from that point of view.
All right, so we can continue this interesting discussion at lunch. Let's thank once again Tim for this surprising conjecture and idea. All right, so hello, Hans. So hello, everyone, and welcome to this after lunch session. We have Now the talk of Hans Liljenström from the Agora for Biosystems that will be about can physics and neuroscience follow free will. Hans, please.
Hello from Sweden on our National Day. And thank you to Paavo and the organizers for inviting me. I wish I could be with you physically, but unfortunately I couldn't. My doctor advised me not to travel with my foot injury, so that I have to stay at home. Sorry for that, but I hope this will work as well. So I will talk about physics and neuroscience with a focus on neuroscience. I will give a little bit background and talk about determinism and indeterminism, primarily in physics. But then I will move more to my main focus, which is the brain, mind, and causality, where intentionality, decision-making, and volition are in focus, and also our neurocomputational modeling of these activities. And then I will end with discussion and conclusion. So, why am I here? Actually, when I prepared this talk, I thought I would be in Helsinki by now. But let's pretend I am there. So, is it because of deterministic laws that I'm not in Helsinki? Or is it by chance? These are the only explanations or reasons that physics could give to why I would be there. But I feel that I'm there by free will. I decided to come to Helsinki after the kind invitation. Then, perhaps by chance or by deterministic laws, I was forced to stay at home. But the feeling of having a free will, of deciding completely by myself, is so strong. I think everybody, or most people, feels this. But is it so? Is it really so? When we listen to science and when we look at the literature on the matter, it seems that free will is an illusion, that we don't have any free will. Later there was a book that came out by the biologist Robert Sapolsky, who said that we are determined. It's a science of life without free will. And I think this is actually quite a general view in science today. So the motivation for this talk, and actually our research, is that current science cannot explain consciousness or free will, which yet seem fundamental for human nature and a meaningful existence. Neither deterministic laws of nature nor chance events at micro level or any level allow for free will. Neuroscience even seems to have demonstrated that conscious free will is an illusion. But willful acts require decision-making, and we are interested in understanding the neurodynamics related to decision-making and investigating the implications for free will. So I will talk primarily on these latter parts. But let's first look at the laws of nature. Are the laws of nature necessarily deterministic? Why do we think so? Well, originally they are based on Newtonian mechanics for rather simple physical systems. And Newton himself was true Christian also, so he actually believed in the deterministic laws of God. So I think that is one of the origins of the idea that these laws are deterministic. But what about Popper's propensity theory? Could that be an alternative? Or dispositionalism by Mumford and others? Or something else, another view on the laws of nature? that is not deterministic in the same way that Newton thought. So what about quantum processes? We have heard a lot about that in this conference. And is quantum indeterminism related to free will? Is a collapse of the wave function related to free will? Can, for example, the Agora theory of Penrose and Hameroff and the quantum effects in microtubuli account for free will? Or can Bohmian active information provide a basis for free will? Or what else? Actually, I will not talk so much about these things in this presentation, but we could discuss it at some point later, perhaps. But I will instead give some views by some of the most prominent scientists in the last century and currently. That sort of sets the tone of the common view of science today. And one of those were Jacques Monod, a geneticist who got the Nobel Prize in physiology or medicine in 1965. And he wrote the book, The Chance and Necessity, where he argues for that the only explanations we can have in science for anything happening is either randomness, chance, for example, at the microscopic level of quantum systems, etc., but also by natural laws. Nothing can occur that is not compatible with the natural laws, he says, which is a little bit strange because he also says that we humans emerge only by chance. But anyway, another strong proponent of determinism was my postdoc host and mentor, John Hopfield at Caltech. He means that the notion of free choice or free will is meaningless, actually, because all our actions are in fact determined. And he even calls free will a myth. That's a myth of free will. And it doesn't, because it doesn't fit with the physics. It doesn't enter into the equations. So this was his view for a long time, but actually I visited him on his 90th birthday last year. Then it seemed that he had actually changed a little bit. He wouldn't give it up completely, but he tended to be more vague on this point. But that's another story. Francis Crick is another one who actually is one of those who opened up neuroscience to the problem of consciousness in the early 90s. And in his book, The Astonishing Hypothesis, The Scientific Search for the Soul, he says that the astonishing hypothesis is that you, your joys and your sorrows, your memories and your ambitions, your sense of personal identity and free will are in fact no more than the behavior of vast assembly of nerve cells and their associated molecules. You are nothing but a pack of neurons. So now we know that. But there are actually alternative views. For example, by the cosmologist and mathematician George Ellis, he says in the book Downward Causation and the Neurobiology of Free Will that all scientific experiments are based on purposeful activity and free will, enabling decisions based in abstract analysis that lies beyond the explanatory scope of physical science. And he talks about top-down and bottom-up causation that occurs simultaneously. So this is quite a different view from the previous ones we've heard. Another one is Giulio Tononi, who is the father of the integrated information theory, IIT. And he says that the first axiom of IIT states that experience exists intrinsically. As recognized by Descartes, my own experience is the only thing whose existence is immediately and absolutely evident. And it exists for myself from my own intrinsic perspective. So this view is completely opposite from that of Francis Crick, which means that the only thing I can know for certain is that I'm conscious. The theory about my neurons are just a theory. They are not one of the axioms that he has for his IIT. Funny enough, actually, Christoph Koch, who previously worked with Francis Crick, has now joined Tononi for this IIT theory, which is quite interesting. Another proponent of an alternative view on the brain and consciousness and free will is the late Walter Freeman, who has his own view on consciousness related to neurodynamics of the brain. And his theory is perhaps closer to the global workspace theory, but it's a theory of his own, I would say, where he emphasizes intentionality, not only in humans, but in animals as well, that he studied. And he says that voluntary acts may be considered acts of free will. And these, we cannot avoid making choices. So this is inherent in our beings. But it's up to us as subjects to decide. So here, the subject is something else than just the neurons. And again, this contradicts or is opposite to the view of Hopfield, Crick, and others. So Freeman's view on intentionality is that it cannot be understood by linear causality, and he says instead that circular causality is better to explain what's going on, and that there is an action perception cycle in our system, in our nervous system, which we're embedded in. And he has 3 properties of intentionality, which is directedness, unity, and wholeness, which are associated with 3 stages of intentional behavior. That is a categorization of emotion and value, an integration into gestalts, and a decision to act. I will talk more about intentionality because in my work we have used a lot of data from Walter Freeman made on animals, but also the general ideas of intentionality related to neurobiology. So this is a sketch of Freeman of an amphibian system, nervous system of intentionality, this action perception cycle of intentionality, in particular related to the olfactory system, which was the topic of study for Freeman. But in general, brains, in particular the human brains, could be considered as a complex system with lots of feedback loops within and without, which really makes it difficult to find the causal pathways or to understand what is causing what. Is it the brain or the neurodynamics or the mind, if you like, which comes first, or the mental events or the physical events are first priority, so to say. This cannot be understood by linear causality, according to Freeman. But we can try to map the causal pathways, for example, by computer simulations, computer modeling, which we ourselves have been working with, actually. So this is more or less a picture of the nervous system with a sensory hierarchy and a motor hierarchy, where the different subsystems of these hierarchies are interacting between themselves and within each hierarchy. And of course, this is part of the organism interaction with the environment. So we perceive the environment and then act upon it in a cycle. And in this cycle, it's sort of difficult to determine what comes first. So in my own view of the action perception cycle, I connect it to my view of consciousness and its dual aspects of intention and attention. And in the human brain, cognition is very prominent, of course, related to consciousness and our perception and action. But in non-human organisms, intention and attention doesn't need to go via cognition, in my view. So I consider consciousness as a graded process, not a dual either or, but that it comes in grades or levels. So all organisms, from single cell organism up to the human, have some degree of consciousness, in my view. So, and it depends on the complexity of the organism. The more complex, the more consciousness. So that in that sense, it also aligns with the IIT idea of consciousness connected to the level of complexity of the system. So what about the causal role of consciousness? Well, according to the Stanford Encyclopedia of Philosophy, if consciousness doesn't have any role or any causal impact on the environment or on the world, it is questionable if it has any significant role at all. And I would state that differently, but in the same line, that causal effects of consciousness are most clearly linked to intention, the actions that we make on the environment, which has to be considered if we are to understand the role of consciousness in evolution. Most of the research on consciousness or study of consciousness is primarily on the attention part, attention aspect, which is the perceptive or the qualia, but not on the active part, which is the intentional aspect. So I think this should be more emphasized in consciousness studies. And it's related, of course, to free will. Intention precedes conscious free will. Actually, free will is a little bit difficult concept, because I would prefer to call it conscious will, because it says more what it is about. And the study of this, we could call it neuroscience of free will or neurophilosophy of free will, where you actually study what happens in the brain when we have intentions or are performing willful acts. That is also connected to agency, of course, and moral responsibility. I will not talk about that here, but it certainly is. So there is a number of so-called free will experiments where people have done a lot of measurements and also stimulations on the brain in relation to volition or voluntary actions. And in particular, I would mention the work by Benjamin Libet and his colleagues, where they measured a signal here in supplementary motor area, SMA, a few or at least half a second before we became aware that we wanted to move, for example, a finger. So this simple movement coming as a result of an urge to move was preceded by this signal in the supplementary motor area. Now, this was done primarily in the 80s, but later on, already, I mean, also in this century, 10 15 years ago, the group of John Dylan Haynes, they did fMRI studies where they could actually see signals in the prefrontal cortex and the parietal lobe up to 10 seconds before the subject wanted to or felt an urge to move a finger or push a button. So this is quite remarkable. I will come back to that later on, but this gives an impression that the brain knows before you what you want to do. But is this really so? Well, first of all, I should say that this signal that was found in the pre-supplementary motor area is called the Bereitschaftspotential. It was actually first found by Kornhuber and Decke in the 60s. And in English, that's the readiness potential. So this is a potential that they found when you sum a lot of subjects performing these simple actions with the fingers movement. So it's not that every time you can see this, but overall you find this signal as accompanying your sense of willful acts. So the question is does this really test for free will? This is just arbitrary movements of our fingers, and is it really related to free will? Well, actually, this was discussed at the conference we had in Sigtuna in 2017. Pavel was there as well, and we had gathered a bunch of neuroscientists and philosophers to discuss this current state of free will in science, and in particular in relation to experimental studies such as Libet's experiments and John Dylan Haynes studies. And actually at this conference, we decided to propose for a project to try to investigate this. And 2 years later, we got funding from the John Templeton Foundation and the Fetzer Institute to set up a 4-year project on the neuroscience and philosophy of free will, with some of the most prominent neuroscientists and philosophers in the field, 17 altogether. And we primarily wanted to investigate the role of consciousness in decisions and in willful acts. What is the role of consciousness, and how is it related to the intentions we have? And also, if there is a difference between conscious control in deliberate versus arbitrary decisions. Where the arbitrary decisions are those in the Libet experiments where you just push a finger or button whenever you feel like it, and it doesn't have any consequences what you do. So we set up experiments that would test for more realistic experiments where there were consequences of our actions. So this is an illustration made by John Dylan Haynes about what is the issues that we were going to discuss. And of course, here, this is representing the consciousness. If consciousness comes first, and then the activity in the brain, and then we move. Or if the brain comes first, and then this gives rise to conscious experience, which it really doesn't have any role. It has no cause. It's an epiphenomenon in this view, and then comes movement. So in a sense, this could have been omitted in some sense, but then we would have what we would call a zombie. So these kind of simple movements are that I told about with Libet's experiments. They can be to 60%, and also John Dylan Haynes' work with Soon and et al. You can predict with a probability of 60% what a person move left or right finger, for example. But if it's more complex decisions, it's very difficult to predict the outcome. So the causal pathways are very difficult to come about, to understand what's going on in the brain. And this was what we wanted to address with the help of neurocomputational modeling, in particular for decision making, which is most important of our cognitive processes related to behavior. And it's of course crucial for survival of all higher animals. And it's linked to the sense of free will. But if our willful acts should have any evolutionary effects, as we said before, our physical body must be under the influence of our consciousness, which is an example of downward causation. And downward causation is a problem in neuroscience or in any sciences, I would say, because it seems to contradict the typical reductionist view of the world, as is most common nowadays. So while decision making then is very important, it's not as rational as we like to think. And Kahneman, the Nobel laureate Kahneman, showed this, and he has tried to show how there is an interplay between intuitive or emotional and rational or cognitive systems in the brain, and which he refers to as system 1 and system 2, and it's also linked to thinking fast and slow, which actually was in the name of his popular book. And it's related to, in some sense, to bottom-up and also top-down causation in the brain. So the system 1 corresponds to the old mind, or old brain even, and it evolved early, while the system 2 is more the neocortical part of the brain. It's evolved later, and it is slower than the fast intuitive or emotional system. And also this system type 2 or system 2 is conscious, while the system 1 would be non-conscious, according to Kahneman. We have taken this as an outset for our own modeling, neurocomputational modeling, but we take it more, we have actually mapped the system 1 and identified the system 1 and system 2 in different brain areas and tried to find the causal relationship between the two and how consciousness comes in, and not as a just all or nothing phenomenon, non-conscious or conscious, but different degrees of consciousness again. So we use these computational methods to study these the cortical subsystems involved in decision making, and in particular the amygdala, orbitofrontal cortex, and the lateral prefrontal cortex, which are some of the key areas, brain areas involved in decision making. And we use population dynamics, similar to the kind of dynamics that Walter Freeman studied in his animals. So again, the two systems that are involved is system 1 is the emotional, which is primarily amygdala and orbitofrontal cortex, and the cognitive or rational part is the lateral prefrontal cortex. So in this figure, we see that this is system 1, the emotional or intuitive, as Kahneman calls it, part. And here we have the system 2, the lateral prefrontal cortex. And the activity of these areas are sort of competing or interacting. And which will win depends on many different factors. But the signals eventually are integrated and may lead to a decision, and then that decision may lead to an action. And we act upon the environment and the society and get feedback from this and learn what the outcome of our actions. So next time we perhaps or hopefully will act better in the future if we failed the first time. So this is again a way of looking at it from an action perception cycle. So again, we have made a 3-layered structure. Actually, the neocortex has 6 layers, but they could be compressed in 3 layers. And we look at the neurodynamics of this excitatory layer and 2 inhibitory layers interacting. And we try to mimic the real neurostructure of the brain, but with rather simple equations. Actually, these are Hopfield-like equations, but we have more realistic connection weights, connectivity than in the Hopfield network, and we have time delays and so forth. So we have a three-dimensional network mimicking 10 by 10 millimeter square of the cortex. So I will just show you the dynamics. I hope it works. I hope you can see how the dynamics works. This is excitation and inhibition in balance. Can show it again. So this is what it looks like. It's very similar to what you find if you have electrodes measuring the activity of the cortex. And it's primarily the middle layer, the excitatory layer, that gives a signal to the other areas of the cortex, for example, motor areas where a decision is transmitted to an action. And in this case, we have the system 1 as a fast system, and then system 2 activity. So this has EEG-like neural network activities that the networks that are model networks are simulating. So depending on, so if we have 3 different choices, we calculate the value of these different cell assemblies that correspond to each of the choices or options, and then the maximum value wins of these different options that we may take. I should finish soon, the time is flying. But we also use this to look in particular for the intentional process preceding the readiness potential. That is, we want to trace where does the readiness potential that is found or measured in the pre-SMA, where does it actually come from? And we think it is primarily from the LPFC and ACC in these areas in the cortex, in the frontal cortex, that initiates the activity and is related to the free will. So there is an interplay between the neural oscillators in these areas. I won't go into the details of this, but the dynamics of these cortical areas is kind of a chaotic-like attractor. That is how we model it, and it seems similar to the measured activity. And then there is a collapse of these, or I should say a convergence of these chaotic attractors into limit cycle or near limit cycle attractors. And that's when a decision is being made, when there's a, we can call it a collapse of the chaotic attractor to an ordered limit cycle attractor. That is when a decision is being made in our model system. So here we again see that the intention is an increasing activity of the primary. This is from the lateral prefrontal cortex, and we can see that it's a graded awareness, we could say, before we are. So we can stop the decision to act any time before, but then it comes to a point where point of no return, so to say, when the activity has come too far in order to inhibit the urge to move, let's say. So here is the readiness potential, and this is a part that we have modeled preceding the decision, actually. So, to conclude, our decisions are based on biological, of course, but also social environmental facts. We have actually made a model of social interaction as well, but I didn't talk about it today. So there's a complex web of causation in which we are embedded. And the unpredictable outcome of an individual could be seen either as a result of random or deterministically chaotic neural activity, or alternatively as a result of free will. In the first interpretation, upward causation could be an explanation, otherwise downward causation, which is more controversial now, today. Again, as I said, downward causation is a kind of a problem in the scientific view. So intentionality is best explained by circular causality, as Walter Freeman suggested, in terms of action perception cycles. And the problem can be viewed in the context of decision making, as we have done, and deliberate decisions are value driven, which is typical for free will choices, in contrast to arbitrary decisions, or when we just move our fingers at will, or when we feel an urge. So the experience of our decisions or choices can be learned and influence then future decisions. That is also an important point here, that we have a model in our neurocomputation model. So the final discussion is that science has problems encompassing free will because it requires the action of conscious agent. And science only deals with objects, not agents or subjects, other than as observers. The theories and laws of physics were developed for inanimate, comparatively simple objects and their interaction, and have very little to say about the behavior of complex biological systems, in particular regarding brain-mind systems and their interactions. Already Einstein and Schrödinger recognized that the insufficiency of physics to describe the immense complexity of living systems. So in order to allow for consciousness and free will, science needs to be extended beyond chance and necessity, which currently are its only models of explanation. I will end with a book that came out from our project on the neurophilosophy of free will. It's a book about a conversation between philosophers and neuroscientists. 15 chapters deals with questions from neuroscientists to philosophers, and 15 chapters about questions from philosophers to neuroscientists. It's edited by Ura Maus and Walter Armstrong. So, thank you for your attention.
Thank you. We have exhausted our allocated time, but I would allow for one question. Please.
Thank you for the talk. I wanted to ask if there is a possibility of, like, rather than top-down or bottom-up causation, could there be a simultaneous causation between brain activity and will, like a circular? Like, can we say that if there could be a model where these two things are always hand-to-hand, in a sense?
Yes, thank you very much for your question. Indeed, I think the simultaneously here is quite interesting, because this the window of simultaneous of a moment in the brain is about 10 milliseconds or 20 milliseconds perhaps, and within that time frame we can see that there are linkages between both experiences and activity of the measurable activity. So yes, indeed, I think that is a good way to approach it. But and this may also be seen partly in our own model because we have a graded conscious experience. So we can actually shift that by will, I would say. We can learn to be more aware of our early intentions. So we can actually come closer to this half a second signal that Libet found before we really will something. And we can push our awareness, so to say, to recognize the signal early on. Thank you for your question. Very good.
Okay, thank you. Are there very quick questions? No? Okay, so let us thank Hans Liljenström and Hans also very best wishes for a prompt recovery.
Thank you.
I understand you very well.
Thank you.
Having a fractured foot as well. Okay, thank you, Hans.
Thank you.
All right, and now it's the time for our final panel discussion. We haven't have a terribly fixed or rigid plan for this. We felt that we, base it on what we have had, like 2.5 days full program, full of talks, very intensive program. But I think the way we thought we set it up is that we would have like opening statements for the keynote, so from Sylvia De Bianchi, Tim Palmer, and David Wallace, and then some of the other plenary speakers, if you want to come here to the front, or we could sit in the front. Just physically, that's the way we can set it up, and then we can have like shorter questions and comments. And of course, like some of the big topics we have, of course, there's been the question of underdetermination in quantum mechanics. Yesterday we talked a lot about the dynamic universe, so we'll see how it goes. I may also then direct with some questions, and if you have this Presemo open, then maybe, who knows, maybe people will write questions then. We will open up it to the audience as well, but who wants to go first? Dave, do you want to?
David first.
Yeah.
Oh, yeah, okay, sure.
Yeah, we want to go. But do you want to?
Yeah,
you can go there, yeah.
Probably not giving me
Yeah, that's right. That's right. Yeah.
Okay, so let me just start quickly by thanking Paavo for what's been an extremely eye-opening meeting in many ways. I think a rather common theme of, by no means all, but a great many of the talks here has been, in various different ways, sort of, what's wrong with physics? What are the problems with our apparently deep physical theories? How can we go beyond those theories? What lessons can we learn about the sort of ways in which our methodology and approach in science is just wrong, blind, missing things? What are the sort of dissident and minority views that we as philosophers need to focus on? In short, how do we wake up from the kind of dogmatic slumber we're in as a consequence of the kind of monolith of physics going on? And I think I'm sort of been playing the loyal opposition at this conference, and that I think the basic message of most of what I've been saying in my talks and largely in questions has been physics is all fine, get back to sleep. So I just want to say a little bit about that. I mean, mainly I'm taking that line simply because I think it's important that somebody's taking it. And so, there needs to be, if philosophers of physics are the gadflies to scientists, then occasionally gadflies also need gadflies. But I suppose I might instead want to try saying something a bit more constructive as to what I think, if you think you need to change a theory, if you think something's wrong with physics and a new physical theory is needed to sort something out, just some sense of what the challenge is that needs to be faced there. And I think that the challenge isn't always obvious unless you're in that bit of theory. I think that it's easy to think of the challenge as something like what are the sort of broad features that need to be explained? What's the nature of how, say, general relativity describes gravity, or what are the weird things about quantum mechanics? And then the thought is like, how can I get a theory that has those kind of features? Or even better, how do I get a theory that doesn't have those kind of features, but somehow explains away how it is that we ended up with a theory that had those kind of features in the first place? And so we saw the idea that, people, if gravity does these kinds of general things, then we need a theory that does those kind of general things. If quantum mechanics has these kind of weird features, then we need to explain away those weird features or produce those weird features a different way. And that's in itself absolutely right. But I think it's just really important to stress the extent to which modern mature physics doesn't, by and large, commit to any of the particular things it commits to because of some general philosophical predilection. It commits because it's a very long way down an empirically connected process of reproducing an extremely large amount of empirical observation data to extremely high precision. So, what do we actually need if you want an alternative to general relativity? We don't need some broad explanation of how the world is qualitatively that sort of connects up to general relativity. We don't even need a re-engagement with the 3 or 4 historically significant experiments that led us to general relativity in the first place. We need to take the entire data set coming out of the LIGO gravity wave experiments and the entire data set coming out of the Event Horizon Telescope, and we need to reproduce the ability of general relativity to predict that data to extremely high precision. And similarly, if we want to develop an alternative to quantum mechanics, we want proofs of concept in the first instance, but, and I think Tim would agree with me here, this is the sort of end of Tim's talk, in due course what we need is the actual dynamics of the theory and the confirmation that those actual dynamics should reproduce all of the predictive work that comes out of quantum mechanics, the spectrum of the atoms, the magnetic moment of the electron, all the kind of predictions, sum to 10 figures that come out in quantum mechanics. And as a practical matter, nearly always, at least in the sort of full empirically confirmed frameworks of our theories, what that actually requires isn't something you can check prediction by prediction. It normally requires a fairly systematic recovery of the mathematical structure of the reproduced theory in a certain domain. So, for instance, I want to better say that general relativity is just systematically predictively effective and extremely precise in the regime of colliding black holes. LIGO has shown that really very strongly. So, unless one's going to take the desperate means of saying that the LIGO experiments are cooked up or something, then what one would need to do is to demonstrate a mathematical equivalence between one's proposal and general relativity in the regime of colliding black holes. And then, of course, to say, well, here's how either my theory reproduces general relativity all the way along, or here's how it reproduces it in those regimes where we've tested it. Here's what it says in regimes where we haven't tested it, or where there's an anomaly in general relativity. Here's how we do better there. And again, I mean, to jump back to something earlier, the Mond approach to gravity, which we had discussed very interestingly yesterday, although I have my criticisms of that framework, absolutely lives up to that kind of framework and sits into that structure. And notice, I mean, I'm putting this in extremely mathematical terms, and I really do want to insist that and this came up a little bit in some of the other discussions, this is absolutely central here. The reason physics models things in mathematics isn't because of a sort of generic trend towards empiricism or some broad prejudice or something. It's because that is how physics manages 10 significant figure predictions. It's how physics manages to build the aircraft you all came to this, or nearly all of you came to this conference on. That's the format in which those predictive frameworks are available. I mean, I have no objection in principle to finding a way of doing things other than in math, but it'd better get me back those 10 significant figure predictions. So, if you like, that's the challenge I want to put. Now, you can respond to that challenge, and I'm inclined to respond to that challenge by saying, as a philosopher, I think my skills are better spent trying to understand and engage with the successful theories we have, rather than trying to develop their alternatives. But that's only what I think. It's not a recommendation for everyone else. It's fine for different people to have different calls on how, for instance, fundamentally unacceptable many worlds approaches to quantum mechanics are, or how fatally incomprehensible our abstract theories of gravity are, and to use those as motivations for developing projects. That just has to be done with one's eyes open, and it has to be done with a realization that until and unless you have that actual full reconstruction of the mathematical structure of our successful theories in their successful domains, then what we have is a research project, a plan to carry out, something that we can explore, that we can philosophize about, by all means, as well as develop. But we need to do so in the appreciation that what we're not discussing is something which at this moment is a rival to the orthodox theories. It's a plan that might lead to a rival in the fullness of time. I think that's all I've got to say.
On the very same topics that have been touched by David, so maybe I will say something very briefly on some aspects of this conference that, well, first of all, thank you, Paavo, and the other organizers. You put together in a beautiful way, I think, because we had time to touch fundamental issues. I would rather focus on philosophy, but broadly understood now, in the sense that the very same title of this conference points to one fundamental question that shaped the history of Western culture and also other cultures in reality, which is reality. Sorry for the joke, but we talk about reality, but we don't have a unique account of it. So for some people in this room, reality can have a very broad meaning. For others, it must include, as far as I can see, consciousness, whatever consciousness is, because if I ask what is consciousness, apart from a few people, for example, in the last talk, I think that there was somebody who had clear in mind what consciousness is, at least in his view, but I really don't know what consciousness is. And when we talk about physics and reality, of course, we're talking about, okay, something that we can recognize and isolate, if you like, or identify with what we call scientific theories, scientific models, and practices also, with observations, experiments, and so on. I'm referring to physics. Of course, when we talk about reality, we are talking about something, if you like, that is at the center of the philosophical reflection. It should be. It's the ontological, it represents the word for the ontological question that any philosopher in the past asked. So my question then would be, okay, are we philosophers able today to produce an understanding of reality, whatever it means, that is suitable, that is compatible with the current development of scientific enterprise in our epoch? And I fear that the ontology and eventually the metaphysics that philosophers endorse and reproduce is not enough, for sure, or is not, or could be better, let's say, than the one that we are producing. And there is this, now I will conclude with this provocative question, and that's it. So what if at some point somebody comes up with a philosophical system or with a philosophical work that clearly defines existence as being different from reality, as being different from possibility, in such a way that many paradoxes that we encounter in quantum mechanics at least are more nuanced, if not disappear? So this is a question that I leave to the public for further discussion. Thank you.
I was asked to speak by Paavo. I feel a bit of an imposter here because I'm not sure I have anything somehow I don't feel I have any unique status here. I'm sure any of you could do just as well. So I'm going to fire out a few random thoughts. First one was a little bit inspired by David's comments. And it kind of goes to also some of the talks I heard on the first day about some of the frustrations, when one works on alternative, say, ideas to the mainstream, why aren't these accepted? And what I want to say kind of links a little bit to the last talk, because it's kind of curious, I think, how, in a way, subjective scientific investigation can be. I first remember reading about Bell's theorem some 40 years ago. And all I can say is I got a gut feeling that something wasn't quite right. And I had a gut feeling that my knowledge I had in nonlinear dynamics could be relevant. Now, I've sort of long since accepted that until the day where I can make some unequivocal experimental prediction about some experiment that can be done, which would show daylight with quantum mechanics, I don't expect anybody to believe, I certainly don't expect physics departments to suddenly drop quantum mechanics in favor of anything that I may say. But in a way, none of that matters, because it is this sort of gut feeling. And I think, I don't know, for young people in the audience, I think that is actually quite... I mean, in my career, I've just felt that kind of very subjective feeling you have about things is quite an important aspect of following one's nose, even if one's nose, even if you can't really objectively justify where your nose is telling you. If you feel that somehow strongly inside, I think it's a good signal, because it gives you motivation to do things. And if you're right, it will set you apart from the others. So I do feel the subjective kind of feeling that one gets is something you shouldn't suppress in your scientific career. So having got onto the brain and all that sort of stuff, I thought I would just say I was quite... I agreed with 95% of the last talk. If you like, I'll say at the end the bit I disagreed with, but it's a kind of fairly trivial thing. In the sense that I do think that free will is a real dilemma. And I think part of the problem, my own, again, this is my gut feeling, and it kind of links to some of the things I said. I think perhaps some of the problem is that we think of determinism in a very kind of classical way. We have some initial conditions which were set in stone at the time of the Big Bang, and some evolution laws which then inexorably took these forward in time to the present. And if you believe that, if you really do believe that, then Hitler is no longer responsible for killing the Jews, because it was all determined by the Big Bang. And that's just morally, it seems inconceivable that one could believe that. But I don't think you have to believe that that is the only way of formulating the notion of determinism. And I was really excited to see the maps of chaotic attractors that they had reconstructed for the brain. This is a deterministic geometric system. It can be described by some initial value problem, but equally it can be described in its own intrinsic terms. I mean, the very simplest example of an attractor is a limit cycle that just goes round and round in a circle. And so you can describe that by x squared plus y squared equals a, or something, where a is the radius of the circle. So that's the specification of that deterministic system. Nowhere have you had to say what the initial condition was. It just goes round and round in the circle. And chaotic systems are just more complicated versions of that. And again, this is my gut feeling against expressing a view which I can't quite articulate, but I think this talk has given me some reason to think about it, that I think maybe we can formulate the notion of free will in a deterministic environment in terms of these more holistic structures. And that very much plays into the Ellis top-down, bottom-up causality I mean, if there are these geometric structures which are playing a role in the deterministic formulation of the laws of physics, then there will be an element of top-down. That is the top-down. So just thinking of always, you know, if you like, the philosophy of particle physics, that everything is just determined by the tiniest scales, ultimately the Planck scale. I mean, that just may be fundamentally incorrect. So I think there's some quite exciting thing. The only 5% I disagreed with is the Kahneman. I don't think Kahneman's experiments do illustrate that we're irrational. I've always felt that this is a misunderstanding. There's this famous puzzle, I'm sure everyone's heard it, the bat and the ball. How does it go? The bat and the ball together cost $1.10, and the bat costs $1 more than the ball. And the question is, how much does the bat cost? How much does the ball cost? And you know, 90% of people ask that question sort of spontaneously say 10 cents. Because the whole thing costs 10 cents and the bat is $1 more than the ball. But that's not the correct answer. If you work out the maths, the ball has to be 5 cents. And then the bat is $1.05, and the two make up $1.10. But the point is, we answer that with our intuitive, system 2, is it? The intuitive system. And that seemed to be an example of irrationalism. But I don't think it is at all, because every day we have to make gazillions of decisions. And, you know, something like this bat, somebody comes up to you and asks you the bat and the ball problem. I mean, who cares? They're not offering you £1 million. They're not going to kill you if you get the answer wrong. So if you sent every single decision that you had to make to your logical, slow, energy-intensive process, you'd have no energy at all to do the important decisions in life. So the fact that we get answers wrong is just an indication that we have evolved an incredibly energy-efficient organ, you know, which runs on 20 watts, 6 orders of magnitude less than a supercomputer. So I see the fact that we get the wrong answer to the bat and ball problem actually as an illustration of how rational we really are. Giving the right answer would have been the irrational answer, because it would mean you're spending valuable joules of energy in answering a totally unimportant and irrelevant question. If you had to answer it on pain of death, then yes, then it's worth thinking very carefully about whether you give the right answer. But of course, these kind of tests that these psychologists do, they're not going to kill people, hopefully. Maybe they do, I don't know. I'm just rambling away. Thank you.
Oh, okay then. So, any follow-up comments or questions from here? Or you can also start a new line if you want. But okay, let's get Tuomas.
I'll take the cue if no one else does. Well, two general points. Well, one general point really. What interests me in this conference and quite generally is the methodology of doing cutting-edge science, which to me is or needs to be continuous with doing cutting-edge philosophy or philosophy of science. But I suppose just because David gave such a nice little challenge to us in his opening speech, if I may pose a question or a challenge back to David on something that came up on his talk already, which is that we still do have big unsolved, I'm not going to say mysteries, but issues in contemporary physics and cutting-edge philosophy of physics as well. Such as the measurement problem. So you hinted at that at the end of your own talk that chips may fall differently depending on the solution to the measurement problem if one is forthcoming. But since you were opposing underdetermination in general, and I feel like you were opposing underdetermination in your last remarks here as well in some regard, wouldn't it be the case that we still have a very serious underdetermination with regard to that aspect of contemporary philosophy of physics and indeed physics itself? And doesn't that entitle a little bit more epistemic humility?
I'm all in favour of epistemic humility. People should be humble, absolutely. But underdetermination doesn't mean we don't know the answer. I mean, our quantum theory of gravity is not underdetermined. It would be underdetermined if we had two quantum theories of gravity, all of which was able to reproduce all of the current empirical data in the world. We actually have zero theories of data. That is a problem. It's a scientific challenge, but it's not underdetermination. So if you think if you think that the measurement problem is unsatisfactorily resolved in contemporary quantum mechanics, I mean, I disagree. I think it's just fine, but you don't need to buy that. If you think it's unsatisfactorily resolved, then depending how you want to think about it, you're going to think either that this is a significant anomaly in our single empirically successful theory of relativistic quantum mechanics, or you're going to think it's worse than an anomaly. It means that our single theory of relativistic quantum mechanics shouldn't be seen as empirically successful at all because it's just unacceptably broken. It's at most some kind of calculational algorithm that somehow physicists learn how to do, like a lot of trained monkeys, or whatever people think about this. And in any case, that's still not underdetermination. That just means we have zero theories in that domain. And if you want to come up with a theory in that domain, you're not excused from actually reproducing the data by your philosophical objections to the extant programs. Does that address the...
Yeah, that's fair enough. Yeah, I mean, I take it that maybe we shouldn't call it underdetermination in that case, but we should call it something else.
Yeah, no, it's fine to still say there are crisis problems in the framework. I'm sanguine about contemporary physics, but there's still plenty of problems in it, and any of those might eventually kind of metastasize into sort of the kind of Kuhnian anomaly that brings down a research program. That's perfectly possible. It can happen, but again, doing that needs to engage with the progress so far. I mean, look, the slogan that physicists often get criticised for in philosophy by philosophers of physics is the whole "shut up and calculate," and I think philosophers have got a point that physicists should stop shutting up, but they're still supposed to keep calculating.
Nicely put. Thanks, David.
Let's have Tuomo could maybe say that. Yeah, okay, yeah.
Okay, thanks. So this is mainly for you, David. Yeah, I fully agree with you that let's start from general relativity, that it's trimmed close to a perfection within the frame of general relativity. And however, when I look at outside the framework of general relativity, then it looks that in many cases trimming is not made to the theory but to the reality. So that instead of trimming the theory, we are changing the reality. For example, adding dark energy or some other new features to reality, which are not inherent features of the theory in the theory originally. The cosmological constant, which Einstein introduced in his 1917 paper, it was just to make three-sphere space static, because at that time it was generally believed that there's no way of having a dynamic space which is moving or which is expanding or contracting or anything. So that once we make such trimming within a limited framework, same is true for quantum mechanics. It's trimmed to perfection in many senses, although we all know that understanding what it means in reality may be much more difficult. But when we are dreaming about unified theories, then perhaps it's better first to start with dreaming of a unified reality, where the reality works in the same way in different branches of physics. And for example, such basis of relativity theory as the principle of relativity, or relativity principle, it authorizes anyone to consider his state as a state of rest. Or if we consider 3 or 4 people looking one event, and these 4 or 3 people have different relative velocities to the event they are looking, they each interpreted the event different. Because let's say the speed of time or speed of clock in the event is different to the relative velocity to the observer. It doesn't work that way. So it doesn't let the opportunity of having unified reality. And before going to developing a unified theory, it's better to start with unified reality. That's my message.
Okay. I mean, in a sense, this is just to repeat things, but perhaps let me make it a bit more vivid. So, you know, during the 90s and the 2000s, there were, I think, two substantial theoretical physics, computational physics research teams who were trying to work out what would actually happen if two rotating black holes collided and what the pattern of gravity waves that would come out of those would be, according to the general theory of relativity. It's not a problem you can solve analytically on paper. You can get an approximation for what it looks like, but it's what people call a strong field regime of the problem. It's got no simple structural solution. This is a fantastically difficult mathematical computational task. It took a couple of decades to get the hang of doing it. It delivered a prediction that there would be a pattern, that you'd see a certain extremely specific pattern in the gravitational radiation emitted from black holes. Gravitational radiation that no one had ever seen at the time these calculations were being done. In parallel, other teams of people over several decades were gradually getting the hang of cooling down extremely large, carefully protected interferometers, things that interfere light to measure very, very precise patterns of vibration. They were doing this in 20-kilometer long tubes. They were having to isolate the frameworks of vibration so much that their computer models to handle it had to include keeping track of the vibrations of cars on the freeway outside the system. And they were doing it in places coordinated from across the United States, so that you'd see what the vibration was here and what the vibration was here, so that if you were picking up some kind of signal, you could see where it was coming from, by which place vibrated first. There's not actually very much general relativity in anything they were doing. There's certainly no black holes in it. There's no particular talking that way. Eventually, we managed to get the damn calculation done. And eventually, we got the devices precise enough that we could actually pick up the pattern of vibration. And the computer simulation said, this is how much, this is the pattern, the chirp, if you like, the very specific signal that you get when two black holes collide 1 billion light years away. And the vibrating systems in the LIGO experiment vibrated like that chirp, exactly like that chirp. That's the empirical way physics works. You can't throw that kind of stuff away because you don't like it aesthetically.
Sorry? Okay. All right. Anybody?
I can comment on this last part. So actually, I already had this kind of comment, but now what David said really triggered this thought. So physics comes with 3 languages, right? That are mathematical or whatever it is. Even, for example, Silvia, in her speech, at some point you said, well, physics hinges on mathematics, and mathematics evolves as a language. So this, you were, if I have understood, you have traced back to this as one of the reasons why one could not. Yeah, indeed. Yes, indeed. As all languages, no? Even when we speak verbal language, this is in continuous evolution, depending on our experiences and depending on the concepts that we want to represent. And this evolution of the language brings to new knowledge and brings to new ways of approaching reality, individual, then when the language is shared, also collective, and so on and so forth. So is a mathematical language for physics, experiment, and imagination. So the success, the rigorous success of physics hinges on a very, very delicate balance among these three. It's like having, you know, in a governance, three powers, and everyone has to take care about the fact that the other doesn't not take advantage or take particular place. Okay, so if you are following your imagination, so you imagine that the explanation of a given phenomenon is really outside any present mainstream, I think that you should be able to pursue that kind of imagination using also mathematics and experiment. So the question simply becomes, how long shall I wait as a scientific community to, how long shall I give fundings to this for waiting, I mean, for this wonderful coincidence of imagination, math, and experiment. 20 years, that was your example with the gravitational waves. Yeah, indeed. So then the one question, so I have no answer to this question. I don't know whether someone has answers to this question. But then the question also becomes, in my opinion, is there a way of doing science that is capable of preserving this beauty? Because I find these three languages together, individual one of them, each of them, and they together, I find all this really a wonderful beauty. So everyone should be able to pursue their own imagination, but of course at some point for physics, shut up, I don't know, maybe not shut up, but calculate and also experiment. So how long shall we wait? I don't know. Is the time that, I mean, for having a unbelievable H index, so that you have to publish 100 papers in Nature, or you are no one? So this is another question. Is a question about how science and the science that has an impact works. So I think that is also a matter about the social rules of science that sooner or later I think we should consider.
Yeah, thank you very much. Okay, actually I would have a question for David, because I think if I understood correctly, you in this, when discussing about the underdetermination, you have mentioned quite often that some of the other interpretations like GRW or the pilot wave, or, you know, the bone theory, that they haven't been, there are not that many areas where they've been applied. But could one, as compared to the so-called standard, you know, quantum mechanics, but could one make there this kind of historical contingency argument, like what Jim Cushing used to say, that like in, you know, suppose that in 1927 people, for whatever reason, they felt the pilot, let's go with de Broglie, and from, you know, 100 years people had been working and applying the pilot wave all over the place, and then, you know, and then somehow, you know, so what we call the usual view would kind of come later, and, you know, people wouldn't have necessarily worked it out. So is there an element there that from, you know, is it kind of historically fair? So, because the idea here is that should scientific truth depend on which interpretation gets there first, so to speak, rather than another kind of comparison. So if we, you know, if we would give enough time for these other interpretations and apply them, do you think the situation might change, or do you see there some more fundamental difficulties over there?
Yeah. slightly diffident that I'm hogging the panel here, so since you asked me. Yeah, look, I mean, there's always a concern of this kind, isn't there? I mean, there's always a question of, okay, how much is it the case that the path less travelled could have been travelled perfectly happily and successfully? Bear in mind, it's an extremely general thing. I mean, you know, the people developing, you know, these similar conversations come up legitimately enough in some of the Mond conversations. They've come up with alternative cosmologies. They've come up with, you know, should people have spent longer on Descartes' vortex theory back in the 17th century? And couldn't the vortex theory have been just as successful? We think probably not in that case. So then we have to start saying, like, what are the places in which you can say that science rationally went in one direction, and what are the places where it didn't? And I don't think there are general answers to give to that, but I'll say sort of two things why I'm not too concerned here. One's quite specific and one's very philosophical. I mean, the specific thing is that I think sort of speaks to the sorts of things I was saying in my talk, that there are features of the way quantum field theory works and relativistic quantum mechanics works that are quite inimical to some of the deep ideas underlying hidden variable theories and collapse theories, basically to do with the layers of indirection between the microphysical and the macroscopic, something which has been very successful as an idea. And I think it's worth remembering here that while it's true that you know, de Broglie came up with these ideas, this is Cushin's point, de Broglie came up with these ideas in the dawn of quantum mechanics, and that was the path not taken. But it's also true, of course, Bohm came back around to these ideas in the early 50s, much later. And while it doesn't get discussed very much these days, Bohm came up with these ideas at a point at which quantum field theory was in the doldrums, at a point where quantum electrodynamics had been profoundly successful calculationally, but nobody understood conceptually how to think about the sort of paradoxical infinities that physicists only really found their way to something they were happy with 20 years later. And calculationally and practically, trying to apply that theory to nuclear interactions was proving extremely unsuccessful. So you have a period where quantum field theory is really falling out of fashion, and the whole sort of S-matrix framework is coming in as like a calculation alternative. And so Bohm says in his paper that while his theory is empirically equivalent to non-relativistic quantum mechanics, he thinks that's a defect, and he hopes that we'll be able to develop it to something that will genuinely be predictive in that domain. But of course it didn't so develop. He was unable to develop that, others didn't. That did not in fact prove at all fruitful as a heuristic to develop beyond that. And in due course we worked out how to do quantum field theory after some very substantial effort in that space, and we moved on. So I kind of think the details of the science are relatively reassuring here. But here's the philosophical point from a different perspective. Suppose they weren't. I mean, if scientific progress is just historical contingency, I think the right conclusion isn't that we should start taking minority scientific positions more seriously. It's that we should all become Bas van Frassen and adopt some kind of instrumentalism or operationalism or empiricism about science. Because if it's the key argument that gets made for why we should think that our scientific theories get at the truth is that their predictive and explanatory and empirical successes are so impressive as to make it miraculous for them to be successful without being largely on the route of the truth. If it's just a matter of historical contingency and we could just as easily have got to an utterly different theory if the chips had fallen differently, then that tells us that those no miracle inference the best explanation type arguments for scientific realism aren't any good. They can't be trusted at all. And if that's true, then we shouldn't start arguing about which interpretation of quantum mechanics is correct. We should just for various reasons, I don't think this is viable, but we should, if those things were true, we should be looking for a much more kind of hands-off, empiricist, reproduce the observable data, don't worry about the deep metaphysics way of thinking about science in general.
Thank you.
Yep, quick comments. As somebody based in a physics department, I've noticed actually quite a sea change in the last 10 years over this area of, if you like, foundations of quantum mechanics. 10 years ago, when string theory was absolutely in the ascendant, foundations was considered, the fringe of the fringe. I mean, nobody in a physics department would, you wouldn't hardly admit to it because it was considered so completely off the chart. But it's the failure to find supersymmetric particles at CERN has really, and I kind of sense this in the coffee room, it has changed people's minds about fundamental questions of, is quantum field theory actually the right tool to be using? Going back to very fundamental questions. You're not considered such a nutcase today as you would have been 10 years ago to ask these questions. So I think in a way this is a good time to be engaged in these areas because people finally are a little bit more open. The failure of string theory really has opened up possibilities.
Yeah, maybe on that note. Oh, yeah, I can take that. Yeah, so maybe on this note also, I was brought up as a particle physicist and looking for the theory of everything and having a deterministic view as an ultimate sort of ideal to try to strive at. I have been looking at that, at theories of consciousness, and I've been doing that during COVID, and to make a very long story short, I entertained the thought that that physics, in principle, if physics is our theory, is the activity of having a theory of our understanding of the world, and if nature is the thing that we need to try to understand, that maybe there is a fundamental limit of what physics can describe. In other words, that there is a fundamental limit to what we can scientifically, mathematically describe. So in that view, if that is the case, so I think what we can, with our senses and with our apparatus, with our technology, it's quite presumptuous to say we can explain everything. And I have always found it quite stifling, that thought, to have a theory of everything. And understanding everything is also implicitly taken to have a deterministic understanding of everything, because if there's some indeterminism left, it is often equated with a lack of understanding. The famous word of Einstein, God doesn't play dice, right? So, but if you entertain the possibility that maybe what we can describe with our physical theories will fundamentally always be just a subset of everything that is there, then whatever we describe here, this system, will be surrounded by an environment, by what we can call an environment, something that we fundamentally cannot describe because it's too big. And that means that that there is influences of the environment on what we can describe, and these influences, by construction, are not under our control, and we cannot say anything about it. A very famous example is, of course, thermodynamics, and we're quite happy to talk about temperature, and temperature is just a number which is assigned to randomness that comes from the environment. It's a summary of our unknown, everything we do not know. And we're quite happy with that, and it's quite successful. We can explain magnetism, phase transitions, and all these kind of things. So in that thermodynamic theory, we're quite happy with indeterminism as embracing it and admitting that that is how we should describe these kind of systems. When it comes to quantum mechanics, we don't want to do that. There are these dynamic collapse theories that I was talking about on Monday that quite explicitly show how the undeterminism and the ignorance of the environment that we cannot model have an impact on the collapse and actually explain very well how these collapses occur. So to conclude, so maybe God doesn't play dice. Indeed, if God represents the whole universe, doesn't play dice, but maybe we are forced to play dice.
This conference, you hear this? This conference is about physics and reality, which are indeed two different things. Physics is a representation of the reality. It's not the reality. This is a trivial thing for philosophers, I think everybody knows. In a Kantian style, we can say that many concepts of physics are just in our mind. Space and time, even mathematics is not the reality. It's that how we represent the reality. What we have are models. In physics, we have a hypothesis. In this discussion that we are now, that which model, which theory is closer to reality, of course, there are methods to know what is a good theory or not. And also philosophers has much to say. Here in this conference, I think we are dominated by some tradition, I would say analytical tradition of philosophy, Anglo-Saxon tradition, that pays a lot of attention to the methodology of science and whether some experiments agree with some theory and falsifiability and all these things. But this philosophy is more than that, I would say. Philosophy is also about the human factor, and science, we should not forget, it has a human factor because it's made by scientists. And this is something that, for instance, continental philosophy pays more attention. Here we have not been speaking about psychoanalysis, for instance, or Marxist theory, or a critical theory of Frankfurt School, or other points of view that can say different things about science. One important thing to have in mind when claiming, of course, this theory is better because it fits better the data. Yes, but take into account one thing. How many people have been working in this theory? Possibly thousands of people. If we compare with another theory with only 2 or 3 people working, it's not competitive enough. So there is one factor, human factor, which is important in comparing theories. It's not just that you have a plot with 3 points and you fit your theory. You have to take into account that this theory is made by humans. There are factors, and this factor has one name. It's money. Money is the important thing for especially for the most speculative areas in physics, in order to get a successful theory. It's not a question of knowing which is the reality. Physics has not the reality. Physics has a representation of the reality, although some theories work better or not. But in order to be fair, in a comparison of different theories, we have to take into account the human factor. Money makes a big difference. Money, mass media, which is the same because those who have money have the control of the mass media. Just using some metaphor or some different case, I think in the words of the philosopher Baudrillard, a French philosopher, sometimes what we reach is not the reality. We have a hyper-reality representation. It's like when we see the television news in the mass media. We now see the news about the war of Ukraine or the Palestine, and everybody has an impression of what is happening there, but we are not there. We have just the impression that the mass media are interested to transmit, and those who control this mass media are those who gain the higher number of people. With physics, although it's not the same, it's also, in some sense, also contaminated by the same habits. Physics is a business. We should not forget that. There is a lot of money, a lot of interest, millions and thousands of millions of dollars invested in some lines of research. And of course, they have this investment has some impact in society. In the end, we have the illusion that some theories represent the reality and other theories are fake theories, or they are not representative of but this is not very philosophical, I would say. It is, one should be more open and one should investigate better in sociological aspects of what is behind not only a theory, but also a representation of everything. I'm not talking about not only general relativity, but we should talk about cosmology, the standard model of particle physics, whatever. It's a human construction, and the fact that we have a lot of support in this human construction is mainly due to the huge amount of manpower and a lot of investment in some direction. Of course, nature is there. I'm not claiming a postmodern relativist that everything is valid. Not all scientific theories are valid, but the human factor is important. We should not forget about that. So this, I wanted to...
Anybody?
I don't want to stand up. Oh, okay.
Yeah, it's better. I think sit down and then you be better with your...
Yeah, I just wanted to say something briefly because people are kind of asking me, well, what's the way forward? Where should we be looking? So I'm thinking about this, and I'm thinking about kind of drawing more connections from different areas. So different branches of physics, different branches of science, to try and get something more unified, I think is a way forward. The more different connections we can get from across these different fields, yeah, you don't want a theory of everything, but I think we should be looking this way to kind of branch out. And we're talking about these different connections yesterday a bit as well, between the condensed matter physics and string theory. It's very, yeah, to just grasp more of reality, I think is a way forward. But of course, experiments, we need to talk more about the empirical stuff as well, this theoretical connection, funny enough. And I think the other point I just wanted to briefly make is talking about the limits of our theories. In a way, they only get revealed once we have these new theories, right? So we're talking about the recovery, but it's never a perfect recovery. It's always modifying the old theory a bit, showing where it's wrong. So it's not that we just recover the whole theory in full, where we knew it was successful. It's that very act that shows exactly where the limits of the theory was, and in what sense it is just an approximation. So that's all I wanted to say.
Actually, just super quick thought to Karen before I make the main comment I was going to make. I mean, I think that's absolutely right. Although I think effective field theory changes the game a little bit because there's a sense in which our theories have already fessed up to the area where we don't expect them to work. I mean, with luck, you might find that actually they also fail in a place we didn't expect them to fail, and then we can test, and that would be great. But there's a degree in which there's already a sort of built-in humility in contemporary QFT that wasn't true. Not for reasons the physicists became any more humble, because that obviously was not true, but that just was structurally not true in earlier theories. I just wanted to come back to Martin's comment, because again, it's repeating this point about, like, well, of course, if thousands of people are working on research program 1 and only a tiny number of people working on research program 2, of course research program 1's done better. And look, that can definitely happen sometimes, and it's a perfectly legitimate thing to explore. But we do need to keep track of the cause and effect as well, and to some extent it can be question-begging to say, well, you know, the reason why this program has worked so well is because thousands of people working on it, rather than the reason thousands of people working on the program is because it's working so well. I mean, if I said, suppose I said to you now, well, I'm developing a new theory of physics. In my new theory of physics, the inverse square law does not govern the electric or the gravitational interaction, even at Newtonian scales, and matter isn't made of atoms. And you say to me, well, look at the incredible empirical success of theories that assume the inverse square law and that matter's made of atoms. And I say, sure, but that's what's been done by tens of thousands of scientists working for hundreds of years, and there's just me. So of course I need to catch up a bit. That's missing the point there. There has to be some space to recognise that we can't automatically go from more people work in this program to that's the reason why this program has been so successful.
Correct, but you give me any crazy idea in physics. You allow me a lot of, to give me a lot of money, a lot of people, and I can modify the theory ad hoc permanently, and I can construct any competitive theory with anyone. I have seen it many times. It's a question of adding more resources, even a crazy idea. It does not work. Anyway, we have a new free parameter, we will modify this, and in the end, it's a question of how much patience you have to modify the theory ad hoc, and you will get whatever you want.
Right, but there is a difference between ad hoc modification and other modifications. There's nothing ad hoc about the way general relativity explains black hole collisions. There aren't a lot of free parameters. You have thousands of data points, and you don't have any parameter to adjust other than n and j. I mean, yes, you can do ad hoc stuff, but we have to, when you do astrophysics, you know this, parameter modeling is important here. One can debate whether any given thing is ad hoc, but we can do judgment on ad hoc modifications, and we can say, look, this thing works without being ad hoc.
Locally, general relativity, yes, can be tested here, but if you say general relativity is valid for the whole universe, maybe you have to any element.
Sure, there's more room to say that, but I want to object to the idea that you can come up with a scientifically reasonable theory of any phenomenon you like, just by having money. If I can give you as much money as you like, and you will not come up with a theory to predict the magnetic moment of the electron to 10 decimal places, that isn't either quantum electrodynamics in some reformulation, or something that reduces to quantum electrodynamics, or something that bakes the answer in advance.
Anybody else? Sorry? Yeah, we open it up, but just if we are finished here, then we can have questions from the audience. So, okay, so let's see. It's over there first, and then over there. So, on the left.
So thanks. So I would like to say something related to the debate between Professor Wallace and Professor Lopez. And I think maybe there is some misunderstanding here on one point. That is, we do not always talk about, let's say, exact, precise results of a theory. And we're not, I think even Professor Lopez was not saying that you have a competing theory which is giving a different result to exactly the precise answer, exactly the same precise question as the other theory. The point is, how do you build the theories in such a way that you, let's say, you define what are the interesting questions, what are the interesting parameters, what are the interesting answers. And that is a very good example in quantum physics, right? So at a certain point, physicists decided that the measurement problem was not a problem of the theory. But if you have a different philosophical view of physics, then you interpret the measurement problem in a, let's say, maybe in a materialistic way as something important, which is not addressed by the standard Copenhagen interpretation. So I think maybe in this sense, the historical development of the theories can be interpreted. And this is just an example. There are many others, but it's not just about giving one single Popperian result of an experiment. Thanks.
To the boundary of our knowledge, I think that it's even worse, because all the time there are some limits, but I suppose all the limits could be overcome because of, for instance, Popper falsification. But on the other hand, there could be potentially infinity of limits. And because this is the logical problem. When we have, I don't know, atom composed of neutrons, electrons, and further, and question is, quark is composed of or superstring or space-time atom, it will not be probably so stupid that parts compose the whole, but all the time there is a logical problem. We must go further and further. Then in metaphor, we will know probably exactly 0% of, I would not say reality, because reality is model of the world. This is, I would say, a logical conclusion.
So if somebody wants to comment, please use the mic here. Ready? I'll go ahead.
Well, okay. I mean, just picking up on the comment earlier. I mean, sure. I don't want to say you can't take the measurement problem seriously. I take the measurement problem seriously. But the point is, you can't. You can say that there were problems that physicists weren't caring about and should, and that's fine. You can even say there are problems, that there's something fundamentally bad about the way physics is modelling and thinking of the world, and it's too abstract and mathematical, and it needs to come down to being more clear about an ontology or something. That's fine as well. Those are defensible things to think. What I want to insist on is that we don't lose a grip of the fact that the success criteria eventually has to be conformity to the data. I'm sure you don't disagree with that. I think it's important. We don't want to be in a situation of saying, well, okay, what physicists care about is getting the answers right to calculations and experiments. But that's just one take on things. The beginning of the scientific revolution is the idea that fundamentally what scientific theories are in the business of doing is making quantified predictions about the world. That's the point where. Where we go from just warring speculations about the structure of the solar system to Newton actually making a calculational model of it. So I don't take us to be disagreeing about that, but there's a kind of trap one can fall into where one says, okay, these people care about correctly predicting the results of experiments, and these people care about getting the metaphysics right, and those are just different value systems. We don't want to be there.
Yes. Thank you for an interesting discussion. This question, I guess, is mainly directed at David, but others might also comment. And that is, what is the space for doing philosophy of physics at this point? Because we have come to a point where physics itself has become a highly specialized field. Philosophy has become a highly specialized field. And in order to, at least I feel, to actually say something substantive about a lot of the theories we have, do require a quite heavy technical knowledge and competency in the physics itself, which might not be possible given a single philosophy career. So should then philosophers of science move away from maybe addressing a lot of these metaphysical sides of questions and move towards the more methodology side and talking about, well, what do we want of our physical theories and what are the spaces? So, as someone trying to find a way in philosophy of physics, this is something that bothers me quite a lot to find that space. Thank you.
So I'm not sure I exactly answered the question, but I just give you my own experience. I started going many years ago to the philosophy of physics seminars in Oxford, not because I was, to be perfectly frank, not because I was the slightest bit interested in philosophy. And to be honest, today, I don't know my Kant from my Hume or anybody else, and I get completely bamboozled by a lot of the jargon that you philosophers use. But I did it because these sorts of questions were not being discussed in physics departments, and I thought these were important questions. And I would just endorse then the comment that, and as I say, I kind of sense, because of the fact that people now are people in physics departments are starting to think beyond string theory, that perhaps this is a good time to, well, philosophy of physics kind of says it. It should be interdisciplinary. And to try, I don't know how it works, Paavo, in Helsinki, but I think we've got to try and make it more interdisciplinary. So it really is a meeting ground where physicists feel they can learn something useful and philosophers can, and we try to avoid our own bits of jargon and discuss things. So I think there's a great opportunity we talked about interdisciplinary. I mean, I think this is an area where we could make some strides forward. But as I say, my own involvement was purely because the philosophy department in Oxford was the only place in Oxford where these kind of questions were being discussed, and that's what drove me to, I went to many of the seminars for that simple reason.
Well, I think that there's plenty of room for philosophers of physics given the current situation. Well, I mean, it's true that physically speaking, the departments of physics are not happy with the introduction of courses in philosophy of physics, even if they need sort of courses on introduction to scientific reasoning or things like that. But still, I have students in physics that come to my lectures in philosophy of physics at the philosophy department. So venues of collaboration could be found. I led several multidisciplinary projects. So this is the right way, I think, to proceed. So to interact with both physicists and philosophers, to let also philosophers and physicists interact. So build up multidisciplinary teams where there are people coming possibly from different backgrounds. So you might want to have in your group somebody that is very well versed in foundations of quantum mechanics, but also somebody that knows very well relativistic physics, especially cosmology and so on. So if you build up a group like that and you include serious philosophers and maybe also a historian of philosophy, it's always good to remember who we are. And then you will find out that of course, a naive scientific realism cannot be endorsed in a so straightforward manner nowadays. So there's plenty of room for the development of alternative views that both concern epistemology and ontology on the one hand. On the other hand, I give you an interesting question to work on. Are you a philosopher or a physicist? You're a philosopher. Okay, imagine that no matter what physicists say, so the expert in condensed matter physics will tell you that he works on the most important thing. The cosmologist will tell you that he works on the ultimate worldview, whatever, and that he has the real picture of how things work in the world. But in reality, for me, any physical theory is just a theory of measurement. That's it. Nothing special to it. So if you start reasoning this way, first you understand the role of mathematics, so why mathematics is so important. Second, you understand that any cosmological model is the result of a theory of computation. And since we're going towards a revolution in computation, there will be a new cosmology, and so on and so forth. So have fun with this.
Yeah, hello everybody. I want to thank Paavo and the other organizers for this conference, also just for my own behalf, because this has been a very, very interesting experience for myself. This is my first philosophy of physics conference I ever attended, and I have been very happy that I have understood more than I expected before, and there has been some real amazing moments. For instance, these very, very different ontological views that reality is what we observe, and then or making scientific experiments, and then Tuomas' view that if we want to have a unified theory, then we first have to need some unified conception of reality. And I think these are very, very different views. And actually, it's very many decades ago when I studied philosophy at the Department of Theoretical Philosophy here in Helsinki. And at that time, in philosophy, it was an important point to criticize the positivist view that observations form the basis of our knowledge, and the notion of theory-latedness of observation. That was the big thing then. And then, I don't know, why did this important understanding fail to reach the physicists? So this is my challenge for you to think about. And because if you make an experiment, there's an awful lot of theory before you can make any simple experiment. So I want to thank all of you who have attended this, and I just enjoy this real lovely atmosphere in this discussion, because I had the feeling that people dare to be honest. And that's a very, very difficult thing in the academia. So I want to congratulate you for this honesty and the beauty of this honesty. Thank you.
I had a question for Professor De Bianchi, to just, if you wouldn't mind expanding a little more on what you were saying. I'm inclined to agree with you that posited ontologies and sort of contemporary metaphysics could benefit from striving to accord more closely with our physical theories. I mean, that's obviously something that many metaphysicians hold themselves to, but I don't think it's like successfully done. But you were saying something about how you could imagine different explanations or models of differences between existence or possibility contributing to the way that physicists perhaps, or philosophers of physics, think about, say, I think you gave the example of issues in quantum mechanics. I just wonder if you could expand on it a little.
Yeah, I can make you an example with regard to the fact that, I mean, the current debates on, for example, the debates on metaphysics, I mean, on dispositionalism, for example, and so on. Of course, they are readapted, let's say, in the modern scenario. But in the end, do point to old ideas, debates that involved the notion of substance and properties, or the debates on essences, and so on. Now, I think that we're in a position to produce a better ontology than that, of course. Now, the real issue is the methodology. So what does the philosopher do? Does a philosopher, I mean, a philosopher can be inspired by the science of her or his time, of course. This is really good. But at the same time, we do a different job. We're not physicists, and we're not mathematicians. So we're not entitled, so to speak, to import straightforwardly import notions from physics to philosophy, and we should maintain an autonomy, of course. But at the same time, our proposal cannot be completely detached from a sensible explanation of what there is. I had a PhD student who worked on, I mean, I really didn't know about that. I was shocked. So he was working on arguments. It's not you, Alvaro, don't worry. I was worried, oh my God. Another PhD. Who worked on arguments developed in metaphysics, in correct metaphysics, regarding the Kalam cosmological arguments and the beginning of the world, etc. So debates on cosmology and philosophical arguments. I mean, the arguments were like dating back to the first millennia after Christ. So I was shocked. So at this point, I think about all the development that we had in modern metaphysics, also in metaphysics, apart from Kant, but even after Kant, that marked, in a way, the difference between philosophy and theology and so on, and even there was a huge distinction between philosophy and physics. So it's good to keep autonomy, but at the same time, it's clear that philosophers should avoid, should decide to develop a metaphysics and an ontology that is not at all detached or that doesn't want to substitute itself to physics. And that's very important, I think. So as I said yesterday, we have the great privilege to take a step back. We don't have to say whether the universe has a beginning or not. We have the privilege to decide not to endorse a bouncing scenario rather than the Big Bang and so on. We are privileged with respect to physicists, and we have to take advantage of it. At the same time, I cannot talk about, okay, what there is, dispositions. Okay, apply this ontology to the current scenarios that we find in cosmology. So what this is referring to. How can I talk about the structure of the universe? So I'm not interested in the very particular galaxy X, but I'm interested in the way in which the universe works. These structures are connected eventually to each other. Are there filaments? So why is that? Is a matter that interests physicists, of course, and astrophysicists, but we philosophers should be able to account with an ontology for the fact that we have an understanding of the universe, and the universe is an important philosophical object that works apparently according to different laws at different scales, or there are some incongruences that our best scientific theories cannot explain yet, at least. But as a matter of fact, does it mean that natura facit saltus? So this is the problem philosophically. So is there a gap in the way in which the laws of nature work in our universe? Yes, no. Can we restate the problem in a different way by working on the idea that our scientific theories are limited, or that they are just theories of measurement, and so on and so forth? So, and then once we answer these questions, we can propose a suitable metaphysics or ontology or whatever, I think. But it comes first, this type of questions, this type of methodology. Sorry for being so long.
Thank you. Okay, we're coming to the final minutes. I thought I'd just say also something to this question about, what can philosophers do with this, physics? Should we do something else as physics is getting so difficult? I guess the question has, for me, been from the very beginning. I'm undergraduate. I studied both physics and philosophy, but then I went to philosophy of science. Even at the PhD stage, there was a bit of I might have a chance to go more like foundation of physics, but I was also interested in things like cognition and consciousness, and went more to that side of things. And of course, then it means that physics is more like just like a hobby, or like, something that you try to understand as much as you can, but of course, we don't, you have to be like David Wallace or some of the others, PhD physics, PhD philosophy, to do, in some ways, more serious work in the actual philosophy of physics area then. But then there are other questions. I think, for example, these issues of questions of consciousness, and which often connect with physics. And so we have, for example, at the moment, there's David Chalmers, Kelvin McQueen, who took up the idea of consciousness collapsing the wave function, and discussed that in the context of the IIT, which is this integrated information theory of consciousness, which has been mentioned. And I think probably a philosopher can perhaps understand the whole picture. I mean, one has to know some physics, but then the philosopher might be motivated to try to understand also what is this IIT theory and, does this thing work? So these are interesting examples. And another example is, it has been mentioned that Penrose and Haveroff proposed this or theory of consciousness, which has been there for 30 years. And of course, often people think, well, it's too off the wall or whatever. But some people are exploring it, like, for example, Hartmut Neven, who is the director of Google Quantum AI, and he's collaborating some people now, including Christoph Koch, who was mentioned. And just now in April in Tucson, he was describing this experimental setup where they have qubits connected to a brain organoid, like a mini brain, which stem cells. They look at whether you could have entanglement in the system, and then they will test anesthesia to see what happens there. I mean, this is just a sort of way of, they talk about a generalized Penrose. So they won't take it, the original theory, but something like that. Again, I think a philosophical understanding may be needed to fully appreciate all these different dimensions of this whole setup. Not at all saying this is correct, the truth, but I find this quite fascinating. And so in a way, I think it depends very much what you want to do. I mean, if you really want to do serious philosophy of physics, then you have to study the physics. That's what I try to tell my students as well. So that don't do what I've done, but go to school. But then if that's not your road, then there are still maybe exciting things to be done. But
just add something to that. And I think I agree with most of that. I'd want to say I don't want people to think that if you want to do technical work in philosophy of physics, then the only way to do that is to study physics all the way up to postdoctoral level. You definitely need to study the subject. You don't get to take shortcuts. And for most people, that tends to mean actually taking formal courses, not so much because that's the only way you learn the particular subject, but because there's a certain general kind of mathematical and scientific maturity that you need to be able to read and learn physics that's quite difficult to pick up in the first place without sort of formal training and feedback. But the amount that's necessary to work in a given area is not, as a philosopher, is not at the same level as what you need to publish cutting-edge calculational or experimental research in the same area. Because if you want to think that in a physics area there's going to be an understanding of some of the conceptual core, and then there'll be 100 different places that develops into the technical details. And getting the ability to know any one of those 100 things can be the work of years. But by that same reason, nobody in physics knows them anyway, either. The nature of specialization is it's not just true that nobody outside physics knows all of the details of some specialist bit of physics. It's that hardly anyone in physics knows either. It's not that unusual as a philosopher of physics who has spent substantial amounts of time learning technical things to actually know more about some particular bit of physics than a physicist you're talking about and have a good conversation. And it can also be that once you've got that kind of, a grad course or so level of training, not like 5 years work, but you've gone to a semester of courses, that tends to put you at the level where you know enough about the subject to have intelligent conversations with genuine experts. And often to collaborate, in fact. The first step in being able to do good collaborative and interdisciplinary work is usually to hit a kind of medium level of training, not to try to replicate or supplant the person in the other discipline, but to know enough to have a high-level engagement with them.
All right. So, thank you, everybody.
Hello. Welcome to the final session. We have 15-minute long talks, a lot to cover in this final period. The last 2 talks will be online, but we have an in-person talk, a series of in-person talks to start with. And first we have Margarida Hermida from King's College London. And you can use this mic.
Okay. Thank you. Thanks to everyone who stayed for the final session. bioenergetics is about how living things work. So all life, all living things require some mechanism to obtain free energy from the environment so they can power their activities. And on Earth, this mechanism involves chemiosmosis, which drives ATP synthesis. And this is based on a proton gradient across a membrane. So this is how Nick Lane explains how respiration works. So electrons are stripped from food and they're passed along a chain of carriers all the way to oxygen. And the energy released from these electron transfers is used to pump protons across a membrane. And the membrane is impermeable to protons, so a gradient is established. And the protons are only allowed to flow back through the ATP synthase, which works as a kind of like a turbine to drive the synthesis of ATP. So as you can see, electron transfer is involved in this process, and there's some speculation that it might even be a universal feature of life. So it's involved in both respiration and photosynthesis, with the main difference being that in respiration, the energy ultimately comes from chemical energy from food, whereas in photosynthesis, it comes from sunlight. So how does quantum tunneling come into this? So like I said, respiration involves the transfer of electrons across a chain of redox centers, which are these clusters of atoms that have high affinity for electrons. And electrons, being quantum particles, the way that they are transferred from these redox centers to the next is they jump through the process of quantum tunneling. And the distance between the redox centers is really crucial for this process, because electron tunneling only takes place at distances less than 14 angstrom. And in fact, the process is so sensitive that if you increase the distance by 1 angstrom, that decreases the rate of electron transfer tenfold. So as you can imagine, this means that the respiratory complexes had better be shaped just right so that these distances don't exceed that range, if respiration is going to carry on at a good rate to maintain life functions. And this is going to be a problem due to the symbiotic nature of the eukaryotic cell. So eukaryotes are basically all complex life on Earth is eukaryotic. It's animals, plants. And eukaryotes originated from an endosymbiotic partnership between an archaeon and a bacterium. Basically, one ate the other but didn't digest it. And the ancient bacterium evolved into what is now the mitochondria. So mitochondria are no longer separate organisms, but they still have their own DNA. And this is a little bit puzzling why they still have their own DNA, because actually most of their genes have been transferred to the nucleus over the course of evolution, and there are very good reasons for that. So firstly, it's more efficient, it allows the cell to have centralized control, and also having DNA right next to where respiration is taking place doesn't seem to be such a good idea due to free radicals of oxygen that can cause mutations. And yet, all eukaryotes that have oxygen respiration still have DNA in their mitochondria. So why is that? Well, the genes that remain in the mitochondria turn out to be critical genes for respiration. And the reason they need to be in the mitochondria is to control respiration locally. So, for example, to very quickly respond to changes in various parameters. So this is known as the core hypothesis, co-location for redox regulation. And basically what it means is that the genes need to be in the same compartment as the gene products to immediately be regulated. So basically the mitochondria can sort out their respiratory issues without having to consult with the nucleus. So they need DNA there. Okay, now the problem is that the result of this is going to be that some respiratory complex subunits are coded by mitochondrial DNA and some by nuclear genes. So this is the mitochondrial respiratory chain, and the subunits in red are coded by the mitochondria. And the subunits in green are coded by genes in the nucleus. And they have to, and then they get assembled and form the same respiratory complexes. So a very delicate balance needs to take place between the nuclear and the mitochondrial genomes for respiration to proceed smoothly. So this is at the heart of this new field of mitonuclear ecology, which hypothesizes that the need for co-adaptation between the mitochondrial and the nuclear genes is actually what drives many aspects of eukaryotic evolution, including especially sexual reproduction with recombination, the maintenance of two sexes, and some other cool features. So sexual reproduction is unique to eukaryotes. Bacteria do exchange genes, but they don't have anything like sexual reproduction. And the main advantage of sexual reproduction is recombination. So that's when our chromosomes line up and physically exchange bits with each other. And what that does is it separates linked genes so that they can become visible to natural selection, so that bad genes can be eliminated and good ones favored. Whereas if they're all linked, it's really hard for natural selection to select them. Now, one problem is that mitochondrial DNA tends to mutate faster than nuclear DNA, and it doesn't have recombination. So it tends to accumulate mutations over time, and that can be very detrimental. So in consequence, the nuclear genes have to compensate for that by evolving some, well, I could explain more about that. And sex is thought to be one way that the nuclear genome keeps up with the mitochondrial mutational erosion by having this recombination thing. But then, even given sexual reproduction, why specifically have two sexes or mating types? It doesn't seem very advantageous because it excludes half the population as potential mates compared to just, everything being compatible with everything else. But it's the only system that allows for mitochondria to be transmitted only by one parent. And what that does is it generates a clonal population of mitochondria within the organism, rather than having diversity of mitochondria within the individual, which would lead to natural selection occurring within the organism, which would be highly detrimental for the organism. There's also some evidence that mitonuclear co-adaptation is involved in the evolution of some features of mate choice, but I'm going to maybe skip this in the interest of time. Okay, so what does this tell us about the relationship between physics and biology and the role and the importance of scale for scientific explanation? So one thing it obviously tells us is that physical and biological aspects are really intertwined in the explanation of biological processes. But I don't think that is particularly surprising. It just reflects the physical nature of living systems. So that's pretty much what we should expect. But a lot of philosophers of biology tend to think that even if physics is important for biology, quantum physics is probably not, because living things are quite large. And I think that there's something in that. So probably most of the time, for most biological processes, quantum processes can be safely ignored. And other areas of physics might be more important. Thank you. So physical laws more prevalent at those scales are going to be more relevant. But we should not presume to decide a priori which scales are going to turn out to be most relevant for the explanation of a particular phenomenon. Now, there's this idea in philosophy of biology that explanations in biology bottom out at the molecular level. But in fact, there can be explanations in biology both above and below the molecular scale, at various scales, in fact. And in this particular case that I've been discussing, because cells obtain free energy from these bioenergetic processes that involve electron transfer. They can't afford to miss out on the quantum processes that allow this energy transfer to obtain, in this case, the process of quantum tunneling. And in the case of the eukaryotic cell and the eukaryotic organisms, which are most organisms that are not bacteria, since maintaining the conditions for this quantum tunneling in respiration requires co-adaptation between the nucleus and the mitochondria, then the biological consequences of this physical phenomenon reach very far indeed. Thank you.
Excellent. We have some time for some questions.
Hi. I just wonder, this might be an overgeneralization, so I just want to ask your opinion of it. Would you say that biology uses quantum processes if it's more energetically efficient than than doing it with classical means? When you look at things like tunneling and so on, or processes that involve tunneling, does the amount of energy used to achieve a certain purpose, is that less than would have been used if that same effect had been somehow done in a classical sense? Is that true generalization or not?
Yeah, so is it okay if I don't use a... this one. Oh, okay, cool. So electron transfer seems to be a very efficient process, and that's what all life on Earth uses to obtain energy in these bioenergetic organelles or directly through their cell membranes in the case of bacteria. The really cool thing about it is that it allows the cell to obtain tiny bits of energy that add up, which wouldn't be possible, for example, in a chemical reaction that would have to obey stereochemical constraints. So each tiny electron jump releases a tiny bit of energy, and the cell is somehow able to use all these little bits of energy to pump the protons and produce the proton gradient, and then enough of those are sufficient to produce one molecule of ATP. So yeah, it's extremely efficient.
Okay, one other question here.
Think about the evolutionary history of the intermediates in the evolution's discovery of the use of tunneling in these electron transfer processes. Like chemically, what were the intermediates that were that led to this discovery by evolution?
So we're not sure about how it came about, but it's quite ancient, and it might be as ancient as pretty much the origin of life itself, except that at the beginning you had to have some gradients that were already there in the environment, and those might be, according to the currently most popular hypothesis, produced in what's that called? Hydrothermal vents, yeah. And there is there's some indication that it is that old, because some of those clusters of atoms, iron sulfur clusters that are assumed to date from that hydrothermal vent environment.
Okay, that's all we have time for question-wise. Let's thank Margarida again. Now we have Alessandra Pulga from the University of Groningen.
Yeah.
Great, excellent.
Thank you. Thank you very much for being here to my talk. And I will be talking about a framework for free will within a quantum universe. So this is my table of content. My presentation will be very philosophical, so I just wanted to say, making this disclaimer. In the first section, I will talk about free will and reductionist theories of consciousness and the possible problems that arise out of it, and how, in the second section, I will be talking about how it had been used. It had been thought to use quantum mechanics for trying to solve certain aspects. And in the third and in the fourth section, I will be talking about my point of view, which is trying to rethink the quantum brain theory through the many words interpretation. And I think that this approach can be very hospitable for free will and a good way to approach it. So first of all, what's going on in the debate on free will? So we can either think that the universe is indeterministic, so we can think that the physical constraints are loose enough that we can actually take free decisions, and we actually have a say in what is happening in the world. Or we can think that the universe is deterministic, and if we are taking the hard determinism in place, well, everything that happens in this world is actually already in place because of the physical constraints, and also what Tim was saying before. We have like some pre-done settings, and we just follow it. There is also another approach that says that determinism and free will are not incompatible definition with each other. So what's going on in particular in this compatibilist approach? So we have basically two ways to approach the problem. Either we think that the will is a kind of it acts like a stimula for certain areas of the brain, and so, for example, I activate and I raise my hand because something like a will activated the area of my brain which makes me raise my hand, but this will is not including in the physical framework itself. Or I can say my physical constraints are so complicated and so I have to consider so many variables that I cannot compute all of them, and therefore I am indeterminate because of uncomputability. So either I go with the first solution, which is very dualist in a way, saying, well, this will, we don't know exactly where does it come from, or I choose uncomputability. But in the case of uncomputability, saying that I don't know what constrains my action doesn't mean that my action are not constraints, are not like already decided in a way. So in this sense, it's more an epistemological problem than an actually ontological free will. So, well, why quantum mechanics comes in place? Well, quantum indeterminism, as we saw also in the Liljenström, Professor Liljenström talk, well, quantum indeterminism had been thought to be relevant for free will, and in particular, Hameroff and Penrose in their quantum brain theories say, well, these quantum systems in the brain can be relevant because free will can also be understood as incomputability. The quantum approach has the advantage that it's not just an incomputability given by an epistemological problem, but it's actually that this incomputability is actually given by an intrinsic stochasticity of how the collapse happens. However, putting in place in our decision-making process, in our brain, this incomputability given by the quantum systems doesn't make our actions free. It just makes our action stochastic. So it's not that the physical constraints are loose enough for us to actually decide freely what to do. It's just that everything is still determined, but by something that we really cannot understand and not even predict. So, should we give up about having free will in a quantum framework? Well, I think we still have a possibility. And this possibility in particular is given by many words interpretation. Why I think so? Because I think it can allow the principle of alternative possibility. So a stronger definition of free will than just saying, well, free will is uncomputability. So how to do that? I think that the most important notion that I'm using here is identity through multiple words. So when we take into consideration, when the branching happens between many realities, so we know that, like in many words, we have a branching of reality for every possible outcome of the measurement. So the fact that basically so like the fact that this branches in this way, like as long as it follows the wave function, it basically is the same system, even it gave different outcomes. And in this sense, like the person that, like myself, me, Alessandra here, and the Alessandra in another branches of reality is still Alessandra. So if my brain is a quantum brain and I take decisions based on a quantum system, like I take a decision that leads me to this reality, and like another version of myself will take a decision that leads to another reality, but we're still talking about the same quantum system, therefore about the same person. So if the possibility of making otherwise was always open in the moment of the branching, this means that the possibility of alternative possibilities is guaranteed, the principle of alternative possibilities is guaranteed, and therefore I have a stronger definition of free will. So, in the last part of my talk, I will be talking about how can we avoid dualism completely, or at least I will try to avoid dualism completely. So, well, what is this will? Where is the limit of my branches? As I said, in compatibilist theories, we have this will that basically in some way it's not in the physical system itself, but why do I want something and I don't want something else? So I think that this limit of the branches I can have is given by the coherence in the environment and the interaction that we can have with the environment. So let's consider this example. So if my brain is a quantum brain and my decision-making process is based on quantum processes, this morning I could have taken the decision if drinking tea or drinking coffee, and this decision would have been based on quantum systems. So I decided for coffee, and another version of myself, which is in another reality, decided for tea. If we imagine this decision, taken through quantum brain, basically, we have a split into different realities. And the habitude for me to drink these two beverages, and also the availability of them in my house, or also the possibility to not drink anything in a way, like all these possible branches are given by the availability I have in the world, like also my previous experience with the world itself, in basically a constant interaction with the environment. There are also some factors I also can be unaware of in a way. So the branches are not infinite, but they are given by the limit that the world gives to us. And in this way, we do not really need to have any kind of dualistic will that basically acts upon our brain for having also a limit for this branching and an explanation of what the will makes us doing. So, for concluding, I think that my view is, it has some advantages. For example, it maintains the principle of alternative possibility, so it's a stronger definition of free will than just incomputability. It guarantees that the brain can self-determine, because the brain is the actual quantum system which which decides where to branch, basically, which reality to choose in a way. And interpreting the quantum brain through the many words interpretation, I think, can also avoid the problem of like the dualism, because like with the constant interaction with the environment and with the loss of quantum coherence in the environment, we can have that, this gives us a limit of the branching, more than one possibility, and having more than one possibility guarantees free will in a way. Okay, thank you very much.
Very good. We have more than 5 minutes for questions. So I see one here. Did I see one back there? No? I see one here. Okay.
Sir.
Oh, he's saying. All right. Please go ahead. If you could use this mic.
Oh, yeah.
Hi, thanks for the talk. I may have misunderstood, but as you've expressed it there, that all of the versions of me are equally me on every branch. To me, it sounds like what's actually happened is that you, on that sort of language, have chosen every option, and so that doesn't feel like free will. That feels like just max, choosing every option doesn't feel like free will, if you see what I mean. To have free will, you'd have to be identical to just one branch. There's some continuity before branching with you and just one branch you.
Okay. I have to make an important clarification here. Let's say that free will, in the way I mean it here, is like all of us in every single branches can have chosen this decision that took like this version of myself here, for example, in a free way. But of course, if we look at the theory, also many words theory, as if we're God and we have like the view of all the branches together, well, the theory is actually still deterministic, so everything happens 100% of the times. It is just like every version of us will have chosen this decision that lead to this branch in a free way. So,
yeah. Thank you for an interesting talk. I was just curious, when you have, let's say that you come to a branch and you choose one of the possibilities, but you said yourself some of them are more probable than others when you actually calculate it. And let's say that you have a certain distribution that you actually calculate. You're saying above and beyond that, there is something extra that could somehow change these numbers a little bit, which would make it falsifiable scientifically, meaning that you could perhaps design an experiment a bit like in the way that's collapse of the wave function, conscious collapse of the brain wave functions can actually maybe produce small differences that could actually be measured if the differences are big enough energetically. So I just wonder if you think that it's a falsifiable theory in that sense.
Yeah, so like the fact that there can be like one possible outcome that is more probable than the others, this is what the question, like, yeah, like.
But I'm saying that once you calculate all the probabilities of all the branches, what you're saying is that we're going to get maybe slightly different numbers because of free will, which is somehow above and beyond the ordinary probabilities that I'll just calculate from a scenario without any free will. So that you could actually maybe design an experiment to test your hypothesis. Okay, so
like the fact that the fact that like probability can say to me that I might choose like, let's say one probable branch towards another, and this is like testable through like probability. And so, well, I do not think this falsifies completely because, well, the way all of us acts in a way, like we still take our free actions, but we do have like one preferred way to go. Like, so the fact that like we do have preferred actions to over others is not really a problem, let's say, for how I thought to structure this this model.
Okay, so we have 2 minutes left, David, and then if there's time,
there's a quite popular take on the metaphysics of the many worlds theory where worlds and in due course people are identified with four-dimensional non-branching continuants so that prior to a branching event there's an overlap. So in other words, if I make a measurement which could have spin up or could have spin down as an answer, then there are two versions of me. They overlap prior to the measurement, they diverge afterwards. I'm not particularly defending that form of the metaphysics, but is that, if that's the right way to think about the metaphysics, would that be a problem for this view?
Well, I'm not totally sure. I might need to think more about this. Yeah, yeah.
Okay, then, well, Jen, I have a question in the back.
It's more of a comment, which is that it seems to me what this does, and which I'm quite supportive of, is less perhaps the question of whether we have free will or not, but it does seem to answer the question of why we all very viscerally feel as if we had free will, which is, which was made by the speaker before the tea break, which is that, if we have some kind of quantum processes going on in the brain, and we have some cognition of these parallel worlds, let's call them, we have then a visceral sense that we could have done otherwise, because those are the worlds, that we that we perceive in some sense. So it does seem to me it addresses the question of why everyone feels very strongly that they have free will. Whether or not we do or not seems to be still an open question.
Yeah, okay. No, in this, I did address the fact that we can feel free, but actually not being free. What I would like to point out here is that for us to be in this branch and for us to having taken the decision that takes us here, these decisions were actually free in a way that we did have alternatives. So what the example you were doing before, like without free will, like Hitler would not be responsible of killing 6 million Jews. This is actually, I think, like he did choose that because he had alternative in this model. And so yeah, if we would be God and looking all the branches all together, everything always happen. But we do have the possibility to decide in which branch to be, in a way.
Okay, we'll have to leave it there. Thank you very much, Alessandra. Next up, we have Sami Tayub from Bristol University. How van Frassen inadvertently showed that metaphysics can be tested. Lessons from Bell's theorem. Would you like to use this mic or one of these two desks? Okay, there you go. Thank you.
Hi. I've also provided a handout which kind of presents kind of a derivation which is quite central to this talk, but it might seem quite like shocking because people are going to object that how can you get an empirical prediction from a metaphysical theory and a conceivable phenomenon, and also from van Frassen no less. So I hope if you have those issues, you can look at the handout and that might help you out. So this talk is, sorry about the, what's that? It was meant to be a lot bigger, I don't know why, it's more. Yeah, so I mean, the main aim of this talk is kind of critique kind of van Frassen's kind of empiricism, which holds that we kind of only have epistemic warrant for the observable because we can observe it and so we can confirm whether it's true or false. But anything beyond that goes into the unobservable, so you have to use kind of contentious rules of inference, like inference-based explanation, which even some naturalists might disagree with, so like David, for instance, in the first day, seemed to kind of disagree with that. So what I argue is that van Frassen's empiricism kind of leads to this very skepticism, which he kind of sought to avoid in this kind of influential paper in 1982, which he kind of leveled against the empiricists. And it seems just as he's agnostic about the common cause, he's going to be agnostic about the empirical adequacy of quantum theory. And I suggest that if we want to escape this kind of skepticism and recover empirical adequacy, we can say that this metaphysic is false, which means we know something about the unobservable. And we can generalize to say empirically adequate metaphysics form an epistemic modal space of the way reality might be. So what is van Frassen's argument? So he argues that the realist only has reasonable expectations about the persistence of correlations because we have some understanding of the causal mechanism which produced those events. But van Frassen shows that because of the observed violations of Bell's inequalities, there are correlations which can't be modeled causally, so they have no reasonable expectations of what we do indeed observe, so that leads to skepticism. So you might ask, what do we mean by causation here? Van Frassen takes Reichenbach's common cause principle, which models the kind of statistical correlations of probabilistic events. So the famous one is rate of cigarette consumption at T and presence of lung cancer. So that's highly correlated, and that has a common cause, which is the smoking history of the patient. And the key kind of feature is that these two effects are factorizable. So someone might have a low probability of smoking at some point, but that smoked a lot in the past, so that explains the presence of lung cancer. So, so the derivation of Bell's inequality, so if you want more details, you can see the handout. But he imagines some conceivable phenomenon where you have two generals who wish to strike a common enemy simultaneously. And then it's kind of, so they have two kind of receivers, and they both receive a signal, and that's kind of an experiment. And then you imagine some perfect correlations, so both experiments have opposite results when they're on the same setting. So that's an analog to the EPR correlations. So he posits factorizability, locality, and no superdeterminism as his models. And they're all kind of metaphysical models, because, for instance, so no superdeterminism, that tells you something about the deterministic structure of the world. So we can say these are metaphysical theories, as Paul 2012 puts it. But from this phenomenon, from this model, from this theory and the conceivable phenomenon, we can derive Bell's inequalities. But it's well known that these inequalities have been observed to be violated. So you might recall, so what does this mean for the realists? So it shows that there's kind of these correlations which can't be modeled causally. So we have new reasonable expectations for these events. And for Van Frassen, if a position leads to skepticism, it's thereby refuted. So there's this positive conclusion that Van Frassen draws, which is that, that instead of focusing on causation, we should just focus on models, and whether models can embed phenomena. So the interesting thing is that these kind of, so he kind of goes further than this in his book in 1991, and he says that quantum theory cannot be extended by this common cause metaphysic. But what do you mean by extensions? So for Van Frassen, extensions are models of scientific theories which go beyond the empirical import of such scientific theories. So they provide extra structure which is capable of being mobilized when radically new phenomena come to light. And I argue this is precisely how Peter Godfrey Smith defines metaphysical models. That is, they're not guided by the desire for an exact fit to empirical data, but for the generation of some important class of behaviors. And Paul described metaphysical theory just as a scientific theory, which is just a class of models. And so these extensions of scientific theories can be metaphysical theories. So what I take this to show is that metaphysical theories can constitute scientific theories, and so they can even be tested by scientific theories, which obviously Van Frassen is going to deny, but you might accept that metaphysical theories can constitute scientific theories. So does Van Frassen actually believe that the common cause principle can extend quantum theory? Well, at the start of his chapter in 1991, he says that perfect correlations would need to be simultaneous. So these rely on kind of the theory of atomic physics to confirm that they are indeed simultaneous. So what that seems to say is that, the observed phenomena that we've kind of seen still allows for a common cause between these correlated events, but we've just not detected it yet. Meaning quantum theory could still be causally extended. But this is not what Van Frassen ultimately advises, even though that's what his empiricism would seem to demand, because he argues that we can't know anything beyond the observable, because we can't, how are we going to confirm it other than by inference best explanation. But despite this, he still argues that there just is no value for the hidden parameter which represents the common cause, such that there kind of is an extended model, extended causal model, which fits the phenomenon we've observed. So we do have a clear, and then he says this kind of astonishing quote, which is that we do have a clear verdict on how the old quantum theory, so that's a quantum theory that doesn't account for the observed violations, could be amended and developed into a new quantum theory, which could be empirically adequate. And the verdict is not, and that's Van Frassen's italics, not mine, the ball is me. And he says it's not such as to turn it into a quantum theory. Now, why is this so astonishing for Van Frassen to say? Because for Van Frassen, a theory is empirically adequate if what it says about the observable things and events in the world is true. So what this seems to show is that by Van Frassen denying that quantum theory can only be empirically adequate when it is not a quantum theory, the new quantum theory can only provide a true account of the observed violation when it is not causal theory, so that implies that causal theory is false. Now, Van Frassen in general will seem to want to deny that. He seems to want to be agnostic about anything beyond the observable. And if he was agnostic about the common cause here, then he would also have to be agnostic about the empirical adequacy of the new quantum theory. So the empiricist finds himself in the same position as the realist. That is, they too cannot provide reasonable explanation of the observed violations of Bell's inequalities. And if this amounted to skepticism in the realist case, then it clearly amounts to skepticism in the empiricist case too. So to avoid skepticism and attain empirical adequacy, I argue that we have to accept that this metaphysic of the common cause is false. And so you can draw this kind of general kind of result that a metaphysical theory is false if it is not empirically adequate, that is, if it cannot embed the experimental data, so metaphysics can be tested. Now you might ask yourself, wait, what happens when metaphysical theories are empirically adequate? And indeed, there are loads of ways that the common cause can be made to be empirically adequate. So they all seem to deny the factorizability constraint, so that the idea that we can factorize these two events of these two receivers. And instead, Chang and Cartwright posit non-locality, so we can have superluminal causes or gaps in space and time. Hofstede-Szabo, Rede, and Hofstede-Szabo water down the concept of the nature of the common cause altogether. So they say that there's not a single parameter which screens off all the correlations, but just a signal for each correlation that happens. And Hossenfelder and Palmer argued that we can have locality, but we have to accept superdeterminism instead. Now, because there's lots of ways that the common cause can be empirically adequate, they can't all then be true. But my supervisors at Bristol, so Tuomas, Tahko, and James Ladyman, they are going to say effectively they're all true by verifying them as objective possibilities. But I argue that presupposes scientific realism, so I kind of steer clear. But Van Frassen would be willing to accept that they are extensions. So you might ask yourself, what is an extension? And for Van Frassen, an extension informs us how reality might be were the theory extends true. But Van Frassen's agnostic about the truth of scientific theories. So these aren't going to be genuine possibilities, but merely pragmatic. But as we show, we have to rule out some of these metaphysics, otherwise get skepticism. So by ruling out these metaphysics, we are saying that it's false that reality could be this way. And even if we were suspicious about the truth of the scientific theories, we're ruling them out as false because of the empirical content of scientific theories, not because we're imagining what would happen if these theories were true. So these possibilities are conditional on what even Van Frassen admits we know, so the account of observables science provides. So that's just the definition of epistemic possibilities. So in general, empirically adequate metaphysics informs how reality might be relative to science's empirical content. So the conclusions I wish to draw are, if a metaphysical theory is not empirically adequate, then it is false. If a metaphysical theory is empirically adequate, then it is epistemically possible. And so, in general, according to my view, metaphysical theories are just like scientific theories in the sense that they can embed experimental data and be empirically adequate. And so this kind of has this kind of general point that empirical adequacy constrains the models our scientific theories consist of, and indeed metaphysical models. And because empirically adequate metaphysics are now possible relative to what science empirical content is, we have this prospect of kind of converging towards a single story about our world, because the empirical content of science can grow. So you might not wish to say goodbye to the metaphysics as Van Frassen wished. That's pretty much it.
Fantastic. Yeah, I saw your hand oozing, and yeah. Okay, 3 minutes.
Thanks for a fascinating talk. I just want to mention a historical anecdote that you may find interesting. There's a paper, at least 20 years old, by Itamar Pitovsky, who wrote, it's a paper that George Boole wrote about the conditions of possible experience. So George Boole wrote this paper, Conditions of Possible Experience, which was expressed as a set of inequalities. And what Pitovsky showed that the violations of Bell's inequalities actually violated also Boole's inequalities, so that his metaphysical picture was falsified by. But it just, I think historically it's interesting.
Yeah, I think there's kind of general people generally accept that you can kind of converge and kind of the way reality might be from the empirical content of science, and kind of even Van Frassen's going to have to be accepted, kind of commit to that kind of thing.
Other questions? Everybody's happy with their metaphysical theories. Okay, so thanks. Let's thank our speaker once again. And now I'd like to invite the next speaker down. We have Anton Svedlikov from the University of Wuppertal talking on event structural realism.
Yeah, hello everyone. My name is Anton Svedlikov. I'm from the University of Wuppertal. I got PhD in theoretical philosophy there. And the topic of my today's presentation is event structural realism. What is it going to be about? Let's take a look at the abstract. What I actually call event structural realism is a sort of empiricist reformulation of classic ontic structural realism that, as I will try to show, allows to address some of empiricist objections against classical ontic structural realism. That is, I will start with a brief introduction of ontic structural realism and of critics of it. Then I will move to the introduction of event ontology, and I will try to present my key argument that the integration of event ontology and ontic structural realism can help us to strengthen the ontic structural realism position. And then, if I will have time, I will present two case studies, the motion of free relativistic particles and the U1 gauge theory. And at the very end, if I will have time, I will like to say a few words about possible applications to QFT and cosmology. Okay, let's start. Before I start, this is still a work in progress. That is, all sort of critics are very welcome. Realism in contemporary philosophy. Well, actually, I would say that ontic structural realism can be seen as sort of answer to the critics of traditional metaphysical realism, that is object realism or realism about object-like or thing-like entities. This position is challenged both in theoretical philosophy and in the philosophy of science. Thus, in theoretical philosophy, the most realistic positions are rarely realistic about objects. Instead, it's much more common to explore alternative ontologies like process ontology, event ontology, trope ontology, and so on. And in the philosophy of science, I would say that traditional metaphysical realism is challenged both ontologically and epistemologically. The ontological challenge revolves around the theory change argument. To put it briefly, the key idea is that it is very hard to epistemologically justify our belief in theoretical entities, in our firm belief in the existence of theoretical entities, since our theory can change, and correspondingly, these entities can turn out not to exist. And the ontological challenge comes from more from a more detailed analysis of ontologies used in contemporary theoretical physics. Yeah, thank you. Thus, we could say that the most fundamental entities that are used in contemporary physics, like quantum fields or elementary particles, do not seem to fit into event-based ontologies. As a result, I would say that scientifically informed realism should move away from object-based ontologies, and at the same time should be capable to account for evolving nature of scientific theories. Okay, and ontic structural realism meets these two demands in a very general form. Ontic structural realism claims that we should be realist not about theoretical entities postulated by our scientific theories, but rather about structures described by our theories. That is, what is fundamentally real is structure and not the entities. There are two main forms in well, there are a lot of forms, but the main two forms are radical structural realism, radical ontic structural realism. According to that, the structure is all there is, and there are only relations without relator. And the second form, more moderate structural realism, is the position according to that there is structure, which is fundamental, but there are also objects or relator that participate in these structural relations. Okay, and there are two, well, there are a lot of very nuanced critics of ontic structural realism, but I would like to focus on the following argument, that actually we have sort of the notion of structure lacks clarity, that we lack a clear conception of structure, what leads presumably to the distinction of difference between the physical and the mathematical. That is, if we say that structure, that mathematical structure of physical theories is all there is, that is the true reality, then it seems that we reduce physics to mathematics. And this is problematic. That is, it is problematic unless we specify what exactly is meant by the thesis that the structure is all there is, that the structure is real. And another point that I would like to mention is this concerns not only the ontic structural realism, but realism in philosophy of physics in general. I would say that it is not always clear what we
mean when we say that certain physical entity, certain concept is real or more fundamental than other physical entities. Like, for example, in these debates regarding the status of gauge fields, what exactly does it mean to say that vector potential is more fundamental or more real than field strength tensor? Okay, and I will try to show that event structure realism can allow to answer these two deficiencies. Okay, that is the problem that I am addressing is how and whether is it possible to reformulate ontic structural realism on a more empiricist basis. And my hypothesis is this, that yes, it is possible using the event ontology framework. Well, what is event ontology about? The key idea is that proposed by some philosophers like Sellers or Reichenbach, is that we can reformulate our talk of objects into talk of events as pure occurrences. That is, for example, as Sellers puts it, instead of saying there is a rectangular expanse of red over there, we could say it rectangularly reds over there, and so on. And this, I would say that this reformulation seemed to be very interesting in the context of philosophy of science, since it can be argued that in science we deal rather with events than with objects. That is, what we observe immediately are rather events than objects, and in this sense, all our observation sentences can be presumably reformulated as sentences about occurrences of some events. And the obvious advantage of this ontology is that we don't need to commit ourselves to existence of some entities, theoretical entities. Instead, we can commit ourselves to existence of immediately observable events. And even if our theory will change, the theoretical entities turn out to not exist. The events that we describe using these entities, the concepts of these entities, cannot cease to exist. Okay, now, and the key aspect of the event ontology that is very important for the application to the structuralism is that actually every co-occurrence or every sum of events can be interpreted as a new event. Okay. Yes, now I would like to try to show how we can reconstruct the ontic structural realism using the event ontology framework. I will try to put it very briefly. The first step, I would say, is to reinterpret the everyday object in terms of this new framework. And it could be argued that all microscopic objects can be described as structured co-occurrences of more fundamental events, namely of interacting molecules. And however, there is a difficulty here because the ontology in this framework is essentially scale relative. That is, we cannot say that microscopic objects constituted by sums of small particles are not fundamental, since if we accept the idea that there are only events and that events are fundamental, then in the world of events, combinations of huge amounts of events can lead to emergence of new kinds of events. And in this sense, we cannot, strictly speaking, say that biology is completely reducible, for example, to particle physics. But at this stage, I would take it for granted that we can consider the most fundamental entities of this framework to be elementary particles and interactions between them. Okay, and now, now I would like to present the first case study. Namely the question about the ontological status of motion of free particles. I propose the following interpretation. We could start with direct observations, and what we observe immediately in case of a non-quantum relativistic particle is its position. Let's suppose that we can observe it for a certain period of time. Then we have to interpret our observations in terms of event ontology. That is, we have to say that what we observe are occurrences of events, particles present at certain points of space-time, and then the sum of all these occurrences would be a new event, namely the event of instantiation of the world line of this particle in the Minkowski spacetime. The fundamental thesis that I propose is that we can argue that the world line is, in a certain sense, more fundamental than so to speak, the occurrences of particles present at singular spacetime points. In other words, we could say that what we immediately observe, that is particles being at a certain point, what we immediately observe, this is not the whole picture, but this is rather only a partial picture, and that we have to reconstruct the whole picture starting from this observance of partial events. In this sense, and this argument is very important for me because it allows actually to answer the question that I raised in the very beginning of my presentation, namely the question about the sense of ontological commitments in the philosophy of physics. I would say that the key idea is that we could, so this is my hypothesis, we could say that for a physical system to be is to instantiate a certain geometric structure in Minkowski spacetime, described by its Lagrangian. And in this sense, I would call this position action realism or world line realism, since the action of a single particle is, for a single particle, is its world line. Okay, and very briefly to the generalization of this approach to the case of gauge fields, I would say that it is possible to generalize the same idea and to say that for let's focus on electromagnetic field, that we can proceed in the same way. We could measure field intensities, and this would be our starting point. And then we could say that this, then we have to reinterpret these observation events as parts of a more complex structure. That is, that events of electric and magnetic field having this or these values are actually part of a more complex event. At first step, we could say that this more complex event is the F tensor of electromagnetic field, and at the second step, we could say that this field tensor itself is, or to put it in a event language, happens to be structured as curvature of U1 fiber bundle over the Minkowski spacetime. In this sense, what is real in the case of electromagnetic field is not field's values in certain spacetime points, but rather the instantiation of the U1 fiber bundle structure over the Minkowski spacetime. That would be my presentation. Thank you for your attention.
Okay, so I see David and Uzi. All right, David first.
What happens in quantum mechanics?
A very good question. Actually, I propose here, as I said, it's still a work in progress. I am very sympathetic to Lagrangian QFT and Hilbert space realism, and I would think, because of the idea of action realism, about past integral reformulation of quantum mechanics, but it's still a work in progress.
Okay, so just as a quick follow-up, I mean, one of the arguments that, as I'm sure you know, drove the development of ontic structural realism is a feeling that there's a lot of underdetermination in physics between mathematical formalisms that physicists regard as completely equivalent, but where one ends up with different ontologies if one tries to do ontology in the same ways. I'm somewhat concerned that this version of ontic structural realism is going to replicate that problem. So in other words, here's your event structural realism defined in terms of the path integral in Hilbert space, and you can imagine somebody else developing an event structural realism that does it in terms of the Hamiltonian formulation and I don't know, Heisenberg operators or something. And again, those are physicists, those are situations that physicists would say, well, these are just reformulations of the same theory, and the structural realism is going to cut rather finer than that. Is that just a price we just need to pay to make this clear on this framework?
Well,
I would agree. I would say that yes, to a certain extent, this reformulation of ontic structural realism actually fits with the basic idea of the classic ontic structural realism, that is to accept this, okay, to solve this problem of underdetermination by proposing the by committing ourselves to existence of structure and not of theoretical entities. Not sure if I answered your question.
Yeah, we're not going to be able to have a second question. So let's thank Anton once again for his presentation. And thanks to all the speakers so far for keeping good time. It's any lapse in the program is my fault rather than theirs. So now we have the home team represented by Sara Vuokko. Sara, would you like to use the mic or the one?
Okay, hello everyone. The aim of my presentation is to give a quick overview of retrocausality and perspectivism in Hugh Price's work. And first I will talk about retrocausality and then go to perspectivism. And I have a question that I want to try to answer here at the end. So what is retrocausality? It's sometimes called also backwards causation or advanced action. And it is like the normal forward causation, but it works backwards in time. And that means that in retrocausality, an effect happens before its cause. One argument or one point in favor of retrocausality is that it is time symmetric. And arguments against retrocausality include, for example, the so-called bilking argument. And according to the bilking argument, retrocausality is not possible because after an effect has already happened, its later cause could be prevented. But Hugh Price argues that the bilking argument doesn't work because there might be other constraints, for example, some physical impossibility to prevent future causes from happening after the effect has already occurred. Retrocausality is an old idea, but one of the important arguments now for retrocausality is that it could explain the behavior of entangled particles in quantum mechanics. In entanglement, when two particles are entangled, it looks like a measurement on one of the particles affects the state of the other one instantaneously, even when the particles are separated by a large distance. The problem is that if the distance is space-like, the effect seems to be faster than light, which is in contradiction with relativity. And in retrocausal explanation, the so-called knowledge that the particles have about each other's state comes from the future measurement settings. Ken Wharton and Hugh Price have written several articles about retrocausality in quantum mechanics. However, earlier this year they wrote a new version of September 2023 paper where they propose a new way of reconciling non-locality with relativity without the postulate of retrocausality. And according to their proposal, Bell correlations could be explained as selection artifacts. And this quote is from the summary part of the article. So they state, "We have shown that in a simple but realistic case, Bell correlations may be regarded as a special sort of pre-selection artifact. produced by ordinary control of the initial conditions of the relevant experiments. We conjecture that the reason this explanation has not been noticed is the sheer familiarity of the initial control concerned. To understand the role it plays, we need to imagine it absent. This step has not previously been taken in this context so far as we are aware. But then about perspectivism. There are several papers and a book, at least one book, on causal perspectivism written by Hugh Price. And more recently, he has talked about pragmatism or neo-pragmatism, which he sees as a global theory that includes causality. According to Price's view, causality could be a perspectival or pragmatic notion. The way an agent, like a human being, sees the world might be different from what the world would look like from some other perspective, according to this view. What makes, in my opinion, Price's views on retrocausality interesting is that for many people, the idea of retrocausality is against their intuition, but at the same time, the normal forward causation seems intuitively obviously true. And Price's causal views seem to go against these common intuitions. So my question is, what is the ontological status of causation if it is at the same time both perspectival and part of the explanation for quantum entanglement? Is causation objective or not? And I sent a similar question to Price via email after the Mind and Matter conference in Helsinki a few years ago. And he suggested that I could look at the dispositional theory of color in one of Price's and Peter Menzies' article called Causation as a Secondary Quality. In that article, they say that there is an analogy between the dispositional theory of color and causality. In the dispositional theory of color, color depends partly on perception, and that is the perspectival aspect of color. Causation, on the other hand, is perspectival because it depends on the agent's agency, so the ability to affect her surroundings. That is something, the causation part is something that, or perspectivity of causation part is something that Price then sorry? Price said that could be focused on, or they don't talk about perspective in the article, but they talk about agency that is perspectival. And in the email, Price also wrote that correlations are objective, and causation is correlation that is perspectival because of the agent. So, to summarize, Price has suggested that the color causation analogy could help with understanding the perspectival aspect of causation. And causality and retrocausality are, in his view, both perspectival, but the correlations underneath are objective. my further question would be, what is the role of retrocausality now that the recent article from Wharton and Price, after in that article they say that they don't probably need retrocausality anymore in the quantum entanglement case, but also Price said that it might be less necessary than they previously thought. So next I would like to figure out maybe that what does the less necessary part mean. Here are the references, and thank you for listening.
And you can use this one. Okay, we have plenty of time for questions. Okay, there's one.
Thanks for the talk. So if I understood you correctly, then Price is saying that the correlations are objective. And of course, the correlations in quantum entanglement are the thing that these different proposals for interpretation usually try to explain. It's not the thing that sort of... So, and then if retrocausality and causality are just sort of perspectival and they're not in the same sense objective, it seems that they cannot offer the explanation. Did I get that sort of bit correctly?
Yeah, well, the correlations are there no matter what. And then the perspectival aspect is what we see there happening in causal situations.
All right. So would you think that Price has given sort of a satisfactory account of entanglement?
Well, that is a good question.
Because it seems to me that he hasn't actually given an account. He's just said that, well, there's this retrocausation thing, but it's not necessary. And then these are objective, these correlations that we were, I think, in physics interested in the first place. It seems like a truism that, of course, are looking at the world as perspectival. But one of the things that I think science tries to do is to have a intersubjective look at things, which means that we try to shed our perspectives as much as possible. Of course, it probably won't be possible to do it all the way. So it seems that the objective correlations are the important bit, the interesting bit for physics.
Yeah. Yeah, thank you.
Thanks. Isn't there an important disanalogy between color and causation in that, in the case of color, what we want to explain is how we perceive color, and that necessarily requires an interaction between our perceptual system and the object that we're observing. But in the case of causation, what we want to explain is causation itself, and that only involves an interaction with the agent when the agent is doing the causing. But in most cases we're interested in, it doesn't.
Well, in the dispositional color theory, color is explained to be partly what we perceive. And of course, there's no similar perception in causality, but then it could be explained with the agency aspect, that the agency carves up the world, like affects the world the way
I agree with that,
Yeah.
but that's only one particular case of causation, right? Most cases of causation don't involve the agent.
The agent, yeah. Well, in the agency theory of price, they have a view that even the things that the agent cannot affect could be affected by a agent that we can imagine of. Like not maybe a human agent, but some kind of agency.
We only have 20 seconds left, so I don't even think I'll bother asking. Let's just thank Sara again. Okay, I think we now have the last of our in-person. No, that was the last of our in-person talks. So now we have some. We're going to go virtual. We're going to go onto Zoom. Now we have Christabel Kane from University College London speaking on the problems of temporary intrinsics. 15 minutes, Christabel, starting now.
Thank you very much. Hi, my name's Christabel, and today I want to talk to you about relationalism, which is the position that I'll be defending in this talk. And the problem, as we'll see, the problems of temporary intrinsics. Let me just get to my, sorry, there's a little bit of a delay. Okay, so the problems, as we'll see, are two. The problems, they simply imply that relationalism isn't compatible with temporary intrinsics. These are properties that are temporary, so they're properties that change within an object's lifetime. And they're intrinsic, which means that they come down entirely to the way that the object itself is. The relationalist has to contend with two possible sources of extrinsicality. We have the classical problem, which is times, and then we've got the updated problem, where the source of extrinsicality is space-time. However, I do think that the relationalist can eliminate these sources of extrinsicality if they adopt these two positions. So the first will be to reject absolute times, and the second will be to endorse a dynamical view of space-time. But what is a relationalist, and why would anyone want to be one? Well, relationalism is first and foremost a solution to the problem of change. Now, this is very simply that the tomato is green all over at one stage and then red all over at some later stage. And yet we want to say that this is the very self-same tomato. However, this seems to contravene Leibniz's law, which states that for any objects A and B, they are only identical if for every property F, A has F if and only if B has F. And this goes for every property. I'm not going to say anything particularly substantial about color. I just wanted to have colorful slides, so that was my example. But it was great that Sara did say some very substantive things about color beforehand. But yes, the problem of change. An intuitive response says something along the lines of, yes, changing objects instantiate these different and often incompatible properties, but they don't instantiate them at the same time. This is a good answer, and indeed, it's what many theorists of persistence avail themselves of by temporally relativizing the instantiation of temporary properties. And I think that relationalism has a particularly neat way of cashing out this temporal relativization function. So they relativize with respect to the property, whereby the temporary property itself is this relation that obtains between the object that instantiates it and the time at which it's instantiated. So instead of saying that the tomato is green, they'll say that it bears the greenness relation to time one. Instead of saying that it's red, for example, they'll say that it bears the redness relation to some later time. The issue is that once the problem of change has been solved in this way, the problem of temporary intrinsics begins to emerge. The problem of temporary intrinsics is just this. All of an object's temporary properties must be extrinsic on the relationalist's model, so extrinsic rather than intrinsic. And we can see that the colors of the changing tomato are no longer entirely down to the way that the tomato itself is, because we've got to make reference to the times at which these colors are instantiated. And these times are external to and distinct from the tomato. But this brings me to the first step of my solution to the problem of temporary intrinsics, which is to simply stop thinking of times as independent of, distinct from, and extrinsic to the times through which they persist. Now, luckily, thinking of times in this way has long since fallen out of fashion, and now we tend to think of objects as intimately interrelated with the times through which they persist. So my paper will build on this new thinking and introduce the idea that objects might intrinsically instantiate at least some of the times through which they persist. So let's consider a tomato that ripens over the course of a working week. I want to introduce metrics A and B as two ways of relativizing the temporary properties of the tomato. Metric A is how the relationalist currently does it, by using datations that are external to the changing object. So if the tomato is green on Monday, orange on Wednesday, and red on Friday, we get the result that these colors are extrinsic, because those days of the week are extrinsic to the tomato. Monday, Wednesday, and Friday would have existed even if the tomato itself hadn't. So I instead proposed that we should use metric B. We temporally relativize to the amount of time that has passed since the tomato was picked, which is to say, since it became an individual object. So let's say that the tomato is still green on the 4th day after it was picked, but it begins to ripen on the 6th day, all the way through to our juicy red tomato on the 8th day. So metric B requires reference to the tomato. So it already looks like we're getting towards a temporal measure that is closer to being intrinsic to it, because these times are in an important sense dependent on the tomato. My solution actually has precedent, as it was suggested by Josh Parsons that we should temporally relativize to times within an object's lifespan. But I want to go further and say that there's no good way of temporally relativizing to metric A, because A implicitly endorses absolute time. Now, we already use metric B when dealing with cases of relative motion, like the twin scenario, for example. I'm sure you all know this, but we have two twins, one of whom stays on Earth and the other of whom travels far away and then back again at a high speed, close to the speed of light. Well, we know that when the traveling twin returns, they will have experienced less time to have passed than the twin who stays on Earth. Now, I think that this shows us that we must relativize to the amount of time that each twin themselves experiences to have elapsed, which is to say metric B. Otherwise, we're liable to commit ourselves to talking all sorts of nonsense. Because the twin paradox discusses aging in that example, I want us to consider the property of wrinkliness. Now, I know this isn't how wrinkles really work, but let's imagine that both twins have great genes such that they'll only get their first wrinkle at 60 years old. Now, according to the earthbound twin, the traveling twin gets their first wrinkles late because more than 60 years have passed since the time and place of their births by her watch. Whereas according to the traveling twin, the earthbound twin gets her first wrinkles early because less than 60 years have passed since the time and place of their births by her watch. But we know that this apparent discrepancy is illusory. We know that it's not that the twins are aging at different rates, it's just that more time has passed for one twin than the other. And this, I think, shows us that it's really important to temporally relativize to metric B. However, this generates what my paper introduces as the second problem of temporary intrinsics. And I'll go through it now. So we start off with this commitment to metric B, which tells us to temporally relativize to an object's proper times. However, the most established understanding of proper times is that they're dependent on an object's world line. And Anton was saying some great stuff about world lines as well. Again, I won't go into too much detail, but it's a sort of given understanding that the proper duration of an object is the function of the geometrical properties of an object's world line. However, the property of having such and such a world line is not a property that an object possesses intrinsically. An object's world line is a set of spatiotemporal points that would have existed even if the object that comes to occupy them had not existed. This means that the object doesn't intrinsically instantiate its proper duration, which means that understood in this way, it does not intrinsically instantiate metric B. Therefore, all the relationalist is doing when they're relativizing to metric B is relativizing to times that are extrinsic to the object, just like before when they relativized to absolute times with metric A. In conclusion, the relationalist's object still lacks these temporary intrinsics, just as before. The temporary intrinsics are intrinsic to a region of space-time, which is to say the set of spatiotemporal points that constitute the object's world line, but not to the object that occupies this region. Well, this brings me to the second part of my solution, which is to endorse a dynamical view of spacetime and to reject a geometrical view of spacetime. So geometrical views of spacetime hold that an object only behaves in the way that it does because spacetime has the structural features that it has. This implies that the processes that an object undergoes are extrinsically instantiated rather than intrinsically, because processes are either properties of the spacetime that the object inhabits or relations between the object and the spacetime that it inhabits. Whereas, on the other hand, proponents of the dynamical view of spacetime hold that this gets the direction of explanation completely wrong. Instead, they hold that spacetime can only be said to have the geometrical features that it has because objects behave in the law-like manner in which they do. This implies that processes instantiated by an object are intrinsic to it, because processes ground both the properties of spacetime and also, I'll argue, the object's intrinsic times, which implies that the object does intrinsically instantiate metric B. This is because we don't need to make reference to a world line in order to explain an object's proper duration. Now, the main proponents of the dynamical view of spacetime, like James Reed, Harvey Brown, thank you, acknowledged, like James Reed, Harvey Brown, and Oliver Pooley, all focus on the Lorentz invariant dynamic behavior of objects. So processes like length contraction and time dilation in relative motion. However, our relationalist who endorses a dynamical view of spacetime can use whatever dynamic behavior they like to ground this notion of intrinsically instantiated temporal passage. And I'm thinking like thermodynamic processes, motion, subatomic processes, or even entropy, depending on what kind of object we're looking at. And as Wayne Marvell points out, space-time symmetries will always coincide with dynamical symmetries, so the relationalist can still help themselves to the same quantity of time as expressed by the proper time, but they don't need to make reference to an object's location in space-time. So the relationalist who endorses this dynamic view essentially sees each object as a non-ideal clock that measures out the amount of time that has passed in virtue of undergoing the dynamic behavior that it undergoes. So this kind of relationalist will think of change as more basic than time, rather than using time to explain change, which turns the problem of temporary intrinsics on its head somewhat, which I think is really exciting. So, to summarize, we can see that we have two problems and two solutions. The first, classical problem, complains that on the relationalist's model, temporary properties can't be intrinsic because we have to make reference to the times at which these properties are instantiated. We saw that the solution to this problem is of very low cost for the relationalist to adopt because we've got plenty of independent motivation to reject absolute times. I proposed instead that we had to relativize to metric B, or this amount of time that an object experiences to have passed since it's coming into being. But I hope that I've shown that this generates a second updated problem of temporary intrinsics, whereby instead of grounding an object's temporary properties with the times at which they're instantiated, we grounded them with reference to their location in space-time. My paper's response was to endorse a dynamical view of space-time, whereby objects carry with them their own intrinsic times in virtue of undergoing these dynamic processes, and we relativize to these intrinsic times. So, if the relationalist is still with me after this talk, they're going to posit temporary intrinsics as relations that obtain between the object that instantiates them and the intrinsic times of that object as given by the dynamic processes that they undergo. And that, my friends, is how I think the problem of temporary intrinsics is best solved. Thank you so much for having me and for listening. My email is on the slide, so do get in contact if you've got any feedback or reading recommendations from me.
Thank you very much, Chrisley. Okay, we do have a couple questions.
Oh, great.
Hey, thanks. So I think you're on the right track with the idea that space-time, we should make it dynamic, because then you can explain the passage of time. And the project of trying to explain away our experiences of passage of time without dynamics is really desperate. So at least that dynamic part I support. Thanks.
Thank you. Yes, and I think my relationalist has a fair bit of leeway into what kind of philosophy of time they need to adopt in a more global sense, just so long as they have these intrinsic times, which are given dynamically, that maybe they can endorse a geometrical view in a more sort of global sense. Like you have some problems where there are changeless regions of space-time, and how do we ground time passing in these changeless regions? And it strikes me that my relationalist isn't completely married to the dynamical view, but they could be if they have other sort of instrumental reasons for being so. But yeah, thank you for your comment.
I think maybe in the end of the answer you just gave there, you were sort of getting onto what I was going to suggest. I'm just sort of sketching this out. I might be missing the mark a little bit. But could you not also consider an option where instead of objects moving through space-time and the problems there being a reason to sort of move away from a geometric conception of space, could you instead identify objects with space-time regions? So so that an object, that's all that an object is, a space-time region which is variously colored along the time dimension. So it's that's what I would say. And then you maintain a sort of familiar geometric conception of space-time.
Well, that completely dispenses with the second part of my solution. And I think Liljenström, a French physicist, identifies an object with its world line. So of course, the second problem of temporary intrinsics doesn't even arise for that view of objects. And I think it's compelling in a number of ways. I worry about identifying objects with regions of space-time, kind of for reasons to do with essences. Do regions of space-time and objects have exactly the same essential properties, modal properties? But I really see the sort of attraction of identifying an object with a spatiotemporal region. I think it does make it easier to cash out some of the kind of non-modal properties of the object. So yeah, kind of depending on your view of modal properties, that sort of response could be more or less attractive.
Thank you for that. We're out of time, so we can't have any more questions right now. But let's thank Christabel once more for her presentation.
Thank you so much for having me.
I can announce our final speaker, I believe, of the day and of the meeting. It's Luca Gasperinetti from the Università della Svizzera Italiana. And the topic is time, causation, and quantum gravity, a first assessment.
So, hi everyone. Nice to meet you all, and thank you for being here, at least online. So today I just give you a brief talk on time causation and quantum gravity, and I will give you a first assessment of my research. So first of all, I would like to set the stage and put on the table the main question, namely, is there causation in fundamental physics? So basically, in the literature, there are a bunch of people that defend the view that there is no fundamental causation, from Mach and Russell to Price and Herman, for instance. They have endorsed this view. And so my question is, what if we tackle this claim, so there is no fundamental causation, or better, this issue, in light of recent development in cutting-edge physics, namely quantum gravity? So my research basically endorses this general aim, namely, I would like to assess whether or not there are different approaches to quantum gravity. And basically, quantum gravity is the theory that combines the principles of general relativity with those of quantum mechanics, or better, quantum field theory. And yes, generally, my aim is to assess whether or not these approaches, because there is no a full-fledged theory of quantum gravity so far, so there are several approaches that we will see later. And my aim, my general issue is whether we can find the causation. Oh, sorry, this is okay. Whether we can find causation in these approaches. So basically, I divide the approaches in two main groups, namely causal approaches, which are those approaches that explicitly are committed explicitly to causation. And this is the case for instance, causal set theory and causal dynamical triangulation. But also there are also other approaches that are not explicitly committed to causations, like string theory or loop quantum gravity. So here is the structure of this brief talk. So first of all, I will give you a primer on causation in fundamental physics. Then I will review one approach of the causal approaches to quantum gravity, and then I will get to a tentative conclusion. So let's start with the first part of this talk, namely, let's address causation in fundamental physics. So again, the question is there causation in fundamental physics? And again, for instance, Russell says, the law of causality, like much that passes muster among philosophers, is a relic of bygone age, surviving, like the monarchy, only because it is erroneously supposed to do no harm. So based on this text, people, based on Russell considerations, people have defended the view called causal republicanism, which is basically the view that there is no causation in fundamental physics. Causation doesn't have any role, but is still used in some upper sciences like biology, for instance. As an example, here is Price and Corey. Although the notion of causation is useful, perhaps indispensable in our dealing with the world, it's a category provided neither by God nor by physics, but rather constructed by us. And so, for instance, people have raised also nowadays several what has been called by Frisk neo-Russellian challenges, which basically have a common structure, which has been showed by Ney. So the structure is of these challenges is basically that they aim to show that fundamental physical theories are incapable of grounding causation. So it appears illegitimate to claim that causation plays a role in such theories. So for instance, there is the vagueness challenge, which is basically causal notions are vague in some sense, which is in contrast with the precise mathematical formalism of physical theories. Or also there is the so-called time asymmetry challenge, which basically amounts to, my dog, sorry. Which basically amounts to the fact that time is symmetric, and laws of nature are symmetric, while causation is asymmetric. And so basically my genuine question is that there might be new challenges also in the domain of quantum gravity, namely what kind of challenges, if there are any, obviously, could theories of quantum gravity raise for fundamental causation? So to just give you an idea of what I'm working on, I would like to deal with the first step of my research, namely address causal approaches to quantum gravity. And basically the idea that there are lots of approaches that explicitly appeal to causation to build up a theory of quantum gravity. So there is just a brief list. So causal set theory, energetic causal set models, causal quantum histories, and causal dynamical triangulations are examples of such approaches. So just to give you an idea, let's consider, for instance, causal set theory. In a nutshell, causal set theory, we can, in some sense, say that the geometry, they hold that the geometry of space-time can be recovered from the causal structure, so the fundamental and discrete causal structure, which is opposed to the smooth and continuous from the emergent space-time in some sense. And the basic, the building blocks of this theory is the so-called causal set, which is an ordered pair of featureless events ordered by a causal precedence relation. And this precedence relation is antisymmetric, reflexive, and transitive. So to give you a rough idea, in this picture, we can see a causal set. What's important here is that in causal set theory, as you can also infer from the name, it seems that we are dealing with causation. And this is the case for Wüthrich and Lamb, as they write. In causal set theory, the fundamental relation is causal rather than temporal. So temporal relations are supposed to emerge from the structure of the causal set. So strictly speaking, there is no time in causal set theory. More impressionistically, the causal precedence relation looks like a discrete spatial relativistic time without metric relations such as durations. So it's clear that the authors, they are claiming that causal relations exist while temporal relation does not. And so causal set theory, at least taken at face value, is explicitly committed to fundamental causation. Pace, Russell, and Mach, for instance. However, some people in the literature have raised concerns about this claim, and for instance, they describe their concern in terms of the temporal set theory instead of calling causal set theory. So it seems that here we are dealing with a metaphysical issues, which basically amounts to define whether time derives from causation or it's causation that derives from time. So, for instance, here is Docker, who basically says that in GR, in general relativity, the space-time causal order is a relation of precedence, of before and after, not of causation. So she says, more importantly, the ambiguous term of causal order is used because the space-time chronological relation is defined by the time-lag curves. And to distinguish this from the relation defined by time-lag or null-lag curves, the term causal relations is used for the latter relation. So the naive non-causal set has therefore inherited this confusion from the continuum GR. The order of a causal set is an order of precedence and not of causation. So temporal set might have been a better name, but it's too late to change it now. So it's clear that for some people in causal set theory, we are dealing with causation, a case for fundamental causation. On the other side, there are people, and for instance, a physicist in this case, that basically says that no, these people are wrong. Causal set theory is just a temporal set theory. So to get to tentative conclusion, it's important to note that despite the talks in terms of causation, as for causal set theory, it's not straightforward to say that there is causation in causal set. So there are also other approaches for causal set theory, for quantum gravity. They're dealing with causal notions, but obviously they remain to be investigated in the future research. So thank you.
Thank you very much, Luca.
Thank you.
I'll just see if there are any questions here. It has been a long day here, Luca, so...
I can imagine.
There is one, at least.
Okay, thanks, Luca.
Thank you.
Okay, suppose first that space-time is dynamic and the past was caused. I mean, the future or the present was caused by the past. Suppose first that. Then you can explain, for instance, like why we have memories of the past, because they were transferred along with the causal succession of events until the future. But then, okay, suppose that it's not dynamic, there's no causation, and the past did not cause the present. So why do we have memories of the past? You know, there's difficult questions that cannot be answered if you don't accept causality. So that's my notion. Thanks.
Yeah, but I agree with you, because there are some people in the literature, especially in quantum physics, or also, for instance, space-time physics, that basically accept the existence of causation, but it's not clear from a metaphysical point of view which kind of causation are we dealing with. As for instance, in this brief talk, I completely didn't address the metaphysical question regarding causation, because there are several approaches to causation, but for instance, the counterfactual, or the regularity theory, or the conceptual quantity approach. But yes, I agree with you. But also, there are other physicists that believe that at least causation, in some sense, emerges from a fundamental level where there are no causal relations. For instance, Rovelli, the Italian physicist, believes that in loop quantum gravity there are no causal relations, and such relations emerge thanks to the thermodynamic asymmetry, so related to the increasing of entropy. So yes, I share your point. I agree with your point. Yes.
Okay. Are there any other questions for Luca? If not, okay, we're going to thank you one more time, Luca. And now the session's over, and I hand the mic over to Paavo.
Okay, so just a couple of more things here. A small but maybe important thing, those of you going to the boat, of course, so we will meet here and leave roughly 6:30 toward the boat. It's not as warm as you have probably noticed, but it's not as warm as it used to be. So, you know, take something like this sweater with you for the boat. I mean, we're going to be inside in the restaurant, so it should be okay, but it's not as hot as it was. So, especially if you want to hang out a little bit later and see the island after, or whatever may happen there. If there might even be a bar there or bar here. We might end up in the Bryggeri again, where we have been at some stage. Yesterday there was a terrible party. I mean, not a terrible, but it was a surprisingly loud party, dancing. I mean, you know, we didn't plan it, nothing like that. But then tonight it's going to be more calm. So if people want to even discuss, it's probably more possible. Now, finally, I mean, I've been getting a lot of thanks from the speakers, partly because I've been kind of interacting, inviting them, but of course it's the entire team who's been working, our helpers, with some of them with this black T-shirt. We have, and of course in the planning, it's been Tuomas Suntula and Avril and Petri and the others, and so planning and putting together the program. But perhaps especially hard work has been done by our conference managers, Saara Vuokko. She has taken the tough, there are always tough times when you're doing a conference. So suddenly some things takes a lot of time, and so she has really done an excellent job there. And because, you know, as far as I can tell, it's been going pretty smoothly, and thanks especially to Saara for that.